Dialectics of Nature, Friedrich Engels, 1883, Notes and Fragments. From the History of Science. The successive development of the separate branches of natural science should be studied. First of all, astronomy, which, if only on account of the seasons, was absolutely indispensable for pastoral and agricultural peoples. Astronomy can only develop with the aid of mathematics, hence this also had to be tackled. Further, at a certain stage of agriculture and in certain regions, raising of water for irrigation in Egypt, and especially with the origin of towns, big building structures, and the development of handicrafts, mechanics also arose. This was soon needed also for navigation and war. Moreover, it requires the aid of mathematics and so promotes the latter's development. Thus, from the very beginning, the origin and development of the sciences has been determined by production. Throughout antiquity, scientific investigation proper remained restricted to those three branches, and indeed in the form of exact, systematic research, it occurs for the first time in the post-classical period, the Alexandrines, Archimedes, etc. In physics and chemistry, which were as yet hardly separated in men's minds, in parentheses, theory of the elements, absence of the concept of a chemical element. In botany, zoology, human and animal anatomy, it had only been possible until then to collect facts and arrange them as systematically as possible. Physiology was sheer guesswork, as soon as one went beyond the most tangible things, for example digestion and excretion, and it could not be otherwise when even the circulation of the blood was not known. At the end of the period, chemistry makes its appearance in the primitive form of alchemy. If, after the dark night of the Middle Ages was over, the sciences suddenly arose anew with undreamt-of force, developing at a miraculous rate, once again we owe this miracle to production. In the first place, following the Crusades, industry developed enormously and brought to light a quantity of new mechanical, in parentheses, weaving, clockmaking, milling, chemical, in parentheses, dyeing, metallurgy, alcohol, and physical, in parentheses, spectacles, facts, and this not only gave enormous material for observation, but also itself provided quite other means for experimenting than previously existed, and allowed the construction of new instruments. It can be said that really systematic experimental science now became possible for the first time. Secondly, the whole of West and Middle Europe, including Poland, now developed in a connected fashion, even though Italy was still at the head, owing to its old inherited civilization. Thirdly, geographical discoveries, made purely for the sake of gain, therefore in the last resort of production, opened up an infinite and hitherto inaccessible amount of material, of a meteorological, zoological, botanical, and physiological, in parentheses human, bearing. Fourthly, there was the printing press. Note in the margin, quote, "Hitherto what has been boasted of is what production owes to science, but science owes infinitely more to production." Unquote. End of note in the margin. Now, apart from mathematics, astronomy, and mechanics, which were already in existence, physics becomes definitely separate from chemistry. Torricelli, Galileo, the former in connection with industrial waterworks, studied first of all the movement of liquids. See Clerk Maxwell. Boyle put chemistry on a stable basis as a science. Harvey did the same for physiology, human and animal, by the discovery of the blood circulation. Zoology and botany remain at first collecting sciences until paleontology appeared on the scene, Cuvier, and shortly afterwards came the discovery of the cell and the development of organic chemistry. Therewith, comparative morphology and physiology became possible, and from then on both are true sciences. Geology was founded at the end of the last century, in parentheses 18th century, and recently anthropology, badly so called, enabling the transition from the morphology and physiology of man and human races to history. This to be studied further in detail and to be developed. The Ancients' Outlook on Nature. Hegel, Geschichte der Philosophie, Volume 1, Greek Philosophy. Footnote: G.W.F. Hegel, Works, Volume 13, Berlin, 1833. End of footnote. Of the first philosophers, Aristotle says, in parentheses Metaphysics 1 and 3, that they assert, quote, that of which all things consist, from which they first come and into which they are ultimately resolved, of which the essence, ousia, persists, although modified by its affections, pakesi, this is the element, stoiketon, and principle, arche, of all being. Hence they believed that nothing is either generated, ute gigneska oden, or destroyed, since this kind of primary entity always persists. Unquote. Page 98. Here, therefore, is already the whole original spontaneous materialism, which at its beginning quite naturally regards the unity of the infinite diversity of natural phenomena as a matter of course, and seeks it in something definitely corporeal, a particular thing, as Thales does in water. Cicero says, quote, Thales of Miletus declared that water is the basis of things, and God, that mind that forms everything out of water. Unquote. De Natura Deorum, Book 1, page 10. Hegel quite rightly declares that this is an addition of Cicero's, and says, quote, however, we are not concerned here with this question, whether in addition Thales believed in God. It is not a matter here of supposition, belief, popular religion, and even if he spoke of God as having created all things from that water, we would not thereby know anything more of this being. It is an empty word without its idea. Unquote. Page 209. In parentheses, circa 600 BC. The oldest Greek philosophers were at the same time investigators of nature. Thales, a geometrician, fixed the year at 365 days, and is said to have predicted a solar eclipse. Anaximander constructed a sun clock, a kind of map, perimetron, of land and sea, and various astronomical instruments. Pythagoras was a mathematician. Anaximander of Miletus, according to Plutarch, Questiones Convivales, Book 8, page 8, makes, quote, man come from a fish, emerging from the water onto the land, unquote. Page 213. For him, the archai, stoikeion to aperon, in parentheses, beginning an element is the infinite. Without determining the arisen, it as air or water or anything else. Diogenes Laertius, Book 2, paragraph 1. This infinite, correctly reproduced by Hegel, page 215, as, quote-unquote, undetermined matter, in parentheses, circa 580 BC. Anaximenes of Miletus takes air as principal and basic element, declaring it to be infinite, in parentheses, Cicero, De Natura Deorum, Book 1, page 10, and that, quote, everything arises from it, in it everything is again dissolved, unquote. Plutarch, De Placitis Philosophorum, Book 1, page 3. Here air, ar, equals pneuma, in parentheses, breath, spirit. Quote, just as our soul, which is air, holds us together, so also a spirit, pneuma, and air hold the world together. Spirit and air have the same meaning, unquote. Plutarch, pages 215 to 16. Footnote. Regarding the work De Placitis Philosophorum, it was subsequently proved that it did not come from Plutarch, but some other unknown author, the so-called pseudo-Plutarch. It derives from Aetius, who lived in about the year 100 of our era. End of footnote. Soul and air conceived as a general medium, circa 555. Aristotle already says that these ancient philosophers put the primordial essence in a form of matter, air and water, and perhaps Anaximander in something midway between both. Later Heraclitus in fire, but none in earth, on account of its multiple composition. Diathen Megalomereian, Metaphysics, Book 1, 8, page 217. Aristotle correctly remarks of all of them that they leave the origin of motion unexplained. Page 218 et seq. Pythagoras of Samos, circa 540, number is the basic principle. Quote, that number is the essence of all things, and the organization of the universe as a whole in its determinations is a harmonious system of numbers and their relations. Unquote. Aristotle, Metaphysics, Book 1, 5, Passim. Hegel justly points out, quote, the audacity of such language, which at one blow strikes down all that is regarded by the imagination as being, or as essential, in parentheses true, and annihilates the sensuous essence, unquote, and puts the essence in a thought determination, even if it is a very restricted and one-sided one. Pages 237 to 38. Just as number is the subject to definite laws, so also the universe. Hereby its obedience to law was expressed for the first time. To Pythagoras is ascribed the reduction of musical harmonies to mathematical relations. Likewise, quote, the Pythagoreans put fire in the center, put earth as a star which revolves in a circle around this central body. Unquote. Aristotle, De Coelo, Book 2, 13, page 265. This fire, however, is not the sun. Nevertheless, this is the first inkling that the earth moves. Hegel on the planetary system, quote, the harmonious element which determines the distances between the planets, all mathematics has still not been able to give any basis for it. The empirical numbers are accurately known, but it has all the appearance of chance, not of necessity. An approximate regularity in the distances is known, and thus with luck, planets between Mars and Jupiter have been guessed at, where later Ceres, Vesta, Pallas, etc. were discovered. But astronomy still did not find a consistent series in which there was any sense, any reason. Rather it looks with contempt on the regular presentation of this series. For itself, however, it is an extremely important point which must not be surrendered. Unquote. Page 267 to 68. For all the naive materialism of the total outlook, the kernel of the later split is already to be found among the ancient Greeks. For Thales, the soul is already something special, something different from the body, just as he described the soul also to the magnet. For Anaximenes, it is air, as in Genesis. Footnote, Genesis chapter 2, verse 7. End of footnote. For the Pythagoreans, it is already immortal and migratory, the body being purely accidental to it. For the Pythagoreans also, the soul is, quote, a chip of the ether, apospasma aikeros, unquote. Diogenes Laertius, Book 8, page 26 to 28, where the cold ether is the air, the dense ether the sea and moisture. Pages 279 to 80. Aristotle correctly reproaches the Pythagoreans also. With their numbers, quote, they do not say how motion comes into being and how, without motion and change, there is coming into being and passing away, or states and activities of heavenly things. Unquote. Metaphysics, Book 1, 8, in parentheses, page 277. Pythagoras is supposed to have discovered the identity of the morning and evening star, that the moon gets its light from the sun, and finally the Pythagorean theorem. Quote, Pythagoras is said to have slaughtered a hecatomb on discovering this theorem, and however remarkable it may be that his joy went so far on that account as to order a great feast, to which the rich and the whole people were invited, it was worth the trouble. It is joyousness, joy of the spirit, knowledge, at the expense of the oxen. Unquote. Page 279. The Eleatics. Leucippus and Democritus. Footnote. This note is written in Marx's handwriting and consists of quotations from Tauchnitz editions in Greek from Aristotle's Metaphysica and from the compilatory work of Diogenes Laertius, Lives and Opinions of Famous Philosophers. The note dates from before June 1878, since it contains quotations about Epicurus, which were used by Engels in the old preface to Anti-Düring. End of footnote. Quote, Leucippus, however, and his disciple Democritus hold that the elements are the full and the void, calling the one what is and the other what is not. Of these they identify the fall or solid with what is, that is, the atoms, and the void or rare with what is not. Hence they hold that what is not is no less real than what is, and they say that these are the material causes of things. And just as those who make the underlying substance a unity generate all other things by means of its modifications, so these thinkers hold that the differences, namely of the atoms, are the causes of everything else. The differences, they say, are three: shape, arrangement, and position. Thus, for example, A differs from N in shape, AN from NA in arrangement, and Z from N in position. Unquote. Aristotle, Metaphysics, Book 1, Chapter 4. Leucippus, quote, was the first to set up atoms as general principles, and these he calls elements. Out of them arise the worlds unlimited in number, and into them they are dissolved. This is how the worlds are formed. In a given section, many atoms of all manner of shapes are carried from the unlimited into the vast empty space. These collect together and form a single vortex, in which they jostle against each other and, circling round in every possible way, separate off, by like atoms joining like, and the atoms being so numerous that they can no longer revolve in equilibrium, the light ones pass into the empty space outside, as if they were being winnowed. The remainder keep together and become entangled, go on their circuit together, and form a primary spherical system. Unquote. Diogenes Laertius, Book 9, Chapter 6. The following about Epicurus. Quote, the atoms are in continual motion through all eternity. Further, he says below that the atoms move with equal speed, since the void makes way for the lightest and heaviest alike. Atoms have no quality at all except shape, size, and weight. They are not of any and every size. At any rate, no atom has ever been seen by our senses. Unquote. Diogenes Laertius, Book 10, paragraphs 43 to 45. Quote, when they are traveling through the void and meet with no resistance, the atoms must move with equal speed. Neither will heavy atoms travel more quickly than small and light ones, so long as nothing meets them, nor will small atoms travel more quickly than large ones, provided they always find a suitable passage, and provided also that they meet with no obstruction. Unquote. Ibid, paragraph 61. Quote, thus it is clear that in every kind of things, the one is of a definite nature, and that in none of them does this, the one, have its nature. Unquote. Aristotle, Metaphysics, Book 9, Chapter 2. Footnote. In the latest editions of Metaphysica, Book 9 is called Book 10. End of footnote. Aristarchus of Samos, 270 BC, already held the Copernican theory of the earth and sun. Medler, page 44, Wolf, pages 35 to 37. Footnote. R. Wolf, Geschichte der Astronomie, History of Astronomy, München, 1877. For Medler's book, see note 22. End of footnote. Democritus had already surmised that the Milky Way sheds on us the combined light of innumerable small stars. Wolf, page 313. Difference between the situation at the end of the ancient world, circa 300, and at the end of the Middle Ages, 1453. 1. Instead of a thin strip of civilization along the coast of the Mediterranean, stretching its arms sporadically into the interior and as far as the Atlantic coast of Spain, France, and England, which could thus easily be broken through and rolled back by the Germans and Slavs from the north and by the Arabs from the southeast, there was now a closed area of civilization, the whole of West Europe with Scandinavia, Poland, and Hungary as outposts. 2. Instead of the contrast between the Greeks or Romans and the barbarians, there were now 6 civilized peoples with civilized languages, not counting the Scandinavians, etc., all of whom had developed to such an extent that they could participate in the mighty rise of literature in the 14th century, and guaranteed a far more diversified culture than that of the Greek and Latin languages, which were already in decay and dying out at the end of ancient times. 3. An infinitely higher development of industrial production and trade created by the burghers of the Middle Ages. On the one hand, production more perfected, more varied and on a larger scale, and on the other hand, commerce much stronger, navigation being infinitely more enterprising since the time of the Saxons, Frisians and Normans, and on the other hand, also an amount of inventions, and importation of Oriental inventions, which not only for the first time made possible the importation and diffusion of Greek literature, the maritime discoveries, and the bourgeois religious revolution, but also gave them quite a different and quicker range of action. In addition, they produced a mass of scientific facts, although as yet unsystematized, such as antiquity never had, the magnetic needle, printing, type, flax paper, used by the Arabs and Spanish Jews since the 12th century, cotton paper gradually making its appearance since the 10th century, and already more widespread in the 13th and 14th centuries, papyrus quite obsolete in Egypt since the Arabs, gunpowder, spectacles, mechanical clocks, great progress both of chronology and of mechanics. See page 11 of the manuscript concerning inventions. In addition, material provided by travels, in parentheses Marco Polo, circa 1272, etc. General education, even though still bad, much more widespread owing to the universities. With the rise of Constantinople and the fall of Rome, antiquity comes to an end. The end of the Middle Ages is indissolubly linked with the fall of Constantinople. The new age begins with the return to the Greeks, negation of the negation. Historical material. Inventions. BC. Fire hose, water clock, circa 200 BC. Street paving, in parentheses Rome. Parchment, circa 160. AD. Water mills on the Moselle, circa 340. In Germany in the time of Charles the Great. First signs of glass windows. Street lighting in Antioch, circa 370. Silkworms from China, circa 550 in Greece. Quill pens in the 6th century. Cotton paper from China to the Arabs in the 7th century, in the 9th in Italy. Water-powered organs in France, in the 8th century. Silver mines in the Harz, worked since the 10th century. Windmills, about 1000. Notes, Guido of Arezzo's musical scale, about 1000. Sericulture introduced in Italy, about 1100. Clocks with wheels, ditto. Magnetic needle from the Arabs to the Europeans, circa 1180. Street paving in Paris, 1184. Spectacles in Florence, glass mirrors, second half of the 13th century. Herring salting, sluices, striking clocks, cotton paper in France. Rag paper, beginning of 14th century. Bills of exchange, middle of ditto. First paper mill in Germany, in parentheses Nuremberg. 1390. Street lighting in London, beginning of 15th century. Post in Venice, ditto. Woodcuts and printing, ditto. Copper engraving, middle ditto. Horse post in France, 1464. Silver mines in Saxon Erzgebirge, 1471. Pedal clavichord invented, 1472. Pocket watches, air guns, flintlock, end of 15th century. Spinning wheel, 1530. Diving bell, 1538. Historical. Footnote. This fragment constitutes the original outline of the introduction. See this edition, pages 20 to 39. End of footnote. Modern natural science, the only one which can come into consideration qua science, as against the brilliant intuitions of the Greeks and the sporadic, unconnected investigations of the Arabs, begins with that mighty epoch when feudalism was smashed by the burghers. In the background of the struggle between the burghers of the towns and the feudal nobility, this epoch showed the peasant in revolt, and behind the peasant the revolutionary beginnings of the modern proletariat, already red flag in hand, and with communism on its lips. It was the epoch which brought into being the great monarchies in Europe, broke the spiritual dictatorship of the Pope, evoked the revival of Greek antiquity, and with it the highest artistic development of the new age, broke through the boundaries of the old world, and for the first time really discovered the world. It was the greatest revolution that the world had so far experienced. Natural science also flourished in this revolution, was revolutionary through and through, advanced hand in hand with the awakening modern philosophy of the great Italians, and provided its martyrs for the stake and the prisons. It is characteristic that Protestants and Catholics vied with one another in persecuting it. The former burnt Servetus, the latter Giordano Bruno. It was a time that called for giants and produced giants, giants in learning, intellect, and character, a time that the French correctly called the Renaissance, and Protestant Europe, with one-sided prejudice, called that of the Reformation. At that time, natural science also had its declaration of independence, though it is true it did not come right at the beginning, any more than that Luther was the first Protestant. Footnote. The Declaration of Independence, adopted on July 4, 1776 at the Philadelphia Congress of Delegates from 13 English colonies in North America, proclaimed the secession of the colonies from England and the establishment of an independent republic, the United States of America. End of footnote. What Luther's burning of the papal bull was in the religious field, in the field of natural science was the great work of Copernicus, in which he, although timidly, after 36 years' hesitation, and so to say on his deathbed, threw down a challenge to ecclesiastical superstition. From then on, natural science was in essence emancipated from religion, although the complete settlement of accounts in all details has gone on to the present day, and in many minds is still far from being complete. But from then on, development of science went forward with giant strides, increasing, so to speak, proportionately to the square of the distance in time from its point of departure, as if it wanted to show the world that for the motion of the highest product of organic matter, the human mind, the law that holds good is the reverse of that for the motion of inorganic matter. The first period of modern natural science ends in the inorganic sphere with Newton. It is the period in which the available subject matter was mastered. It performed a great work in the fields of mathematics, mechanics, and astronomy, statics and dynamics, especially owing to Kepler and Galileo, from whose work Newton drew the conclusions. In the organic sphere, however, there was no progress beyond the first beginnings. The investigation of the forms of life, historically succeeding one another and replacing one another, as well as the changing conditions of life corresponding to them, paleontology and geology, did not yet exist. Nature was not at all regarded as something that had developed historically, that had a history in time. Only extension in space was taken into account. The various forms were grouped, not one after the other, but only one beside the other. Natural history was valid for all periods, like the elliptical orbits of the planets. For any closer analysis of organic structure, both the immediate bases were lacking, viz., chemistry and knowledge of the essential organic structure, the cell. Natural science, at the outset revolutionary, was confronted by an out-and-out conservative nature, in which everything, remaining today as it was at the beginning of the world, and in which, right to the end of the world, everything would remain as it had been in the beginning. It is characteristic that this conservative outlook on nature, both in the inorganic and in the organic sphere, ... The first breach, Kant and Laplace. The second, geology and paleontology. In parentheses, Lyell, slow development. The third, organic chemistry, which prepares organic bodies and shows the validity of chemical laws for living bodies. The fourth, 1842, mechanical theory of heat, Grove. The fifth, Darwin, Lamarck, the cell, etc. In parentheses, struggle, Cuvier and Agassiz. The sixth, the comparative element in anatomy, climatology, in parentheses, isotherms. Animal and plant geography, in parentheses, scientific travel expeditions since the middle of the 18th century. Physical geography in general, in parentheses, Humboldt. The assembling of the material in its interconnection, morphology, embryology, Bayer. Editor's note. Up to this point, the text of the note has been crossed out in the manuscript by a vertical stroke, as having been used by Engels in the first part of the introduction. See this volume, pages 20 to 31. The two further paragraphs, partially used in the second part of the introduction, pages 31 to 39, were not crossed out. End of editor's note. The old teleology has gone to the devil, but it is now firmly established that matter in its eternal cycle moves according to laws which, at a definite stage, now here, now there, necessarily give rise to the thinking mind in organic beings. The normal existence of animals is given by the contemporary conditions in which they live and to which they adapt themselves. Those of man, as soon as he differentiates himself from the animal in the narrower sense, have as yet never been present and are only to be elaborated by the ensuing historical development. Man is the sole animal capable of working his way out of the mere animal state. His normal state is one appropriate to his consciousness, one that has to be created by himself. Omitted from quote-unquote Feuerbach. Footnote. This is the heading of the fragment given in the list of contents of the second folder of materials for Dialectics of Nature. The fragment consists of 4 pages of the original manuscript of L. Feuerbach, numbered 16, 17, 18, and 19. At the top of page 16 is written in Engels' handwriting, Aus Ludwig Feuerbach. This fragment was part of the second chapter of L. Feuerbach, and was intended to follow immediately after the description of the 3 principal quote-unquote limitations of the French materialists of the 18th century. On finally revising the manuscript of L. Feuerbach, Engels removed these 4 pages and replaced them by another text, but the basic contents of these pages, left out of the second chapter, in parentheses, on the 3 great discoveries in natural science of the 19th century, were reproduced in an abbreviated form in the 4th chapter of L. Feuerbach. Since Engels' L. Feuerbach was originally printed in the April and May issues of the magazine Die Neue Zeit for 1886, it can be considered that this fragment dates from the first quarter of 1886. On the first page of the fragment, the text begins in the middle of a sentence. The beginning of the sentence, restored according to the text of L. Feuerbach, printed in Die Neue Zeit, is given in square brackets. End of footnote. In square brackets, the vulgarizing peddlers who dealt in materialism in Germany of the 50s in no wise went beyond these limits of their teachers. All the advances made by natural science since then served them merely, end of square bracket, as fresh arguments against the belief in a creator of the universe, and in fact, the further development of theory was quite outside their line of business. Idealism was hard hit owing to 1848, but materialism in this renovated form of it sank still lower. Feuerbach was absolutely right in repudiating responsibility for this materialism, only he had no right to confuse the doctrine of the itinerant preachers with materialism in general. At about the same time, however, empirical natural science made such an advance and arrived at such brilliant results that not only did it become possible to overcome completely the mechanical one-sidedness of the 18th century, but also natural science itself, owing to the proof of the interconnections existing in nature itself between the various fields of investigation, mechanics, physics, chemistry, biology, etc., was transformed from an empirical into a theoretical science, and by generalizing the results achieved, into a system of the materialist knowledge of nature. The mechanics of gases, newly created organic chemistry, which stripped the last remnants of incomprehensibility from one so-called organic compound after another by preparing them from inorganic substances, scientific embryology dating from 1818, geology and paleontology, comparative anatomy of plants and animals, all these furnished new material in an unprecedented measure. Three great discoveries, however, were of decisive importance. The first was the proof of the transformation of energy arising out of the discovery of the mechanical equivalent of heat by Robert Meyer, Joule, and Quadling. All the innumerable acting causes in nature, which had hitherto led a mysterious, inexplicable existence as so-called forces, mechanical force, heat, radiation, light and radiant heat, electricity, magnetism, chemical force of association and dissociation, have now been proved to be special forms, modes of existence of one and the same energy, that is, motion. We can not only demonstrate its conversion from one form into another, which continually takes place in nature, but we can carry out this conversion in the laboratory and in industry, and indeed in such a way that a given quantity of energy in one form always corresponds to a given quantity of energy in some other form. Thus we can express the unit of heat in kilogram meters, and the units or any quantity of electrical or chemical energy once more in heat units and vice versa. We can likewise measure the energy consumption and energy intake of a living organism and express it in any desired unit, for example in heat units. The unity of all motion in nature is no longer a philosophical assertion, but a natural scientific fact. The second discovery, earlier in point of time, was the organic cell by Schwann and Schleiden, as being the unit out of which, by its multiplication and differentiation, all organisms, with the exception of the lowest, are formed and developed. This discovery, for the first time, gave a firm basis to the investigation of the organic, living products of nature, both comparative anatomy and physiology, and embryology. The origin, growth, and structure of organisms were deprived of their mysterious character. The hitherto incomprehensible miracle was merged in a process which takes place according to a law that is essentially identical for all multicellular organisms. But an essential gap still remained. If all multicellular organisms, both plants and animals including man, in each case grow out of a single cell according to the law of cell division, what then is the source of the infinite diversity of these organisms? This question was answered by the third great discovery, the theory of evolution, which for the first time was comprehensively worked out and substantiated by Darwin. However many transformations this theory will still undergo as regards details, in the main it has already solved the problem in a more than adequate manner. The evolutionary series of organisms, from a few simple forms to increasingly multifarious and complicated ones, as it confronts us today, and extending right up to man, has been established as far as its main features are concerned. Thanks to this, not only has it become possible to explain the existing stock of organic products of nature, but the basis has also been provided for the prehistory of the human mind, for tracing the various stages of its development, from the simple protoplasm, structureless but sensitive to stimuli, of the lowest organisms right up to the thinking human brain. Without this prehistory, however, the existence of the thinking human brain remains a miracle. By means of these three great discoveries, the main processes of nature were explained and referred to natural causes. One thing still remains to be done here, to explain the origin of life from inorganic nature. At the present stage of science, that implies nothing less than the preparation of protein bodies from inorganic substances. Chemistry is approaching closer and closer to the solution of this task, but it is still a long way from it. If, however, we bear in mind that it was only in 1828 that Wohler prepared the first organic body, urea, from inorganic materials, and what an innumerable number of so-called organic compounds are now artificially prepared without any organic materials, we shall not be inclined to bid chemistry halt when confronted by protein. So far, chemistry has been able to prepare every organic substance, the composition of which is accurately known. As soon as the composition of the protein bodies becomes known, chemistry will be able to set about the preparation of living protein. But to demand that it should achieve overnight what nature itself succeeds in doing only under very favorable circumstances, on a few cosmic bodies after millions of years, would be to demand a miracle. Thus the materialist outlook on nature rests today on much firmer foundation than it did in the previous century. At that time, only the motion of the heavenly bodies and that of terrestrial solid bodies, under the influence of gravity, was at all exhaustively understood. Almost the entire field of chemistry and the whole of organic nature remained mysterious and not understood. Today, the whole of nature lies spread out before us as a system of interconnections and processes that, at least in its main features, has been explained and understood. At all events, the materialist outlook on nature means nothing more than the simple conception of nature just as it is, without alien addition, and hence among the Greek philosophers it was originally understood in this way as a matter of course. But between those ancient Greeks and us lie more than 2,000 years of an essentially idealist outlook on the world, and so the return to self-evident understanding is more difficult than it appears to be at first sight. For it is by no means a matter of simply throwing overboard the entire thought content of those 2,000 years, but of a criticism of it, extracting the results that had been won within a form that was false and idealistic, but which was inevitable for its time and for the course of evolution itself, from this transitory form. And how difficult that is proved for us by those numerous natural scientists who are inexorably materialists within their science, but outside it are not merely idealists, but even pious and indeed orthodox Christians. All these epoch-making advances of natural science passed Feuerbach by without affecting him in any essential respect. This was not so much his fault as that of the miserable German conditions, owing to which the university chairs were occupied by empty-headed, eclectic hair-splitters, while Feuerbach, who towered high above them, was compelled almost to rusticate in lonely village isolation. That is why, on the subject of nature, he wastes so much labor, except for a few brilliant generalizations, on empty belletristic writing. Thus he says, quote, "Life is of course not the product of a chemical process, nor in general is it the product of an isolated natural force or phenomena, to which the metaphysical materialist reduces it. It is a result of the whole of nature." Unquote. Footnote. This quotation is given in Starke's book Ludwig Feuerbach, Stuttgart, 1885, on pages 154 to 55. It is taken from Feuerbach's work, The Question of Immortality from the Standpoint of Anthropology, which was written in 1846. See Ludwig Feuerbach's Sämtliche Werke, Volume 3, Leipzig, 1847, page 331. End of footnote. That life is a result of the whole of nature in no way contradicts the fact that protein, which is the exclusive independent bearer of life, arises under definite conditions, determined by the whole interconnection of nature, but arises precisely as the product of a chemical process. In square brackets is the following sentence, which Engels has struck out of the manuscript. Had Feuerbach lived in conditions which permitted him to follow even superficially the development of natural science, it would never have happened that he would speak of a chemical process as the effect of an isolated force of nature. Back to text. To the same solitariness must be ascribed the fact that Feuerbach loses himself in a circle of barren speculations on the relation of thought to the thinking organ, the brain, a sphere in which Starke follows him willingly. Enough, Feuerbach revolts against the name materialism, and not entirely without reason, for he never completely ceases to be an idealist. In the field of nature he is a materialist, but in the human field... Footnote. Engels has in mind Feuerbach's aphorisms, published posthumously in K. Grun, Ludwig Feuerbach, in his Correspondence and Legacy, as well as in his Philosophical Development. Volume 2, Leipzig and Heidelberg, 1874, page 308. The aphorisms are quoted on page 166 of Starke's book. See Friedrich Engels, Ludwig Feuerbach, and the End of Classical German Philosophy, Chapter 2. End of footnote. Editor's note. Page 19 of the original manuscript of L. Feuerbach ends here. The end of this sentence occurs on the following page, which has not come down to us. On the basis of the printed text of L. Feuerbach, it may be supposed that this sentence read approximately as follows, quote, "In the sphere of human history, he is an idealist," unquote. End of editor's note. God is nowhere treated worse than by the natural scientists who believe in him. Materialists simply explain the facts, without making use of such phrases. They do this first when importunate pious believers try to force God upon them, and then they answer curtly, either like Laplace, "Si, je ne vais pas," etc., or more rudely in the manner of the Dutch merchants, who, when German commercial travelers press their shoddy goods on them, are accustomed to turn them away with the words, "Ik kan die zaken niet gebruiken," I have no use for the things, and that is the end of the matter. But what God has had to suffer at the hands of his defenders. Footnote. Si je ne vais pas, besoin de cette hypothèse. The words of Laplace in answer to Napoleon's question why he had made no mention of God in his work on celestial mechanics. Translation, Sire, I had no need of that hypothesis. End of footnote. In the history of modern natural science, God is treated by his defenders as Frederick William III was treated by his generals and officials in the Jena campaign. One division of the army after another lays down its arms. One fortress after another capitulates before the march of science, until at last the whole infinite realm of nature is conquered by science, and there is no place left in it for the Creator. Newton still allowed him the quote-unquote first impulse, but forbade him any further interference in his solar system. Father Secchi bows him out of the solar system altogether, with all canonical honors it is true, but nonetheless categorically for all that, and he only allows him a creative act as regards the primordial nebula. And so in all spheres. In biology, his last great Don Quixote, Agassiz, even ascribes positive nonsense to him. He is supposed to have created not only the actual animals, but also abstract animals, the fish as such. And finally Tyndall totally forbids him any entry into nature, and relegates him to the world of emotional processes, only admitting him because, after all, there must be somebody who knows more about all these things, nature, than John Tyndall. Footnote. Engels is referring to Tyndall's opening speech at the 44th meeting of the British Association for the Advancement of Science in Belfast, August 19, 1874, published in Nature, number 251 of August 20, 1874. In a letter to Marx, dated September 21, 1874, Engels gives a more detailed characterization of this speech. End of footnote. What a distance from the old God, the creator of heaven and earth, the maintainer of all things, without whom not a hair can fall from the head. Tyndall's emotional need proves nothing. The Chevalier de Gris also had an emotional need to love and possess Marianne Le Chat, who sold herself and him over and over again. For her sake he became a card sharper and pimp, and if Tyndall wants to reproach him, he would reply with his quote-unquote emotional need. God equals nescio, but ignorantia non est argumentum. Spinoza. Footnote. Ignorance is no argument, says Spinoza in his Ethics, Part 1, Addendum, as he opposes the exponents of the clerical teleological view on nature, who gave the quote-unquote will of God as the cause of causes of all phenomena, and had no other argument left them but the assertion that they knew no other causes. End of footnote. Natural Science and Philosophy. Büchner. Footnote. The fragment headed Büchner was written before the other parts of Dialectics of Nature. It is the opening note of the first folder of the manuscript. The fragment is apparently a synopsis of a work planned by Engels against Büchner as an exponent of vulgar materialism and social Darwinism. Judging by the content of the fragment and by Engels' marginal notes in his copy of Büchner's book Der Mensch und seine Stellung in der Natur, Man and His Place in Nature, a second edition of which appeared late in 1872, Engels proposed to criticize primarily this work of Büchner's. The laconical comment we find in W. Liebknecht's letter to Engels, dated February 8, 1873, quote, "As for Büchner, go ahead," unquote, seems to suggest that Engels had just informed Liebknecht of his plan. It is therefore safe to assume that this fragment was written early in 1873. End of footnote. Rise of the tendency. The passing of German philosophy into materialism. Control over science abolished. Outbreak of shallow materialist popularization, in which the materialism had to make up for the lack of science. Its flourishing at the time of the deepest degradation of bourgeois Germany and official German science, 1850-60. Vogt, Mollschott, Büchner, mutual assurance. New impetus by the coming into fashion of Darwinism, which was immediately monopolized by these gentlemen. One could let them alone, and leave them to their not unpraiseworthy, if narrow occupation of teaching atheism, etc., to the German Philistine, but for 1. Abuse directed against philosophy, in parentheses, passages to be quoted, which, in spite of everything, is the glory of Germany, and 2. The presumption of applying the theories about nature to society, and of reforming socialism. Thus they compel us to take note of them. Footnote by Engels. Büchner is acquainted with philosophy only as a dogmatist, just as he himself is a dogmatist of the shallowest reflection of the German would-be Enlightenment, which missed the spirit and movement of the great French materialists. In parentheses, Hegel on this, just as Nicolai had that of Voltaire. Lessing's quote-unquote dead dog Spinoza. Hegel, Encyclopedia, Preface, page 19. End of footnote by Engels. Footnote. Engels is quoting the following passage from the preface to the second edition of Hegel's Encyclopedia of the Philosophical Sciences. Quote, "Lessing said in his time that people treat Spinoza like a dead dog." Unquote. Hegel had in mind a conversation between Lessing and Jacobi on June 7, 1780, during which Lessing had said, quote, "Why, people still talk of Spinoza as if he were a dead dog." Unquote. See F. H. Jacobi, Works, Volume 4, First Edition, Leipzig, 1819, page 68. Hegel deals in detail with the French materialists in Volume 3 of his History of Philosophy. End of footnote. First of all, what do they achieve in their own sphere? Quotations. 2. Turning point, pages 170 to 171. Whence this sudden Hegelianism? Transition to Dialectics. Footnote. The reference is to L. Büchner, Man and His Place in Nature in the Past, Present and Future, Leipzig, 1872. On pages 170 to 171 of this book, Büchner says that as mankind gradually develops, there arrives the moment when nature in man becomes aware of itself, and when man stops submitting passively to the blind laws of nature to become their master, that is, when quantity becomes quality, to use Hegel's phrase. In his copy of Büchner's book, Engels marked this passage with a stroke and commented, Umschlag, a reversal. End of footnote. Two philosophical tendencies, the metaphysical with fixed categories, the dialectical, Aristotle and especially Hegel, with fluid categories. The proofs that these fixed opposites, of basis and consequence, cause and effect, identity and difference, appearance and essence, are untenable, that analysis shows one pole already present in the other in nous, that at a definite point the one pole becomes transformed into the other, and that all logic develops only from these progressing contradictions. This mystical in Hegel himself, because the categories appear as pre-existing, and the dialectics of the real world as their mere reflection. In reality it is the reverse. The dialectics of the mind is only the reflection of the forms of motion of the real world, both of nature and of history. Until the end of the last century, indeed until 1830, natural scientists could manage pretty well with the old metaphysics, because real science did not go beyond mechanics, terrestrial and cosmic. Nevertheless, confusion had already been introduced by higher mathematics, which regards the eternal truth of lower mathematics as a superseded point of view, often asserting the contrary and putting forward propositions which appear sheer nonsense to the lower mathematician. The rigid categories disappeared here. Mathematics arrived at a field where even such simple relations as those of mere abstract quantity, bad infinity, assumed a completely dialectical form and compelled the mathematicians to become dialectical, unconsciously and against their will. There is nothing more comical than the twistings, subterfuges, and expedients employed by the mathematicians to solve this contradiction, to reconcile higher and lower mathematics, to make clear to their understanding that what they had arrived at as an undeniable result is not sheer nonsense, and in general rationally to explain the starting point, method and result of the mathematics of the infinite. Now, however, everything is quite different. Chemistry, the abstract divisibility of physical things, bad infinity, atomistics. Physiology, the cell, the organic process of development, both of the individual and of species, by differentiation, the most striking test of rational dialectics. And finally, the identity of the forces of nature and their mutual convertibility, which put an end to all fixity of categories. Nevertheless, the bulk of natural scientists are still held fast in the old metaphysical categories, and helpless when these modern facts, which, so to say, prove the dialectics in nature, have to be rationally explained and brought into relation with one another. And here, thinking is necessary. Atoms and molecules, etc., cannot be observed under the microscope, but only by the process of thought. Compare the chemists, except for Schorlemer, who is acquainted with Hegel, and Virchow's cellular pathology, where in the end the helplessness has to be concealed by general phrases. Dialectics, divested of mysticism, becomes an absolute necessity for natural science, which has forsaken the field where rigid categories sufficed, which represents, as it were, the lower mathematics of logic, its everyday weapons. Philosophy takes its revenge posthumously on natural science, for the latter having deserted it. And yet, the scientists could have seen from the successes in natural science achieved by philosophy that the latter possesses something that was superior to them even in their own special sphere. Leibniz, the founder of the mathematics of the infinite, in contrast to whom the inductive ass, Newton, appears as a plagiarist and corrupter, Kant, the theory of the origin of the universe before Laplace, Oken, the first in Germany to accept the theory of evolution, Hegel, whose ... Footnote. This word in Engels' manuscript is undecipherable. End of footnote. Comprehensive treatment and rational grouping of the natural sciences is a greater achievement than all the materialistic nonsense put together. Footnote on Newton. Engels has in mind the limitation of Newton's philosophical views, his one-sided overestimation of the method of induction, and his negative attitude to hypotheses, expressed by him in the well-known words, hypotheses non fingo. I do not invent hypotheses. End of footnote. Footnote on Newton's plagiarism. At the present time, it is considered to be beyond doubt that Newton arrived at the discovery of the differential and integral calculus independently of and earlier than Leibniz, but Leibniz, who made this discovery also independently, gave it a more perfect form. Already within 2 years of writing the present fragment, Engels expressed a more accurate view on this question. See this edition, page 258. End of footnote. On Buchner's claim to pronounce judgment on socialism and political economy on the basis of the struggle for existence, Hegel, Encyclopédie 1, page 9, on cobbling. Footnote. Engels has in mind the following passage from Hegel's Logic, In Encyclopedia of the Philosophical Sciences, Section 5, note, quote, "Everybody allows that to know any other science you must first have studied it, and that you can claim to express a judgment upon it in virtue of such knowledge. Everybody allows that to make a shoe you must have learnt and practiced the craft of the shoemaker. For philosophy alone, it seems to be imagined, such study, care, and application are not in the least requisite." Unquote. End of footnote. On Politics and Socialism, the understanding for which the world has waited, page 11. Footnote. Hegel, Encyclopedia of the Philosophical Sciences, Section 6, Observation. Quote, "This divorce between idea and reality is especially dear to the analytic understanding, which looks upon its own abstractions, dreams though they are, as something true and real. It prides itself on the imperative ought, which it takes especial pleasure in prescribing, even on the field of politics, as if the world had waited on it to learn how it ought to be and was not." Unquote. End of footnote. Separation, Coexistence, and Succession, Hegel, Encyclopedia, page 35, as determination of the sensuous, of the idea. Footnote. Ibid, Observation to Section 20. End of footnote. Hegel, Encyclopedia, page 40, Natural Phenomena, but in Buchner, not thought about, merely copied out, hence it is superfluous. Footnote. Ibid, Addendum to Section 21. End of footnote. Page 42, Solon's laws were, quote, "produced out of his head," unquote. Buchner is able to do the same for modern society. Page 45, Metaphysics, the science of things, not of movements. Page 53, quote, "In experience, everything depends upon the mind we bring to bear upon actuality. A great mind is great in its experience, and in the motley play of phenomena at once perceives the point of real significance." Unquote. Page 56, The parallelism between the human individual and history, the parallelism between embryology and paleontology. Footnote. The reference is to Hegel's argument on the transition from a naively unsophisticated state to a state of reflection, both in the history of society and in the development of the individual. Quote, "But the truth is that the awakening of consciousness follows from the very nature of man, and the same history repeats itself in every son of Adam." Unquote. Encyclopedia of the Philosophical Sciences, Section 24, Addendum 3. End of footnote. Just as Fourier is a mathematical poem, and yet still used, so Hegel a dialectical poem. Footnote. A quote-unquote mathematical poem is the term applied by W. Thomson to the book of the French mathematician Jean-Baptiste Joseph Fourier, Analytical Theory of Heat, Paris, 1822. See the appendix to the book of Thomson and Tate, A Treatise on Natural Philosophy, Volume 1, Oxford, 1867, page 713. In the synopsis of this book made by Engels, this passage is copied out and underlined. End of footnote. The incorrect theory of porosity, according to which the various false matters, caloric, etc., are situated in the pores of one another, and yet do not penetrate one another, is presented by Hegel as a pure figment of the mind. Encyclopedia, Volume 1, page 259. See also his Logic. Footnote. Hegel, Encyclopedia of the Philosophical Sciences, Section 130, Observation, Science of Logic, Book 2, Section 11, Chapter 1, Note on the Porosity of Matter. End of footnote. Hegel, Encyclopedia, Volume 1, pages 205 to 206. A prophetic passage on atomic weights, in contrast to the physical views of the time, and on atoms and molecules as thought determinations, on which thinking has to decide. Footnote. Hegel, Encyclopedia of the Philosophical Sciences, Section 103, Addendum. Here Hegel is polemizing with those physicists who explained the differences of the specific gravity of bodies by saying that, quote, a body with a specific gravity twice that of another contains within the same space twice as many material parts, atoms, as the other, unquote. End of footnote. If Hegel regards nature as a manifestation of the eternal quote-unquote idea in its alienation, and if this is such a serious crime, what are we to say of the morphologist Richard Owen? Quote, the archetypal idea was manifested in the flesh under diverse modifications upon this planet, long prior to the existence of those animal species that actually exemplify it, unquote. Nature of Limbs, 1849. Footnote. R. Owen, On the Nature of Limbs, London, 1849, page 86. End of footnote. If that is said by a mystical natural scientist who means nothing by it, it is calmly allowed to pass, but if a philosopher says the same thing, and one who means something by it, and indeed, au fond, something correct, although in inverted form, then it is mysticism and a terrible crime. Natural scientific thought. Agassiz' plan of creation, according to which God proceeded in creation from the general to the particular and individual, first creating the vertebrate as such, then the mammal as such, the animal of prey as such, the cat as such, and only finally the lion, etc. That is to say, first of all abstract ideas in the shape of concrete things, and then concrete things. See Haeckel, page 59. Footnote. E. Haeckel, Natural History of Creation, Berlin, 1873. End of footnote. In Oken, Haeckel, page 85, etc., the nonsense that has arisen from the dualism between natural science and philosophy is evident. By the path of thought, Oken discovers protoplasm and the cell, but it does not occur to anyone to follow up the matter along the lines of natural scientific investigation. It is to be accomplished by thinking. And when protoplasm and the cell were discovered, Oken was in general disrepute. Hoffmann, Ein Jahrhundert Chemie unter den Hohenzollern, cites the philosophy of nature. A quotation from Rosenkranz, the belletrist whom no real Hegelian recognizes. To make the philosophy of nature responsible for Rosenkranz is as foolish as Hoffmann making the Hohenzollerns responsible for Margraaf's discovery of beet sugar. Footnote. On page 26 of his book, Hoffmann gives the following quotation from Rosenkranz's book, System der Wissenschaft, ein philosophisches Einschädigung, Königsberg, 1850. Quote, Platinum is basically only a paradox of silver, wishing to occupy already the highest stage of metallicity. This belongs only to gold. Unquote. Section 475, page 301. Hoffmann speaks of the quote-unquote services of the Prussian king Frederick William III in organizing the sugar beet industry on pages 5 to 6 of his book. End of footnote. Theory and empiricism. The oblateness of the earth was theoretically established by Newton. The Cassinis and other Frenchmen maintained a long time afterwards, on the basis of their empirical measurements, that the earth is ellipsoidal and the polar axis the longest one. Footnote. In Engels' manuscript, the surname Cassini is given in the plural, die Cassinis. 4 astronomers named Cassini are known in the history of French science. 1. Giovanni Domenico Cassini, 1625 to 1712, first director of the Paris Observatory, who emigrated from Italy. 2. His son Jacques Cassini, 1677 to 1756. 3. The son of the last named, César François Cassini, 1714 to 1784. And 4. His son Jacques Dominique Cassini, 1748 to 1845. All 4 consecutively held the office of director of the Paris Observatory from 1669 to 1793. The first three upheld incorrect, anti-Newtonian notions of the shape of the Earth, and only the last was compelled, under the influence of more accurate measurements of its volume and shape, to admit that Newton was correct in inferring that the globe is compressed along the axis of its rotation. End of footnote. The contempt of the empiricists for the Greeks receives a peculiar illustration if one reads, for instance, T.H. Thomson on electricity, where people like Davy and even Faraday grope in the dark, in parentheses, the electric spark, etc., and make experiments that quite remind one of the stories of Aristotle and Pliny about physico-chemical phenomena. It is precisely in this new science that the empiricists entirely reproduce the blind groping of the ancients, and when Faraday, with his genius, gets on the right track, the Philistine Thomson has to protest against it. Page 397. Footnote. T.H. Thomson, An Outline of the Sciences of Heat and Electricity, 2nd edition, London, 1840. End of footnote. Haeckel, Anthropogeny, page 707. Quote, according to the materialist outlook on the world, matter or substance was present earlier than motion or vis viva, matter created force. Unquote. This is just as false as that force created matter, since force and matter are inseparable. Where does he get his materialism from? Footnote. E. Haeckel, Anthropogeny oder Entwicklungsgeschichte des Menschen, Leipzig, 1874, sections 707 to 8. End of footnote. Causae finales and efficientes transformed by Haeckel, pages 89-90, into purposively acting and mechanically acting causes, because for him, causa finalis equals God. Likewise for him, quote-unquote mechanical, adopted out of hand from Kant, equals monistic, not equals mechanical in the sense of mechanics. With such confusion of language, nonsense is inevitable. What Haeckel says here of Kant's Kritik der Urteilskraft does not agree with Hegel, Geschichte der Philosophie, Volume 3, page 603. Footnote. Haeckel, Natürliche Schöpfungsgeschichte, 4th edition, Berlin, 1873, pages 89 to 94, stresses the contradiction in Kant's critique of the teleological faculty of judgment, in parentheses, second part, between the, quote, mechanical methods of explanation, unquote, and teleology. Haeckel depicting the latter in opposition to Kant as the doctrine of external aims, of external expediency. Hegel, however, who examines this same critique of the teleological faculty of judgment in his History of Philosophy, Volume 3, Part 3, Chapter 4, Paragraph on Kant, Works, Volume 15, Berlin, 1836, page 603, put in the foreground Kant's conception of, quote-unquote, inner expediency, according to which in organic beings, quote, everything is purpose and reciprocally also means, unquote. Quotation from Kant given by Hegel. End of footnote. Another example of polarity in Haeckel, mechanism equals monism, and vitalism or teleology equals dualism. Already in Kant and Hegel, inner purpose is a protest against dualism. Mechanism applied to life is a helpless category. At the most we could speak of chemism, if we do not want to renounce all understanding of names. Purpose, Hegel, 5, page 205. Footnote. Hegel, Science of Logic, Book 3, Section 2, Chapter 3. In working on Dialectics of Nature, Engels used the edition G.W.F. Hegel, Works, Volume 5, 2nd edition, Berlin, 1841. End of footnote. Quote, thus mechanism manifests itself as a tendency of totality in that it seeks to seize nature for itself as a whole, which requires no other for its notion, a totality which is not found in end and the extra-mundane understanding which is associated therewith." Unquote. The point is, however, that mechanism, and also the materialism of the 18th century, does not get away from abstract necessity, and hence not from chance either. That matter evolves out of itself, the thinking human brain, is for mechanism a pure accident, although necessarily determined step by step where it happens. But the truth is that it is the nature of matter to advance to the evolution of thinking beings. Hence, this always necessarily occurs wherever the conditions for it, not necessarily identical at all places and times, are present. Further, Hegel 5, page 206, quote, "Consequently, in its connection of external necessity, this principle of mechanism affords the consciousness of infinite freedom as against teleology, which sets up as something absolute whatever it contains that is trivial or even contemptible, and here a more universal thought can only feel infinitely cramped or even nauseated." Unquote. Here again, the colossal waste of matter and motion in nature. In the solar system, there are perhaps 3 planets at most on which life and thinking beings could exist under present conditions, and the whole enormous apparatus for their sake. The inner purpose in the organism, according to Hegel 5, page 244, operates through impulse. Patois fort. Impulse is supposed to bring the single living being more or less into harmony with the idea of it. From this it is seen how much the whole inner purpose is itself an ideological determination, and yet Lamarck is contained in this. Natural scientists believe that they free themselves from philosophy by ignoring it or abusing it. They cannot, however, make any headway without thought, and for thought they need thought determinations, but they take these categories unreflectingly from the common consciousness of so-called educated persons, which is dominated by the relics of long obsolete philosophies, or from the little bit of philosophy compulsorily listened to at the university, which is not only fragmentary, but also a medley of views of people belonging to the most varied and usually the worst schools, or from uncritical and unsystematic reading of philosophical writings of all kinds. Hence, they are no less in bondage to philosophy, but unfortunately in most cases to the worst philosophy. And those who abuse philosophy, most are slaves to precisely the worst vulgarized relics of the worst philosophies. Natural scientists may adopt whatever attitude they please. They are still under the domination of philosophy. It is only a question whether they want to be dominated by a bad, fashionable philosophy, or by a form of theoretical thought, which rests on acquaintance with the history of thought and its achievements. Quote, "Physics, beware of metaphysics," unquote, is quite right, but in a different sense. Footnote, that is, taking metaphysics not in its old meaning, not as Newton did, for example, see note 15, who regarded it as philosophical thought in general, but in its modern meaning, that is, as the metaphysical method of thought. End of footnote. Natural scientists allow philosophy to prolong an illusory existence by making shift with the dregs of the old metaphysics. Only when natural and historical science has become imbued with dialectics will all the philosophical rubbish, other than the pure theory of thought, be superfluous, disappearing in positive science. Dialectics. A. General questions of dialectics. The fundamental laws of dialectics. Dialectics, so-called objective dialectics, prevails throughout nature, and so-called subjective dialectics, dialectical thought, is only the reflection of the motion through opposites, which asserts itself everywhere in nature, and which, by the continual conflict of the opposites and their final passage into one another, or into higher forms, determines the life of nature. Attraction and repulsion. Polarity begins with magnetism. It is exhibited in the one and the same body. In the case of electricity, it distributes itself over two or more bodies, which become oppositely charged. All chemical processes reduce themselves to processes of chemical attraction and repulsion. Finally, in organic life, the formation of the cell nucleus is likewise to be regarded as a polarization of the living protein material, and from the simple cell onwards, the theory of evolution demonstrates how each advance up to the most complicated plant on the one side and up to man on the other is affected by the continual conflict between heredity and adaptation. In this connection, it becomes evident how little applicable to such forms of evolution are categories like positive and negative. One can conceive of heredity as the positive, conservative side, adaptation as the negative side that continually destroys what has been inherited, but one can just as well take adaptation as the creative, active, positive activity, and heredity as the resisting, passive, negative activity. But just as in history, progress makes its appearance as the negation of the existing state of things, so here also, on purely practical grounds, adaptation is better conceived as negative activity. In history, motion through opposites is most markedly exhibited in all critical epochs of the foremost peoples. At such moments, a people has only the choice between two horns of a dilemma, either or, and indeed the question is always put in a way quite different from that in which the Philistines, who dabble in politics in every age, would have liked it put. Even the liberal German Philistine of 1848 found himself in 1849 suddenly, unexpectedly, and against his will confronted by the question, a return to the old reaction in an intensified form, or continuance of the revolution up to the republic, perhaps even the one and indivisible republic with a socialist background. He did not spend long in reflection, and helped to create the Manteuffel reaction as the flower of German liberalism. Similarly, in 1851, the French bourgeois, when faced with the dilemma which he certainly did not expect, a caricature of the empire, Praetorian rule, and the exploitation of France by a gang of scoundrels, or a social democratic republic, and he bowed down before the going of scoundrels so as to be able, under their protection, to go on exploiting the workers. Hard and fast lines are incompatible with the theory of evolution. Even the borderline between vertebrates and invertebrates is now no longer rigid. Just as little is that between fishes and amphibians, while that between birds and reptiles dwindles more and more every day. Between Compsognathus and Archaeopteryx, only a few intermediate links are wanting, and birds' beaks with teeth crop up in both hemispheres. Footnote: Compsognathus, an extinct animal of the order of dinosaurs, belonging to the class of reptiles, but according to the structure of the pelvis and hind extremities, closely related to the birds. H. A. Nicholson, A Manual of Zoology, 5th edition, Edinburgh and London, 1878, page 545. End of footnote. Either or becomes more and more inadequate. Among lower animals, the concept of the individual cannot be established at all sharply, not only as to whether a particular animal is an individual or a colony, but also where in development one individual ceases and the other begins. In parentheses, nurses. Footnote: Engels is referring to multiplication by budding or division among coelenterets. End of footnote. For a stage in the outlook on nature where all differences become merged in intermediate steps, and all opposites pass into one another through intermediate links, the old metaphysical method of thought no longer suffices. Dialectics, which likewise knows no hard and fast lines, no unconditional, universally valid either-or, and which bridges the fixed metaphysical differences, and besides either-or recognizes also in the right place both this and that, and reconciles the opposites, is the sole method of thought appropriate in the highest degree to this stage. Of course, for everyday use, for the small change of science, the metaphysical categories retain their validity. The transformation of quantity into quality equals quote-unquote mechanical world outlook. Quantitative change alters quality. The gentleman never suspected that. The character of mutual opposites belonging to the thought determinations of reason, polarization, just as electricity, magnetism, etc. become polarized and move in opposites, so do thoughts. Just as in the former, it is not possible to maintain any one-sidedness, and no natural scientist would think of doing so, so also in the latter. The true nature of the determinations of quote-unquote essence is expressed by Hegel himself. Encyclopedia 1, paragraph 3, addendum. Quote, "In essence, everything is relative," unquote. For example, positive and negative, which have meaning only in their relation, not each for itself. Part and whole, for instance, are already categories which become inadequate in organic nature. The ejection of seeds, the embryo, and the newborn animal are not to be conceived as a quote-unquote part that is separated from the quote-unquote whole. That would give a distorted treatment. It becomes a part only in a dead body. Encyclopedia 1, page 268. Footnote. Hegel, Encyclopedia of the Philosophical Sciences, section 135, addendum. Quote, "The limbs and organs, for instance, of an organic body are not merely parts of it. It is only in their unity that they are what they are, and they are unquestionably affected by that unity, as they also in turn affect it. These limbs and organs become mere parts only when they pass under the hands of the anatomist, whose occupation, be it remembered, is not with the living body but with the corpse." Unquote. End of footnote. Simple and compound, categories which even in organic nature likewise lose their meaning and become inapplicable. An animal is expressed neither by its mechanical composition from bones, blood, gristle, muscles, tissue, etc., nor by its chemical composition from the elements. Hegel, Encyclopedia 1, page 256. The organism is neither simple nor compound, however complex it may be. Footnote. Opus Citato, section 126, addendum. End of footnote. Abstract identity, A equals A, and negatively, A cannot be simultaneously equal and unequal to A, is likewise inapplicable in organic nature. The plant, the animal, every cell is at every moment of its life identical with itself, and yet becoming distinct from itself, by absorption and excretion of substances, by respiration, by cell formation and death of cells, by the process of circulation taking place, in short, by a sum of incessant molecular changes which make up life, and the sum total of whose results is evident to our eyes in the phases of life: embryonic life, youth, sexual maturity, process of reproduction, old age, death. The further physiology develops, the more important for it became these incessant, infinitely small changes, and hence the more important for it also the consideration of difference within identity, and the old abstract standpoint of formal identity, that an organic being is to be treated as something simply identical with itself, as something constant, becomes out of date. Note in the margin, quote, "apart, moreover, from the evolution of species," unquote. End of note in the margin. Nevertheless, the mode of thought based thereon, together with its categories, persists. But even in inorganic nature, identity as such is in reality non-existent. Every body is continually exposed to mechanical, physical, and chemical influences, which are always changing it and modifying its identity. Abstract identity, with its opposition to difference, is in place only in mathematics, an abstract science which is concerned with creations of thought, even though they are reflections of reality, and even there it is continually being sublated. Hegel, Encyclopedia 1, page 235. Footnote. Opus Citato, section 117, addendum. End of footnote. The fact that identity contains difference within itself is expressed in every sentence, where the predicate is necessarily different from the subject. The lily is a plant, the rose is red, where either in the subject or in the predicate there is something that is not covered by the predicate or the subject. Hegel, page 231. Footnote. Opus Citato, section 115. Note. Here Hegel says that the very form of judgment speaks of the distinction between the subject and the predicate. End of footnote. That from the outset identity with itself requires difference from everything else as its complement is self-evident. Continual change, that is, sublation of abstract identity with itself, is also found in so-called inorganic nature. Geology is its history. On the surface, mechanical changes, denudation, frost, chemical changes, weathering, internally mechanical changes, pressure, heat, volcanic, chemical, water, acids, binding substances, on a large scale, upheavals, earthquakes, etc. The slate of today is fundamentally different from the ooze from which it is formed, the chalk from the loose microscopic shells that compose it. Even more so limestone, which indeed, according to some, is of purely organic origin, and sandstone from the loose sea sand, which again is derived from disintegrated granite, etc., not to speak of coal. The law of identity, in the old metaphysical sense, is the fundamental law of the old outlook, A equals A. Each thing is equal to itself. Everything was permanent, the solar system, stars, organisms. This law has been refuted by natural science bit by bit in each separate case, but theoretically it still prevails, and is still put forward by the supporters of the old in opposition to the new. A thing cannot simultaneously be itself and something else, and yet the fact that true, concrete identity includes difference, change, has recently been shown in detail by natural science. See above. Abstract identity, like all metaphysical categories, suffices for everyday use, where small dimensions or brief periods of time are in question. The limits within which it is usable differ in almost every case, and are determined by the nature of the object. For a planetary system, where in ordinary astronomical calculation the ellipse can be taken as the basic form for practical purposes without error, they are much wider than for an insect that completes its metamorphosis in a few weeks. Give other examples, for example alteration of species, which is reckoned in periods of thousands of years. For natural science, in its comprehensive role, however, even in each single branch, abstract identity is totally inadequate, and although on the whole it has now been abolished in practice, theoretically it still dominates people's minds, and most natural scientists imagine that identity and difference are irreconcilable opposites instead of one-sided poles, which represent the truth only in their reciprocal action, in the inclusion of difference within identity. Identity and difference, necessity and chance, cause and effect, the two main opposites, which treated separately become transformed into one another, and then, quote-unquote, first principles must help. Positive and negative can also be given the reverse names in electricity, etc. North and south, ditto. If one reverses this and alters the rest of the terminology accordingly, everything remains correct. We can call west east and east west, the sun rises in the west, and planets revolve from east to west, etc. The names alone are changed. Indeed, in physics, we call the real south pole of the magnet, which is attracted by the north pole of the Earth's magnetism, the north pole, and it does not matter. That positive and negative are equivalent, irrespective of which side is positive and which negative, holds good not only in analytical geometry, but still more in physics. See Clausius, page 87 etc. Footnote. This refers in all probability to the book by Clausius, Die mechanische Wärmetheorie, second revised German edition, Volume 1, Braunschweig, 1876. Pages 87 to 88 of this book speak of the, quote, positive and negative quantities of heat, unquote. End of footnote. Polarity. A magnet, on being cut through, polarizes the neutral middle portion, but in such a way that the old poles remain. On the other hand, a worm, on being cut into two, retains the receptive mouth at the positive pole and forms a new negative pole at the other end with excretatory anus, but the old negative pole, the anus, now becomes positive, becoming a mouth, and a new anus or negative pole is formed at the cut end. Voila, transformation of positive into negative. Polarization. For J. Grimm, it was still a firmly established law that a German dialect must be either High German or Low German. In this he totally lost sight of the Frankish dialect. Footnote. Engels has in mind J. Grimm's Geschichte der deutschen Sprache, a history of the German language, 4th German edition, Leipzig, 1880, first published in Leipzig in 1848. He speaks of the Frankish dialect in greater detail in his work, The Frankish Dialect, written in 1881 to 82. Engels must have written his comment in 1881. End of footnote. Because the written Frankish of the later Carlovingian period was High German, since the High German shifting of consonants had taken possession of the Frankish southeast, he imagined that Frankish passed in one place into Old High German, in another place into French. It then remained absolutely impossible to explain the source of the Netherland dialect in the ancient Salic regions. Frankish was only rediscovered after Grimm's death, Salic in its rejuvenation as the Netherland dialect, Ripuaric in the Middle and Lower Rhine dialects, which in part have been shifted to various stages of High German, and in part have remained Low German, so that Frankish is a dialect that is both High German and Low German. Chance and necessity. Another opposition in which metaphysics is entangled is that of chance and necessity. What can be more sharply contradictory than these two thought determinations? How is it possible that both are identical, that the accidental is necessary and the necessary is also accidental? Common sense, and with it the majority of natural scientists, treats necessity and chance as determinations that exclude each other once and for all. A thing, a circumstance, a process, is either accidental or necessary, but not both. Hence, both exist side by side in nature. Nature contains all sorts of objects and processes, of which some are accidental, the others necessary, and it is only a matter of not confusing the two sorts with each other. Thus, for instance, one assumes the decisive specific characters to be necessary, other differences between individuals of the same species being termed accidental, and this holds good of crystals as it does for plants and animals. Then again, the lower group becomes accidental in relation to the higher, so that it is declared to be a matter of chance how many different species are included in the genus, Felis or Equus, or how many genera and orders there are in a class, and how many individuals of each of these species exist, or how many different species of animals occur in a given region, or what in general the fauna and flora are like. And then it is declared that the necessary is the sole thing of scientific interest, and that the accidental is a matter of indifference to science. That is to say, what can be brought under laws, hence what one knows, is interesting. What cannot be brought under laws, and therefore what one does not know, is a matter of indifference and can be ignored. Thereby all science comes to an end, for it has to investigate precisely that which we do not know. That is to say, what can be brought under general laws is regarded as necessary, and what cannot be so brought as accidental. Anyone can see that this is the same sort of science as that which proclaims natural what it can explain, and ascribes what it cannot explain to supernatural causes. Whether I term the cause of the inexplicable chance, or whether I term it God, is a matter of complete indifference as far as the thing itself is concerned. Both are only equivalents for I do not know, and therefore do not belong to science. The latter ceases where the requisite connection is wanting. In opposition to this view, there is determinism, which passed from French materialism into natural science, and which tries to dispose of chance by denying it altogether. According to this conception, only simple, direct necessity prevails in nature. That a particular pea pod contains 5 peas and not 4 or 6, that a particular dog's tail is 5 inches long and not a whit longer or shorter, that this year a particular clover flower was fertilized by a bee and another not, and indeed by precisely one particular bee, and at a particular time, that a particular wind-blown dandelion seed has sprouted and another not, that last night I was bitten by a flea at 4 o'clock in the morning, and not at 3 or 5 o'clock, and on the right shoulder and not on the left calf. These are all facts which have been produced by an irrevocable concatenation of cause and effect, by an unshatterable necessity of such a nature, indeed, that the gaseous sphere from which the solar system was derived was already so constituted that these events had to happen thus and not otherwise. With this kind of necessity, we likewise do not get away from the theological conception of nature. Whether with Augustine and Calvin we call it the eternal decree of God, or kismet as the Turks do, or whether we call it necessity, is all pretty much the same for science. Footnote: Kismet, in Muslim, chiefly Turkish usage, means destiny or fate. End of footnote. There is no question of tracing the chain of causation in any of these cases, so we are just as wise in one as in another. The so-called necessity remains an empty phrase, and with it, chance also remains what it was before. As long as we are not able to show on what the number of peas in the pod depends, it remains just a matter of chance, and the assertion that the cause was foreseen already in the primordial constitution of the solar system does not get us a step further. Still more, a science which was to set about the task of following back the causes of this individual pea pod in its causal concatenation would be no longer science, but pure trifling. For this same pea pod alone, in addition, innumerable other individual, accidentally appearing qualities, shade of color, thickness and hardness of the pod, size of the peas, not to speak of the individual peculiarities revealed by the microscope. The one pea pod, therefore, would already provide more causal connections for following up than all the botanists in the world could solve. Hence, chance is not here explained by necessity, but rather necessity is degraded to the production of what is merely accidental. If the fact that a particular pea pod contains 6 peas and not 5 or 7 is of the same order as the law of motion of the solar system or the law of the transformation of energy, then as a matter of fact, chance is not elevated into necessity, but rather necessity degraded into chance. Furthermore, however much the diversity of the organic and inorganic species and individuals existing side by side in a given area may be asserted to be based on irrefragable necessity, for the separate species and individuals it remains what it was before, a matter of chance. For the individual animal it is a matter of chance where it happens to be born, what environment it finds for living, what enemies and how many of them threaten it. For the mother plant it is a matter of chance whither the wind scatters its seeds, and for the daughter plant where the seed finds soil for germination. And to assure us that here also everything rests on irrefragable necessity is a poor consolation. The jumbling together of natural objects in a given region, still more in the whole world, for all the primordial determination from eternity, remains what it was before, a matter of chance. In contrast to both conceptions, Hegel came forward with the hitherto quite unheard of propositions that the accidental has a cause because it is accidental, and just as much also has no cause because it is accidental, that the accidental is necessary, that necessity determines itself as chance, and on the other hand, this chance is rather absolute necessity. Logic 2, Book 3, 2, Reality. Natural science has simply ignored these propositions as paradoxical trifling, as self-contradictory nonsense, and as regards theory, has persisted on the one hand in the barrenness of thought of Wolffian metaphysics, according to which a thing is either accidental or necessary, but not both at once, or on the other hand, in the hardly less thoughtless mechanical determinism, which in words denies chance in general, only to recognize it in practice in each particular case. While natural science continued to think in this way, what did it do in the person of Darwin? Darwin, in his epoch-making work, set out from the widest existing basis of chance. Footnote. This refers to Darwin's The Origin of Species by Means of Natural Selection, 1859. End of footnote. Precisely the infinite, accidental differences between individuals within a single species, differences which become accentuated until they break through the character of the species, and whose immediate causes even can be demonstrated only in extremely few cases, compelled him to question the previous basis of all regularity in biology, viz., the concept of species in its previous metaphysical rigidity and unchangeability. Without the concept of species, however, all science was nothing. All its branches needed the concept of species as basis. Human anatomy and comparative anatomy, embryology, zoology, paleontology, botany, etc. What were they without the concept of species? All their results were not only put in question, but directly set aside. Chance overthrows necessity, as conceived hitherto. Note in the margin of the manuscript, quote, "The material on chance occurrences accumulated in the meantime has suppressed and shattered the old idea of necessity." Unquote. End of the note in the margin. The previous idea of necessity breaks down. To retain it means dictatorially to impose on nature as a law a human arbitrary determination that is in contradiction to itself and to reality. It means to deny thereby all inner necessity in living nature. It means generally to proclaim the chaotic kingdom of chance to be the sole law of living nature. Quote, "Gilt nichts mehr der Tausves Jontov," unquote, cried out quite logically the biologists of all schools. Darwin. Footnote. A quotation from Heine's satirical poem Disputation, Roman 0, Volume 3, 1851, which depicts a medieval dispute between a Catholic Capuchin monk and a learned Jewish rabbi, who in the course of the dispute appeals to the Jewish religious book Tausves Jontov. The Capuchin's reply is to send the Tausves Jontov to the devil. Thereupon the indignant rabbi cries out in a frenzy, quote, "Gilt nichts mehr des Tausves Jontov, was soll gelten, zeter, zeter," unquote. In parentheses, if the Tausves Jontov has no longer authority, then what shall prevail? Help, help. End of footnote. Hegel, Logic, Volume 1. Footnote. G.W.F. Hegel, Works, Volume 3, 2nd German edition, Berlin, 1841. End of footnote. Quote, "Nothing that is opposed to something, the nothing of any something, is a determinate nothing." Unquote. Page 74. Quote, "In view of the mutually determinate connection of the world whole, metaphysics could make the assertion, which is really a tautology, that if the least grain of dust were destroyed, the whole universe must collapse." Unquote. Page 78. Negation, main passage, quote-unquote introduction, page 38, quote, "that the self-contradictory resolves itself not into nullity, into abstract nothingness, but essentially only into the negation of its particular content," unquote, etc. Negation of the negation, Phenomenology, preface, page 4, bud, flower, fruit, etc. Footnote. This reference is to the following passage from Hegel's preface to Phenomenology des Geistes, Phenomenology of Mind. Quote, "The bud disappears when the blossom breaks through, and we might say that the former is refuted by the latter. In the same way, when the fruit comes, the blossom may be explained to be a false form of the plant's existence, for the fruit appears as its true nature in place of the blossom." Unquote. Engels is quoting from G.W.F. Hegel, Works, Volume 2, Second German edition, Berlin, 1841. End of footnote. B. Dialectical logic and the theory of knowledge. On the quote-unquote limits of knowledge. Unity of nature and mind. To the Greeks, it was self-evident that nature could not be unreasonable, but even today, the stupidest empiricists prove by their reasoning, however wrong it may be, that they are convinced from the outset that nature cannot be unreasonable or reason contrary to nature. The evolution of a concept, or of a conceptual relation, positive and negative, cause and effect, substance and accidency, in the history of thought, is related to its development in the mind of the individual dialectician, just as the evolution of an organism in paleontology is related to its development in embryology, or rather in history and in the single embryo. That this is so was first discovered by concept by Hegel. In historical development, chance plays its part, which in dialectical thinking, as in the development of the embryo, is summed up in necessity. Abstract and concrete. The general law of the change of form of motion is much more concrete than any single so-called concrete example of it. Understanding and reason. This Hegelian distinction, according to which only dialectical thinking is reasonable, has a definite meaning. We have in common with animals all activity of the understanding, induction, deduction, and hence also abstraction. In parentheses, Diderot's generic concepts, quadrupeds and bipeds. Analysis of unknown objects. Even the cracking of a nut is a beginning of analysis. Synthesis, in animal tricks, and as the union of both, experiment, in the case of new obstacles and unfamiliar situations. Footnote. Dido, the name of Engels' dog, which he mentioned in his letter to Marx, dated April 16, 1865, and August 10, 1866. End of footnote. In their nature, all these modes of procedure, hence all means of scientific investigation that ordinary logic recognizes, are absolutely the same in men and higher animals. They differ only in degree of development of the method in each case. The basic features of the method are the same and lead to the same results in man and animals, so long as both operate or make shift merely with these elementary methods. On the other hand, dialectical thought, precisely because it presupposes investigations of the nature of concepts themselves, is only possible for man, and for him only at a comparatively high stage of development, in parentheses, Buddhists and Greeks, and it attains its full development much later still through modern philosophy. And yet we have the colossal results already among the Greeks, which by far anticipate investigation. On the classification of judgments. Dialectical logic, in contrast to the old, merely formal logic, is not, like the latter, content with enumerating the forms of motion of thought, that is, the various forms of judgment and conclusion, and placing them side by side without any connection. On the contrary, it derives these forms out of one another. It makes one subordinate to another instead of putting them on an equal level. It develops the higher forms out of the lower. Faithful to his division of the whole of logic, Hegel groups judgments as. Footnote. Hegel explains the correspondence between the division of logic into three parts, the doctrine of being, doctrine of essence, and doctrine of notion, and the four-member classification of judgments as follows. Quote, the different species of judgment derive their features from the universal forms of the logical idea itself. If we follow this clue, it will supply us with three chief kinds of judgment, parallel to the stages of being, essence, and notion. The second of these kinds, as required by the character of essence, which is the stage of differentiation, must be doubled. Unquote. Hegel, Encyclopedia of the Philosophical Sciences, section 171, addendum. End of footnote. 1. Judgment of inheritance, the simplest form of judgment, in which a general property is affirmatively or negatively predicated of a single thing. Positive judgment, the rose is red. Negative judgment, the rose is not blue. Infinite judgment, the rose is not a camel. 2. Judgment of subsumption, in which a relation determination is predicated of the subject. Singular judgment, this man is mortal. Particular judgment, many men are mortal. Universal judgment, all men are mortal, or man is mortal. Footnote. Here the definitions singular, particular, and universal stand for individual, particular, and universal in the sense of formal logic, as distinct from the dialectical categories of Einzelnes, Besonderes, and Allgemeines, single, special, and general. End of footnote. 3. Judgment of necessity, in which its substantial determination is predicated of the subject. Categorical judgment, the rose is a plant. Hypothetical judgment, when the sun rises it is daytime. Disjunctive judgment, Lepidosiren is either a fish or an amphibian. 4. Judgment of the notion, in which is predicated of the subject how far it corresponds to its general nature, or, as Hegel says, to the notion of it. Assertoric judgment, this house is bad. Problematic judgment, if a house is constituted in such and such a way, it is good. Apodeictic judgment, the house that is constituted in such and such a way is good. 1. Individual judgment. 2 and 3. Special. 4. General. However dry this sounds here, and however arbitrary at first sight this classification of judgments may here and there appear, yet the inner truth and necessity of this grouping will become clear to anyone who studies the brilliant exposition in Hegel's Larger Logic, Works 5, pages 63 to 115. Footnote. Engels gives the pages of the whole chapter on judgment in the third book of Hegel's Science of Logic. End of footnote. To show how much this grouping is based not only on the laws of thought, but also on the laws of nature, we should like to put forward here a very well-known example outside this connection. That friction produces heat was already known practically to prehistoric man, who discovered the making of fire by friction, perhaps more than 100,000 years ago, and who still earlier warmed cold parts of the body by rubbing. But from that to the discovery that friction in general is a source of heat, who knows how many thousands of years elapsed. Enough that the time came when the human brain was sufficiently developed to be able to formulate the judgment, friction is a source of heat, a judgment of inheritance, and indeed a positive one. Still further thousands of years passed until, in 1842, Meyer, Joule, and Kolding investigated this special process in its relation to other processes of a similar kind that had been discovered in the meantime, that is, as regards its immediate general conditions, and formulated the judgment, all mechanical motion is capable of being converted into heat by means of friction. So much time and an enormous amount of empirical knowledge were required before we could make the advance in knowledge of the object from the above positive judgment of inheritance to this universal judgment of subsumption. But from now on things went quickly. Only 3 years later, Meyer was able, at least in substance, to raise the judgment of subsumption to the level at which it now stands. Any form of motion, under conditions fixed for each case, is both able and compelled to undergo transformation, indirectly into any form of motion, a judgment of the notion and moreover an apodeictic one, the highest form of judgment altogether. What, therefore, in Hegel appears as a development of the thought form of judgment as such, confronts us here as the development of our empirically based theoretical knowledge of the nature of motion in general. This shows, however, that laws of thought and laws of nature are necessarily in agreement with one another, if only they are correctly known. We can regard the first judgment as that of individuality. The isolated fact that friction produces heat is registered. The second judgment is that of particularity. A special form of motion, mechanical motion, exhibits the property, under special conditions, through friction, of passing into another special form of motion, viz. Heat. The third judgment is that of universality. Any form of motion proves able and compelled to undergo transformation into any other form of motion. In this form, the law attains its final expression. By new discoveries, we can give new illustrations of it. We can give it a new and richer content. But we cannot add anything to the law itself, as here formulated. In its universality, equally universal in form and content, it is not susceptible of further extension. It is an absolute law of nature. Unfortunately, we are in a difficulty about the form of motion of protein, alias life, so long as we are not able to make protein. Above, however, it has also been proved that to make judgments involves not merely Kant's so-called power of judgment, but a ... Footnote. This unfinished note closes the fourth page of the double sheet, of which the second and third pages and the beginning of the fourth page constitute the preceding large fragment on the classification of judgments. Engels apparently meant to finish the note by counterposing his thesis on the empirical basis of all knowledge to the Kantian a priorism. End of footnote. Individuality, particularity, universality, these are the three determinations in which the whole, quote-unquote, doctrine of notion moves. Footnote. That is, the whole of the third part of Hegel's Science of Logic. End of footnote. Under these heads, progression from the individual to the particular, and from the particular to the universal, takes place not only in one but in many modalities, and this is often enough exemplified by Hegel as the progression individual, species, genus. And now the Haeckel's come forward with their introduction and trumpet it as a great fact against Hegel that progression must be from the individual to the particular and then to the universal, from the individual to the species and then to the genus, and then permit deductive conclusions which are supposed to lead further. These people have got into such a deadlock over the opposition between induction and deduction that they reduce all logical forms of conclusion to these two, and in so doing, do not notice that they 1. Unconsciously employ quite different forms of conclusion under those names, 2. Deprive themselves of the whole wealth of forms of conclusion, insofar as it cannot be forced under these two, and 3. Thereby convert both forms, induction and deduction, into sheer nonsense. Induction and deduction. Haeckel, page 75 et seq., where Goethe draws the inductive conclusion that man, who does not normally have a premaxillary bone, must have one, hence by incorrect induction arrives at something correct. Footnote. On pages 75 to 77 of the fourth edition of his Natural History of Creation, Berlin 1873, Haeckel relates how Goethe discovered the existence of the intermaxillary bone in man. In Haeckel's opinion, Goethe arrived first of all at the inductive proposition, quote, all mammals have an intermaxillary bone, unquote, from which he drew the deductive conclusion, quote, therefore man also has such a bone, unquote, following which this conclusion was confirmed by experimental data, by the discovery of the intermaxillary bone in the human embryo and in occasional atavistic cases in adults. Engels says that the induction of which Haeckel speaks is incorrect because it was contradicted by the proposition, considered correct, that the mammal, man, has no intermaxillary bone. End of footnote. Haeckel's nonsense. Induction against deduction, as if it were not the case that deduction equals conclusion, and therefore induction is also a deduction. This comes from polarization. Haeckel's Schöpfungsgeschichte, pages 76 to 77. The conclusion polarized into induction and deduction. By induction, it was discovered 100 years ago that crayfish and spiders were insects and all lower animals were worms. By induction, it has now been found that this is nonsense and there exist X classes. Wherein, then, lies the advantage of the so-called inductive conclusion, which can be just as false as the so-called deductive conclusion, the basis of which is nevertheless classification. Induction can never prove that there will never be a mammal without lacteal glands. Formerly, nipples were the mark of a mammal, but the platypus has none. The whole swindle of induction is derived from the Englishmen. Whewell, inductive sciences, comprising the purely mathematical sciences, and so the antithesis to deduction invented. Footnote: Engels is obviously referring to the main works of Whewell, History of the Inductive Sciences, 3 volumes, London 1837, and Philosophy of the Inductive Sciences, 2 volumes, London 1840. The manuscript has, quote, Die bloß mathematischen umfassend, unquote. The word umfassend is used here obviously in the sense of compromising the purely mathematical sciences, which according to Whewell are sciences of pure reason that investigate the so-called conditions of all theory, and in this sense occupy, as it were, a central position in the quote-unquote geography of the intellectual world. In Philosophy of the Inductive Sciences, Volume 1, Book 2, Whewell gives a brief outline of the quote-unquote philosophy of the pure sciences, regarding geometry, theoretical arithmetic, and algebra as its main components. In his History of the Inductive Sciences, Whewell counterposes the so-called inductive sciences, mechanics, astronomy, physics, chemistry, mineralogy, botany, zoology, physiology, geology, to the so-called deductive sciences, geometry, arithmetic, algebra. End of footnote. Logic, old or new, knows nothing of this. All forms of conclusion that start from the individual are experimental and based on experience. Indeed, the inductive conclusion even starts from U-I-P, universal. Footnote: in the formula U-I-P, U denotes the universal, I the individual, and P the particular. This formula is used by Hegel in analyzing the logical essence of inductive conclusions. See Hegel, Science of Logic, Book 3, Section 1, Chapter 3, Paragraph, The Syllogism of Induction. Hegel's proposition, mentioned by Hegel further down, that inductive conclusion is in effect problematic, occurs in the same place. End of footnote. It is also characteristic of the thinking capacity of our natural scientists that Haeckel fanatically champions induction at the very moment when the results of induction, the classifications, are everywhere put in question. Limulus, a spider, Ascidia, a vertebrate or chordate, the dipnoi, however, being fishes, in opposition to all original definitions of amphibia, and daily new facts are being discovered which overthrow the entire previous classification by induction. Footnote: H. A. Nicholson, A Manual of Zoology, 5th edition, Edinburgh and London, 1878, pages 283 to 85, 363 to 70, 481 to 84. End of footnote. What a beautiful confirmation of Hegel's thesis that the inductive conclusion is essentially a problematic one. Indeed, owing to the theory of evolution, even the whole classification of organisms has been taken away from induction and brought back to so-called deduction, to descent, one species being literally deduced from another by descent, and it is impossible to prove the theory of evolution by induction alone, since it is quite anti-inductive. The concepts with which induction operates, species, genus, class, have been rendered fluid by the theory of evolution, and so have become relative, but one cannot use relative concepts for induction. To the pan-inductionists, footnote, in the manuscript, den all-Induktionisten, that is, to those who regard induction as the only correct method. End of footnote. With all the induction in the world, we would never have gotten to the point of becoming clear about the process of induction. Only the analysis of this process could accomplish this. Induction and deduction belong together as necessarily as synthesis and analysis. Note in the margin, quote, chemistry, in which analysis is the predominant form of investigation, is nothing without its opposite, synthesis, unquote. End of note in the margin. Instead of one-sidedly loading one to the skies at the expense of the other, we should seek to apply each of them in its place, and that can only be done by bearing in mind that they belong together, that they supplement each other. According to the inductionists, induction is an infallible method. It is so little so that its apparently surest results are every day overthrown by new discoveries. Light corpuscles and caloric were results of induction. Where are they now? Induction taught us that all vertebrates have a central nervous system, differentiated into brain and spinal cord, and that the spinal cord is enclosed in cartilaginous or bony vertebrae, whence indeed the name is derived. Then Amphioxus was revealed as a vertebrate with an undifferentiated central nervous strand and without vertebrae. Induction established that fishes are those vertebrates which throughout life breathe exclusively by means of gills. Then animals come to light whose fish character is almost universally recognized, but which, besides gills, have also well-developed lungs, and it turns out that every fish carries a potential lung in the swim bladder. Only by audacious application of the theory of evolution did Haeckel rescue the inductionists, who were feeling quite comfortable in these contradictions. If induction were really so infallible, whence come the rapid successive revolutions in classifications of the organic world? They are the most characteristic product of induction, and yet they annihilate one another. Induction and analysis. A striking example of how little induction can claim to be the sole or even the predominant form of scientific discovery occurs in thermodynamics. The steam engine provided the most striking proof that one can impart heat and obtain mechanical motion. 100,000 steam engines did not prove this more than one, but only more and more forced the physicists into the necessity of explaining it. Sadi Carnot was the first seriously to set about the task, but not by induction. He studied the steam engine, analyzed it, and found that in it the process which mattered does not appear in pure form, but is concealed by all sorts of subsidiary processes. He did away with these subsidiary circumstances that did not have a bearing on the essential process, and an ideal steam engine, or gas engine, which, it is true, is as little capable of being realized as, for instance, a geometrical line or surface, but in its way performs the same service as these mathematical abstractions. It presents the process in a pure, independent, and unadulterated form, and he came right up against the mechanical equivalent of heat. See the significance of his function C, which he only failed to discover and see because he believed in caloric. Here also proof of the damage done by false theories. The empiricism of observation alone can never adequately prove necessity. Post hoc, but not propter hoc. Encyclopédie 1, page 84. Footnote, Hegel, Encyclopedia of the Philosophical Sciences, section 39. Quote, mere experience affords perception of changes succeeding each other, but it presents no necessary connection. End of footnote. This is so very correct that it does not follow from the continual rising of the sun in the morning that it will rise again tomorrow, and in fact we know now that a time will come when one morning the sun will not rise. But the proof of necessity lies in human activity, in experiment, in work. If I am able to make the pose hoc, it becomes identical with the propter hoc. Causality. The first thing that strikes us in considering matter in motion is the interconnection of the individual motions of separate bodies, their being determined by one another. But not only do we find that a particular motion is followed by another, we find also that we can evoke a particular motion by setting up the conditions in which it takes place in nature, that we can even produce motions which do not occur at all in nature, in parentheses industry, at least not in this way, and that we can give these motions a predetermined direction and extent. In this way, by the activity of human beings, the idea of causality becomes established, the idea that one motion is the cause of another. True, the regular sequence of certain natural phenomena can by itself give rise to the idea of causality, the heat and light that come with the sun, but this affords no proof, and to that extent Hume's skepticism was correct in saying that a regular pos hoc can never establish a propter hoc. But the activity of human beings forms the test of, and make them by, proof that heat comes from the sun. If we bring together in a rifle the priming, the explosive charge, and the bullet, and then fire it, we count upon the effect known in advance from previous experience, because we can follow in all its details the whole process of ignition, combustion, explosion by the sudden conversion into gas and pressure of the gas on the bullet. And here the skeptic cannot even say that because of previous experience it does not follow that it will be the same next time, for as a matter of fact, it does sometimes happen that it is not the same, that the priming or the gunpowder fails to work, that the barrel bursts, etc. But surely this which proves causality instead of refuting it, because we can find out the cause of each such derivation from the rule by appropriate investigation. Chemical decomposition of the priming, dampness, etc. of the gunpowder, defect in the barrel, etc., etc., so that here the test of causality is, so to say, a double one. Natural science, like philosophy, has hitherto entirely neglected the influence of activity on their thought. Both know only nature on the one hand and thought on the other, but it is precisely the alteration of nature by men, not solely nature as such, which is most essential and immediate basis of human thought, and it is in the measure that man has learned to change nature that his intelligence has increased. The naturalistic conception of history, as found, for instance, to a greater or lesser extent in Draper and other scientists, as if nature exclusively reacts on man, and natural conditions everywhere exclusively determined his historical development, is therefore one-sided and forgets that man also reacts on nature, changing it and creating new conditions of existence for himself. There is devilishly little left of quote-unquote nature as it was in Germany at the time when the Germanic peoples immigrated into it. The Earth's surface, climate, vegetation, fauna, and the human beings themselves have infinitely changed, and all this owing to human activity, while the changes of nature in Germany, which have occurred in this period of time without human interference, are incalculably small. Reciprocal action is the first thing that we encounter when we consider matter in motion as a whole from the standpoint of modern natural science. We see a series of forms of motion: mechanical motion, heat, light, electricity, magnetism, chemical union and decomposition, transition of states of aggregation, organic life, all of which, if at present we still make an exception of organic life, pass into one another, mutually determine one another, are in one place cause and in another effect, the sum total of the motion in all its changing forms remaining the same. Spinoza, substance is causa sui, strikingly expresses the reciprocal action. Footnote. Spinoza, Ethics, Part 1, Definitions 1 and 3, and Theorem 6. End of footnote. Mechanical motion becomes transformed into heat, electricity, magnetism, light, etc., and vice versa. Thus natural science confirms what Hegel has said, in parentheses where, that reciprocal action is the true causa finalis of things. We cannot go back further than to knowledge of this reciprocal action, for the very reason that there is nothing behind to know. If we know the forms of motion of matter, for which it is true there is still very much lacking, in view of the short time that natural science has existed, then we know matter itself, and therewith our knowledge is complete. Grove's whole misunderstanding about causality rests on the fact that he does not succeed in arriving at the category of reciprocal action. He has the thing, but not the abstract thought, and hence the confusion. Pages 10 to 14. Only from this universal reciprocal action do we arrive at the real causal relation. In order to understand the separate phenomena, we have to tear them out of the general interconnection and consider them in isolation, and then the changing motions appear, one as cause and the other as effect. For one who denies causality, every natural law is a hypothesis, among others also the chemical analysis of heavenly bodies, by means of the prismatic spectrum. What shallowness of thought to remain at such a viewpoint. On Negeli's incapacity to know the infinite. Negeli, pages 12-13. Footnote. This heading is given in the list of contents drawn up by Engels for the second folder of materials for Dialectics of Nature. This note is devoted to a critical analysis of the basic thesis put forward by the botanist Negeli in his lecture to the Munich Congress of German Natural Scientists and Physicians on September 20th, 1877. Negeli's lecture was entitled The Limits of Natural Scientific Knowledge. Engels quotes it according to the appendix to the Congress report, Tagblatt der 15, Versammlung Deutscher Naturforscher und Ärzte in München, 1877. This edition was supplied to Engels in all probability by K. Schorlemer, who attended the Congress. End of footnote. Negeli first of all says that we cannot know real qualitative differences, and immediately afterwards says that such quote-unquote absolute differences do not occur in nature. Page 12. Firstly, every quality has infinitely many quantitative gradations. For example, shades of color, hardness and softness, length of life, etc. And these, although qualitatively distinct, are measurable and knowable. Secondly, qualities do not exist, but only things with qualities, and indeed with infinitely many qualities. Two different things always have certain qualities, properties of corporeality at least, in common, others differing in degree, while still others may be entirely absent in one of them. If we consider two such extremely different things, for example a meteorite and a man, in separation, we get very little out of it. At most, that heaviness and other general properties of bodies are common to both. But an infinite series of other natural objects and natural processes can be put between the two things, permitting us to complete the series from meteorite to man, and to allocate to each its place in the interconnection of nature, and thus to know them. Negeli himself admits this. Thirdly, our various senses might give us impressions differing absolutely as regards quality. In that case, properties which we experience by means of sight, hearing, smell, taste, and touch would be absolutely different. But even here, the differences disappear with the progress of investigation. Smell and taste have long ago been recognized as allied senses belonging together, which perceive conjoint if not identical properties. Sight and hearing both perceive wave oscillations. Touch and sight supplement each other to such an extent that from the appearance of an object we can often enough predict its tactile properties. And finally, it is always the same eye that receives and elaborates all these different sense impressions, that therefore comprehends them into a unity, and likewise these various impressions are provided by the same thing, appearing as its common properties, and therefore helping us to know it. To explain these different properties accessible only to different senses, to bring them into connection with one another, is precisely the task of science, which so far has not complained, because we have not a general sense in place of the 5 special senses, or because we are not able to see or hear tastes and smells. Wherever we look, nowhere in nature are there to be found such, quote-unquote, qualitatively or absolutely distinct fields, page 12, which are alleged to be incomprehensible. The whole confusion springs from the confusion about quality and quantity. In accordance with the prevailing mechanical view, Nageli regards all qualitative differences as explained only in so far as they can be reduced to quantitative differences, on which what is necessary is said elsewhere, or because quality and quantity are for him absolutely distinct categories, metaphysics. Quote, "We can know only the finite," unquote, etc., page 13. This is quite correct insofar as only finite objects enter the sphere of our knowledge. But the proposition needs to be supplemented by this, quote, "Fundamentally, we can know only the infinite," unquote. In fact, all real exhaustive knowledge consists solely in raising the individual thing in thought from individuality into particularity, and from this into universality, in seeking and establishing the infinite in the finite, the eternal in the transitory. The form of universality, however, is the form of self-completeness, hence of infinity. It is the comprehension of the many finites in the infinite. We know that chlorine and hydrogen, within certain limits of temperature and pressure and under the influence of light, combine with an explosion to form hydrochloric acid gas, and as soon as we know this, we know also that this takes place everywhere and at all times, where the above conditions are present, and it can be a matter of indifference whether this occurs once or is repeated 1,000,000 times, or on how many heavenly bodies. The form of universality in nature is law, and no one talks more of the eternal character of the laws of nature than the natural scientists. Hence, when Nageli says that the finite is made impossible to understand, by not desiring to investigate merely this finite, but instead adding something eternal to it, then he denies either the possibility of knowing the laws of nature or their eternal character. All true knowledge of nature is knowledge of the eternal, the infinite, and hence essentially absolute. But this absolute knowledge has an important drawback. Just as the infinity of knowable matter is composed of the purely finite things, so the infinity of the thought, which knows the absolute, is composed of an infinite number of finite human minds, working side by side and successively at this infinite knowledge, committing practical and theoretical blunders, setting out from erroneous, one-sided and false premises, pursuing false, tortuous and uncertain paths, and often not even finding what is right when they run their noses against it. In parentheses, Priestley. Footnote. Engels is referring to the discovery of oxygen in 1774 by Joseph Priestley, who did not even guess that he had discovered a new chemical element, and that this discovery would lead to a revolution in chemistry. Engels speaks in more detail about this discovery in his preface to the 2nd volume of Marx's Capital. End of footnote. The cognition of the infinite is therefore beset with double difficulty, and from its very nature can only take place in an infinite, asymptotic progress. And that fully suffices us in order to be able to say, the infinite is just as much knowable as unknowable, and that is all that we need. Curiously enough, Nageli says the same thing, quote, "We can know only the finite, but we can know all the finite that comes into the sphere of our sensuous perception," unquote. The finite that comes into the sphere, etc., constitutes in sum precisely the infinite, for it is just from this that Nageli has derived his idea of the infinite. Without this finite, etc., he would have indeed no idea of the infinite. Bad infinity as such to be dealt with elsewhere. Before this investigation of infinity comes the following. 1. The so-called insignificant sphere in regard to space and time. 2. The quote-unquote probable defective development of the sense organs. 3. That we, quote, only know the finite, changing, transitory, only what is different in degree and relative, because we can only transfer mathematical concepts to natural objects and judge the latter only by measures obtained from themselves. We have no notions for all that is infinite or eternal, for all that is permanent, for all absolute differences. We know exactly the meaning of an hour, a meter, a kilogram, but we do not know what time, space, force and matter, motion and rest, cause and effect are." Unquote. It is the old story. First of all, one makes sensuous things into abstractions, and then one wants to know them through the senses, to see time and smell space. The empiricist becomes so steeped in the habit of empirical experience that he believes that he is still in the field of sensuous experience when he is operating with abstractions. We know what an hour is, or a meter, but not what time and space are. As if time was anything other than just hours, and space anything but just cubic meters. The two forms of existence of matter are naturally nothing without matter, empty concepts, abstractions which exist only in our minds. But of course, we are supposed not to know what matter and motion are. Of course not, for matter as such and motion as such have not yet been seen or otherwise experienced by anyone, only the various existing material things and forms of motion. Matter is nothing but the totality of material things from which this concept is abstracted, and motion as such, nothing but the totality of all sensuously perceptible forms of motion. Words like matter and motion are nothing but abbreviations, in which we comprehend many different sensuous perceptible things according to their common properties. Hence, matter and motion can be known in no other way than by investigation of the separate material things and forms of motion, and by knowing these, we also pro tanto know matter and motion as such. Consequently, in saying that we do not know what time, space, matter, motion, cause and effect are, Negeli merely says that first of all we make abstractions of the real world through our minds, and then cannot know these self-made abstractions, because they are creations of thought and not sensuous objects, while all knowing is sensuous measurement. This is just like the difficulty mentioned by Hegel. We can eat cherries and plums, but not fruit, because no one has so far eaten fruit as such. Footnote. See Hegel, Encyclopedia of the Philosophical Sciences, section 13, note, quote, "When the universal is made a mere form and coordinated with the particular, it sinks into a particular itself. Even common sense in everyday matters is above the absurdity of setting a universal beside the particulars. Would anyone who wished for fruit reject cherries, pears, and grapes on the ground that they were cherries, pears, or grapes, and not fruit?" Unquote. End of footnote. When Negeli asserts that there are probably a whole number of forms of motion in nature which we cannot perceive by our senses, that is a poor apology, equivalent to the suspension, at least for our knowledge, of the laws of the uncreatability of motion, for they could certainly be transformed into motion perceptible to us. That would be an easy explanation of, for instance, contact electricity. Ad vocem Negeli. Impossibility of conceiving the infinite. When we say that matter and motion are not created and are indestructible, we are saying that the world exists as an infinite progress, that is, in the form of bad infinity, and thereby we have understood all of this process that is to be understood. At the most, the question still arises whether this process is an eternal repetition in great cycles, or whether the cycles have descending and ascending branches. Bad infinity. True infinity was already correctly put by Hegel in filled space and time, in the process of nature and in history. The whole of nature also is now merged in history, and history is only differentiated from natural history as the evolutionary process of self-conscious organisms. The infinite complexity of nature and history has within it the infinity of space and time, bad infinity, only as a sublated factor, essential but not predominant. The extreme limit of our natural science until now has been our universe, and we do not need the infinitely numerous universes outside it to have knowledge of nature. Indeed, only a single sun among millions with its solar system forms the essential basis of our astronomical researches. For terrestrial mechanics, physics, and chemistry, we are more or less restricted to our little Earth, and for organic science entirely so. Yet, this does not do any essential injury to the practically infinite diversity of phenomena and natural knowledge, any more than history is harmed by the similar, even greater limitation to a comparatively short period and small portion of the Earth. 1. According to Hegel, infinite progress is a barren waste because it appears only as eternal repetition of the same thing, 1 + 1 + 1, etc. 2. In reality, however, it is no repetition, but a development, an advance or regression, and thereby it becomes a necessary form of motion. This apart from the fact that it is not infinite. The end of the Earth's lifetime can already be foreseen, but then, the Earth is not the whole universe. In Hegel's system, any development was excluded from the temporal history of nature. Otherwise, nature would not be the being beyond self of spirit. But in human history, infinite progress is recognized by Hegel as the sole true form of existence of spirit, except that fantastically, this development is assumed to have an end in the production of the Hegelian philosophy. 3. There is also infinite knowing, quantity, page 259, Astronomy. Questa infinita che le cose non hanno in progresso, la hanno in giro. This infinite, which things do not have in progress, they have in circling. Footnote. This is a quotation slightly modified by Engels from the treatise Della Moneta on money of the Italian economist Galliani. This same quotation was used by Marx in Volume 1 of Capital. Marx and Engels used the custody edition Scrittori classici italiani di economia politica, parte moderna, Book 3, Milano, 1803, page 156. End of footnote. Thus, the law of the change of form of motion is an infinite one, including itself in itself. Such infinities, however, are in their turn smitten with finiteness, and only occur piecemeal. So also 1 divided by r squared. Footnote. The words, so also 1 divided by r squared, were added subsequently by Engels. It is possible that Engels had in mind the number pi, which has a quite definite meaning, but which cannot be expressed by a finite decimal or an ordinary fraction. If the area of a circle is taken as 1, the formula pi r squared equals 1 gives pi equals 1 divided by r squared, where r is the radius of the circle. End of footnote. The eternal laws of nature also become transformed more and more into historical ones. That water is fluid from 0 Celsius to 100 Celsius is an eternal law of nature, but for it to be valid, there must be 1. Water, 2. The given temperature, 3. Normal pressure. On the moon there is no water, in the sun only its elements, and the law does not exist for these two heavenly bodies. The laws of meteorology are also eternal, but only for the Earth or for a body of the size, density, axial inclination, and temperature of the Earth, and on condition that it has an atmosphere of the same mixture of oxygen and nitrogen, and with the same amounts of water vapor being evaporated and precipitated. The moon has no atmosphere, the sun one of glowing metallic vapors. The former has no meteorology, that of the latter is quite different from ours. Our whole official physics, chemistry and biology are exclusively geocentric, calculated only for the Earth. We are still quite ignorant of the conditions of electric and magnetic tensions on the Sun, fixed stars, and nebulae, even on the planets of a different density from ours. On the Sun, owing to high temperature, the laws of chemical combination of the elements are suspended or only momentarily operate at the limits of the solar atmosphere, the compounds becoming dissociated again on approaching the Sun. The chemistry of the Sun is just in process of arising, and is necessarily quite different from that of the Earth, not overthrowing the latter, but standing outside it. In the nebulae, perhaps there do not exist even those of the 65 elements, which are possibly themselves of compound nature. Hence, if we wish to speak of general laws of nature that are uniformly applicable to all bodies, from the nebula to man, we are left only with gravity, and perhaps the most general form of the theory of the transformation of energy, vulgo the mechanical theory of heat. But on its general, consistent application to all phenomena of nature, this theory itself becomes converted into a historical presentation of the successive changes occurring in a system of the universe, from its origin to its passing away, hence into a history in which at each stage different laws, that is, different phenomenal forms of the same universal motion, predominate, and so nothing remains as absolutely universally valid except motion. The geocentric standpoint in astronomy is prejudiced and has rightly been abolished, but as we go deeper in our investigations, it comes more and more into its own. The Sun, etc., serve the Earth. Hegel, Naturphilosophie, page 155. Footnote. Engels is referring to the following passage in Hegel's Philosophy of Nature. Quote, "The Sun serves the planet just as in general sun, moon, comets, stars are merely significations of the Earth." Unquote. Section 280, Addendum. End of footnote. The whole huge Sun exists merely for the sake of the little planets. Anything other than geocentric physics, chemistry, biology, meteorology, etc. is impossible for us, and these sciences lose nothing by saying that they only hold good for the Earth, and are therefore only relative. If one takes that seriously and demands a centerless science, one puts a stop to all science. It suffices us to know that under the same conditions everywhere, the same must take place. At a distance to the right or to the left of us is a million times as great as the distance from the Earth to the Sun. Cognition. Ants have eyes different from ours. They can see chemical light rays. In parentheses, Nature, June 8, 1882, Lubbock. But as regards knowledge of these rays that are invisible to us, we are considerably more advanced than the ants, and the very fact that we are able to demonstrate that ants can see things invisible to us, and that this proof is based solely on perceptions made with our eyes, shows that the special construction of the human eye sets no absolute barrier to human cognition. Footnote. Engels is referring to George Romain's review of Sir John Lubbock's book Ants, Bees and Wasps, London 1882. The review appeared in the British journal Nature, number 658 of June 8, 1882. The passage which interested Engels, that ants are, quote, very sensitive to the ultraviolet rays, unquote, occurs on page 122 of volume 26 of Nature. End of footnote. In addition to the eye, we have not only the other senses, but also our thought activity. With regard to the latter, matters stand exactly as with the eye. To know what can be discovered by our thinking, it is no use 100 years after Kant to try and find out the range of thought from the critique of reason or the investigation of the instruments of knowing. It is as little use as when Helmholtz uses the imperfection of our sight Indeed, a necessary imperfection, for an eye that could see all rays would for that very reason see nothing at all, and the construction of our eye, which restricts sight to definite limits, and even so does not give quite correct reproduction, as proof that the eye acquaints us incorrectly or unreliably with the nature of what is seen. What can be discovered by our thought is more evident from what it has already discovered, and is every day still discovering, and that is already enough both as regards quantity and quality. On the other hand, the investigation of the forms of thought, the thought determinations, is very profitable and necessary, and since Aristotle, this has been systematically undertaken only by Hegel. In any case, we shall never find out how chemical rays appear to ants. Anyone who is distressed by this is simply beyond help. The form of development of natural science, in so far as it thinks, is the hypothesis. A new fact is observed, which makes impossible the previous method of explaining the facts belonging to the same group. From this moment onwards, new methods of explanation are required. At first, based only on a limited number of facts and observations. Further observational material weeds out these hypotheses, doing away with some and correcting others, until finally the law is established in a pure form. If one should wait until the material for a law was in a pure form, it would mean suspending the process of thought in investigation until then, and, if only for this reason, the law would never come into being. The number and succession of hypotheses supplanting one another, given the lack of logical and dialectical education among natural scientists, easily gives rise to the idea that we cannot know the essence of things, in parentheses Haller and Goethe. Footnote. Engels is referring to A. von Haller's poem Falschheit der menschlichen Tugenden, in which Haller asserted, quote, "No mortal mind can nature's inner secrets tell, too happy only if he knows the outer shell." Unquote. Goethe in his poem Allerdings, 1820, opposed Haller's assertion, pointing out that nature is a single unity and cannot be divided, as is done by Haller, into an unknowable inner kernel and an outer shell accessible to man. Hegel mentions this argument between Goethe and Haller twice in his Encyclopedia of the Philosophical Sciences, section 140, note, and section 246, addendum. End of footnote. This is not peculiar to natural science, since all human knowledge develops in a much twisted curve, and in the historical sciences also, including philosophy, theories displace one another, from which, however, nobody concludes that formal logic, for instance, is nonsense. The last form of this outlook is the so-called thing in itself. In the first place, this assertion that we cannot know the thing in itself, in parentheses Hegel, Encyclopedia, paragraph 44, passes out of the realm of science into that of fantasy. Secondly, it does not add a word to our scientific knowledge, for if we cannot occupy ourselves with things, they do not exist for us. And thirdly, it is a mere phrase and is never applied. Taken in the abstract, it sounds quite sensible, but suppose one applies it. What would one think of a zoologist who said, quote, "A dog seems to have 4 legs, but we do not know whether in reality it has 4 million legs or none at all," unquote. Or of a mathematician who first of all defines a triangle as having 3 sides, and then declares that he does not know whether it might not have 25. That 2 times 2 seems to be 4. But scientists take care not to apply the phrase about the thing in itself in natural science. They permit themselves this only in passing into philosophy. This is the best proof how little seriously they take it, and what little value it has itself. If they did take it seriously, what would be the good of investigating anything? Taken historically, the thing would have a certain meaning. We can only know under the conditions of our epoch, and as far as these allow. The thing in itself. Hegel, Logic 2, page 10, also later a whole section on it. Footnote. Hegel, Science of Logic, Book 2, Section 1, Chapter 1, Paragraph Show, and Section 2, Appearance. which contains a special paragraph on thing in itself and existence, and an observation, the thing in itself of transcendental idealism. End of footnote. Quote, skepticism did not dare to affirm it is. Modern idealism, that is Kant and Fichte, did not dare to regard cognition as a knowledge of the thing in itself. Note in the margin of the manuscript, quote, see Encyclopedia 1, page 252, unquote. End of note in the margin. Footnote, Hegel, Encyclopedia of the Philosophical Sciences, section 124, observation and addendum. End of footnote. But at the same time, skepticism admitted manifold determinations of its show, or rather, its show had for content all the manifold riches of the world. In the same manner, the quote-unquote appearance of idealism, that is, what idealism calls appearance, comprehends the whole range of these manifold determinatenesses. The content may then have no basis in any being, nor in any thing, nor thing in itself. For itself, it remains as it is. It has only been translated from being into show. Unquote. Hegel, therefore, is here a much more resolute materialist than the modern natural scientists. Valuable self-criticism of the Kantian thing in itself, which shows that Kant suffers shipwreck also on the thinking ego and likewise discovers in it an unknowable thing in itself. Hegel 5, page 256, etc. Footnote, Hegel, Science of Logic, Book 3, Section 3, Chapter 2. End of footnote. Forms of motion of matter. Classification of the sciences. Causa finalis. Matter and its inherent motion. This matter is no abstraction. Even in the sun, the different substances are dissociated and without distinction in their action. But in the gaseous sphere of the nebula, all substances, although separately present, become merged in pure matter as such, acting only as matter, not according to their specific properties. Moreover, already in Hegel, the antithesis of causa efficiens and causa finalis is sublated in reciprocal action. Primordial matter, quote, the conception of matter as original and pre-existent, and as naturally formless, is a very ancient one. It meets us even among the Greeks, at first in the mythical shape of chaos, which is supposed to represent the unformed substratum of the existing world. Unquote. Hegel, Encyclopedia 1, page 258. Footnote, Hegel, Encyclopedia of the Philosophical Sciences, section 128, addendum. End of footnote. We find this chaos again in Laplace, and approximately in the nebula, which also has only the beginning of form. Differentiation comes afterwards. Gravity, as the most general determination of materiality, is commonly accepted. That is to say, attraction is a necessary property of matter, but not repulsion. But attraction and repulsion are as inseparable as positive and negative, and hence, from dialectics itself, it can already be predicted that the true theory of matter must assign as important a place to repulsion as to attraction, and that a theory of matter based on mere attraction is false, inadequate, and one-sided. In fact, sufficient phenomena occur that demonstrate this in advance. If only on account of light, the ether is not to be dispensed with. Is the ether of material nature? If it exists at all, it must be of material nature. It must come under the concept of matter, but it is not affected by gravity. The tail of a comet is granted to be of material nature. It shows a powerful repulsion. Heat in a gas produces repulsion, etc. Attraction and gravitation. The whole theory of gravitation rests on saying that attraction is the essence of matter. This is necessarily false. Where there is attraction, it must be complemented by repulsion. Hence, already Hegel was quite right in saying that the essence of matter is attraction and repulsion. Footnote, Opus Citato, section 98, addendum 1, quote, attraction is as essential a part of matter as repulsion." Unquote. End of footnote. And in fact, we are more and more becoming forced to recognize that the dissipation of matter has a limit where attraction is transformed into repulsion, and conversely, the condensation of the repelled matter has a limit where it becomes attraction. The transformation of attraction into repulsion and vice versa is mystical in Hegel, but in substance he anticipated by it the scientific discovery that came later. Even in a gas there is repulsion of the molecules, still more so in more finely divided matter, for instance in the tail of a comet, where it even operates with enormous force. Hegel shows his genius even in the fact that he derives attraction as something secondary from repulsion as something preceding it. A solar system is only formed by the gradual preponderance of attraction over the originally prevailing repulsion. Expansion by heat equals repulsion, the kinetic theory of gases. The divisibility of matter. For science, the question is in practice a matter of indifference. We know that in chemistry there is a definite limit to divisibility, beyond which bodies can no longer act chemically, the atom, and that several atoms are always in combination, the molecule. Ditto in physics. We are driven to the acceptance of certain, for physical analysis, smallest particles, the arrangement of which determines the form and cohesion of bodies. Their vibration becomes evident as heat, etc. But whether the physical and chemical molecules are identical or different, we do not know yet. Hegel very easily gets over this question of divisibility by saying that matter is both divisible and continuous, and at the same time neither of the two, which is no answer but is now almost proved. See sheet 5.3 below, Clausius. Footnote. See Hegel, Science of Logic, Book 1, Section 11, Chapter 1, Observation on Kant's antinomy of the indivisibility and infinite divisibility of time, space, and matter. End of footnote. Divisibility. Mammal is indivisible. The reptile can regrow a foot. Ether waves, divisible and measurable to the infinitesimally small. Every body divisible, in practice within certain limits, for example in chemistry. Quote, "Its essence of motion is to be immediate unity of space and time. To motion belong space and time. Velocity, the quantum of motion, is space in relation to a definite time that has elapsed." Unquote. Hegel, Naturphilosophie, page 65. Quote, "Space and time are filled with matter. Just as there is no motion without matter, so there is no matter without motion." Unquote. Page 67. Footnote. Hegel, Naturphilosophie, Philosophy of Nature, section 261, addendum. End of footnote. The indestructibility of motion in Descartes' principle that the universe always contains the same quantity of motion. Footnote. The idea of the preservation of the quantity of motion was expressed by Descartes in his Treatise on Light, first part of the work Le Monde, the World, written in 1630-33 and published posthumously in 1664, and in his letter to de Bonne, dated April 30th, 1639. This proposition is given in its most complete form in R. Descartes' Principia Philosophiae, Principles of Philosophy, Amsterdam, 1644, Pars Secunda, 26. End of footnote. Natural scientists express this imperfectly as the quote-unquote indestructibility of force. The merely quantitative expression of Descartes is likewise inadequate. Motion as such, as essential activity, the mode of existence of matter, is indestructible as the latter itself. This formulation includes the quantitative element. So here again, the philosopher has been confirmed by the natural scientist after 200 years. The indestructibility of motion, a pretty passage in Grove, page 20 et seq. Footnote. Grove, The Correlation of Physical Forces, On pages 20 to 29, Grove speaks of the so-called indestructibility of force, when mechanical motion is converted into a quote-unquote state of tension and into heat. End of footnote. Motion and equilibrium. Equilibrium is inseparable from motion. Note in the margin, equilibrium equals predominance of attraction over repulsion. End of note in the margin. In the motion of the heavenly bodies, there is motion in equilibrium and equilibrium in motion, in parentheses, relative. But all specifically relative motion, that is, here all separate motion of individual bodies on one of the heavenly bodies in motion, is an effort to establish relative rest, equilibrium. The possibility of bodies being at relative rest, the possibility of temporary states of equilibrium, is the essential condition for the differentiation of matter and hence for life. On the Sun, there is no equilibrium of the various substances, only of the mass as a whole, or at any rate only a very restricted one, determined by considerable differences of density. On the surface, there is eternal motion and unrest, dissociation. On the Moon, equilibrium appears to prevail exclusively, without any relative motion death. In parentheses, moon equals negativity. On the Earth, motion has become differentiated into interchange of motion and equilibrium. The individual motion strives towards equilibrium. The motion as a whole once more destroys the individual equilibrium. The rock comes to rest, but weathering, the action of the ocean surf, of rivers and glacier ice, continually destroy the equilibrium. Evaporation and rain, wind, heat, electric and magnetic phenomena offer the same spectacle. Finally, in the living organism, we see continual motion of all the smallest particles, as well as of the larger organs, resulting in the continual equilibrium of the total organism during the normal period of life, which yet always remains in motion, the living unity of motion and equilibrium. All equilibrium is only relative and temporary. 1. Motion of the heavenly bodies, approximate equilibrium of attraction and repulsion in motion. 2. Motion on one heavenly body, mass. Insofar as this motion comes from pure mechanical causes, here also there is equilibrium. The masses are at rest on their foundation. On the Moon, this is apparently complete. Mechanical attraction has overcome mechanical repulsion. From the standpoint of pure mechanics, we do not know what has become of the repulsion, and pure mechanics just as little explains whence come the forces by which nevertheless masses on the Earth, for example, are set in motion against gravity. It takes the fact for granted. Here, therefore, there is simple communication of repelling, displacing motion from mass to mass, without equality of attraction and repulsion. 3. The overwhelming majority of all terrestrial motions, however, are made up of the conversion of one form of motion into another, mechanical motion into heat, electricity, chemical motion, and of each form into any other. Hence, either the transformation of attraction into repulsion, mechanical motion into heat, electricity, chemical decomposition, the transformation is the conversion of the original, lifting mechanical on into heat, not of the falling motion, which is only the semblance, or the transformation of repulsion into attraction. 4. All energy now active on the Earth is transformed heat from the Sun. Footnote. This note was written on the same sheet as outline of part of the plan and is a conspectus of ideas developed by Engels in the chapter Basic Forms of Motion. End of footnote. Mechanical motion. Among natural scientists, motion is always, as a matter of course, taken to mean mechanical motion, change of place. This has been handed down from the pre-chemical 18th century and makes a clear conception of the process much more difficult. Motion, as applied to matter, is change in general. From the same misunderstanding is derived also the craze to reduce everything to mechanical motion. Even Grove is, quote, strongly inclined to believe that the other affections of matter are and will ultimately be resolved into modes of motion, unquote, page 16. Footnote. Grove, The Correlation of Physical Forces. By, quote-unquote, affections of matter, Grove means, quote, heat, light, electricity, magnetism, chemical affinity, and motion, unquote, page 15, and by quote-unquote motion, he means mechanical motion or displacement, end of footnote, which obliterates the specific character of the other forms of motion. This is not to say that each of the higher forms of motion is not always necessarily connected with some real mechanical, external or molecular motion, just as the higher forms of motion simultaneously also produce other forms, and just as chemical action is not possible without change of temperature and electric changes, organic life without mechanical, molecular, chemical, thermal, electric, etc. changes. But the presence of these subsidiary forms does not exhaust the essence of the main form in each case. One day we shall certainly, quote-unquote, reduce thought experimentally to molecular and chemical motions in the brain, but does that exhaust the essence of thought? Dialectics of Natural Science. Footnote. This outline was written on the first sheet of the first folder of Dialectics of Nature. As regards its contents, it coincides with Engels' letter to Marx, dated May 30th, 1873. This letter begins with the words, quote, "This morning in bed, the following dialectical ideas about natural science came into my head," unquote. The exposition of these ideas is more definite in the letter than in the present outline. It may be inferred that the outline was written before the letter on the same day, May 30th, 1873, not counting the fragment on Buchner, which was written shortly before this outline. All the other chapters and fragments of Dialectics of Nature were written later, that is, after May 30th, 1873. End of footnote. Subject matter, matter in motion. The different forms and varieties of matter itself can likewise only be known through motion. Only in this are the properties of bodies exhibited. Of a body that does not move, there is nothing to be said. Hence, the nature of bodies in motion results from the forms of motion. 1. The first, simplest form of motion is the mechanical form, pure change of place. A. Motion of a single body does not exist. It can be spoken of only in a relative sense, falling. B. The motion of separated bodies, trajectory, astronomy, apparent equilibrium, the end always contact. C. The motion of bodies in contact in relation to one another, pressure, statics, hydrostatics and gases, the lever and other forms of mechanics proper, which all in their simplest form of contact amount to friction or impact, which are different only in degree. But friction and impact, in fact contact, have also other consequences, never pointed out here by natural scientists. They produce, according to circumstances, sound, heat, light, electricity, magnetism. 2. These different forces, with the exception of sound, physics of heavenly bodies, A. Pass into one another and mutually replace one another, and B. On a certain quantitative development of each force, different for each body, applied to the bodies, whether they are chemically compound or several chemically simple bodies, chemical changes take place, and we enter the realm of chemistry. Chemistry of heavenly bodies. Crystallography, part of chemistry. 3. Physics had to leave out of consideration the living organic body, or could do so. Chemistry finds only in the investigation of organic compounds the real key to the true nature of the most important bodies, and, on the other hand, it synthesizes bodies which only occur in organic nature. Here chemistry leads to organic life, and it has gone far enough to assure us that it alone will explain to us the dialectical transition to the organism. 4. The real transition, however, is in history of the solar system, the Earth, the real precondition for organic nature. 5. Organic nature. Classification of the sciences, each of which analyzes a single form of motion, or a series of forms of motion that belong together and pass into one another, is therefore the classification, the arrangement of these forms of motion, themselves according to their inherent sequence, and herein lies its importance. At the end of the last 18th century, after the French materialists, who were predominantly mechanical, the need became evident for an encyclopedic summing up of the entire natural science of the old Newton-Linnaeus school, and two men of the greatest genius undertook this, Saint-Simon, in parentheses uncompleted, and Hegel. Today, when the new outlook on nature is complete in its basic features, the same need makes itself felt, and attempts are being made in this direction. But since the general evolutionary connection in nature has now been demonstrated, an external side-by-side arrangement is as inadequate as Hegel's artificially constructed dialectical transitions. The transitions must make themselves. They must be natural. Just as one form of motion develops out of another, so their reflections, the various sciences, must arise necessarily out of one another. How little Comte can have been the author of his encyclopedic arrangement of the natural sciences, which he copied from Saint-Simon, is already evident from the fact that it only serves him for the purpose of arranging the means of instruction and course of instruction, and so leads to the crazy enseignement integral, where one science is always exhausted before another is even broached, where a basically correct idea is pushed to a mathematical absurdity. Footnote. A. Comte set out this system of classification of the sciences in his main work, A Course of Positive Philosophy, first published in Paris in 1830-42. The question of classification of the sciences is specifically dealt with in the second lecture in Volume 1 of the book, headed An Exposition of the Plan of this Course, or General Considerations Concerning the Hierarchy of the Positive Sciences. See A. Comte, Cours de Philosophie Positive, Volume 1, Paris, 1830. End of footnote. Hegel's division, the original one, into mechanics, chemics, and organics, fully adequate for the time. Footnote. Engels is referring to the third part of Hegel's Science of Logic, first published in 1816. In his Philosophy of Nature, Hegel denotes these three main divisions of natural science by the terms mechanics, physics, and organics. End of footnote. Mechanics, the movement of masses. Chemics, molecular, for physics is also included in this, and indeed both physics as well as chemistry belong to the same order, motion and atomic motion. Organics, the motion of bodies in which the two are inseparable, for the organism is certainly the higher unity, which within itself unites mechanics, physics, and chemistry into a whole where the trinity can no longer be separated. In the organism, mechanical motion is affected directly by physical and chemical change, in the form of nutrition, respiration, secretion, etc., just as much as pure muscular movement. Each group in turn is twofold. Mechanics, 1. Celestial, 2. Terrestrial. Molecular motion, 1. Physics, 2. Chemistry. Organics, 1. Plant, 2. Animal. Physiography. After the transition from chemistry to life has been made, then in the first place it is necessary to analyze the conditions in which life has been produced and continues to exist. That is, first of all, geology, meteorology, and the rest. Then the various forms of life themselves, which indeed without this are incomprehensible. On the so-called mechanical conception of nature, regarding page 46, the various forms of motion and the sciences dealing with them. Footnote. This note is one of those three larger notes which Engels put in the second folder of materials for Dialectics of Nature. The smaller notes were put in the first and fourth folders. Two of these notes, on the prototypes of the mathematical infinite in the real world, and on the so-called mechanical conception of nature, are notes or addenda to Anti-Düring, in which Engels elaborates some very important ideas that were only outlined or stated in brief in various parts of Anti-Düring. The third note, Nägeli's inability to cognize the infinite, has nothing to do with Anti-Düring. The first two notes were in all probability written in 1885. In any case, they cannot date from earlier than mid-April 1884, when Engels decided to prepare for the press a second enlarged edition of Anti-Düring, or later than late September 1885, when Engels finished and sent to the publisher his preface to the second edition of the book. Engels' letters to Bernstein and Kautsky in 1884 and to Schluter in 1885 indicate that he planned to write a series of addenda and appendices of a natural scientific character to various passages in Anti-Düring, with a view to giving them at the end of the second edition of the book, but owing to being extremely busy with other matters, above all with his work on the second and third volumes of Marx's Capital, Engels was prevented from carrying out his intention. He only managed to make a rough outline of the two notes or addenda to pages 17 to 18 and page 46 of the text of the first edition of Anti-Düring. The present notice is the second of these notes. The heading, on the so-called mechanical conception of nature, was given by Engels in his list of contents of the second folder of Dialectics of Nature. The subheading, Note 2 to page 46, quote, the various forms of motion and the sciences dealing with them, unquote, occurs at the beginning of this notice. End of footnote. Since the above article appeared, in parentheses, Vorwärts, February 9, 1877, Kekule, Die wissenschaftlichen Ziele und Leistungen der Chemie, has defined mechanics, physics, and chemistry in a quite similar way. Quote, if this idea of the nature of matter is made the basis, one could define chemistry as the science of atoms, and physics as the science of molecules, and then it would be natural to separate that part of modern physics which deals with masses as a special science, reserving for it the name of mechanics. Thus mechanics appears as the basic science of physics and chemistry, insofar as in certain aspects, and especially in certain calculations, both of these have to treat their molecules or atoms as masses. Unquote. Footnote. A. Kekule, Die wissenschaftlichen Ziele und Leistungen der Chemie, Bonn, 1878, page 12. End of footnote. It will be seen that this formulation differs from that in the text and in the previous note only by being rather less definite. But when an English journal, Nature, put the above statement of Kekule in the form that mechanics is the statics and dynamics of masses, physics the statics and dynamics of molecules, and chemistry the statics and dynamics of atoms, then it seems to me that this unconditional reduction of even chemical processes to merely mechanical ones unduly restricts the field, at least of chemistry. Footnote. This refers to an item in Nature number 420, November 15, 1877, summarizing A. Kekule's speech on October 18, 1877, when he took the office of rector at the University of Bonn. In 1878, the speech was published in pamphlet form under the title The Scientific Aims and Achievements of Chemistry. End of footnote. And yet, it is so much the fashion that, for instance, Haeckel continually uses quote-unquote mechanical and quote-unquote monistic as having the same meaning, and in his opinion, quote, modern physiology in its field allows only the operation of physico-chemical, or in the wider sense, mechanical forces." Unquote. Perigenesis. Footnote. I Haeckel, die Perigenesis der Plastidule oder die Wellenzeugung der Liebenstäuschen, ein Versuche zur mechanischen Erklärung der elementaren Entwicklungsvorgänge. Berlin, 1874, page 13. End of footnote. If I term physics the mechanics of molecules, chemistry the physics of atoms, and furthermore biology the chemistry of proteins, I wish thereby to express the passing of each of these sciences into another. Hence, both the connection, the continuity, and the distinction, the discrete separation between the two of them. To go further and to define chemistry as likewise a kind of mechanics seems to me inadmissible. Mechanics, in the wider or narrower sense, knows only quantities. It calculates the velocities and masses, and at most with volumes. Where the quality of bodies comes across its path, as in hydrostatics and aerostatics, it cannot achieve anything without going into molecular states and molecular motions. It is itself only an auxiliary science, the prerequisite for physics. In physics, however, and still more in chemistry, not only does continual qualitative change take place in consequence of quantitative change, the transformation of quantity into quality, but there are also many qualitative changes to be taken into account, whose dependence on quantitative change is by no means proven. That the present tendency of science goes into this direction can be readily granted, but does not prove that this direction is the exclusively correct one, that the pursuit of this tendency will exhaust the whole of physics and chemistry. All motion includes mechanical motion, change of place of the largest or smallest portions of matter, and the first task of science, but only the first, is to obtain knowledge of this motion. But this mechanical motion does not exhaust motion as a whole. Motion is not merely change of place. In fields higher than mechanics, it is also change of quality. The discovery that heat is a molecular motion was epoch-making, but if I have nothing more to say of heat than that it is a certain displacement of molecules, I should best be silent. Chemistry seems to be well on the way to explaining a number of chemical and physical properties of elements, from the ratio of the atomic volumes to the atomic weights. But no chemist would assert that all the properties of an element are exhaustively expressed by its position in the Lothar-Meyer curve, that it will ever be possible by this alone to explain, for instance, the peculiar constitution of carbon that makes it the essential bearer of organic life, or the necessity for phosphorus in the brain. Footnote. The Lothar-Meyer curve shows the relation between the atomic weights of the elements and their atomic volumes. It was constructed by L. Meyer, who dealt with it in his article Die Natur der chemischen Elemente als Funktion ihrer Atomgewichte, which appeared in 1870 in the journal Annalen der Chemie und Pharmacie. The discovery of the correlation between the atomic weights of the elements and their physical and chemical properties was made by the great Russian scientist D.I. Mendeleev, who was the first to formulate the periodic law of the chemical elements in his article The Correlation of the Properties of the Elements and Their Atomic Weights, published in March 1869, that is, a year prior to L. Meyer's article, in the Journal of Russian Chemical Society. Meyer, too, was close to establishing the periodic law when he learned about Mendeleev's discovery. The curve made by him graphically illustrated the law discovered by Mendeleev, except that it expressed the law in external and, unlike Mendeleev, one-sided terms. Mendeleev went much further than Meyer in his conclusions. On the basis of the periodic law discovered by him, Mendeleev predicted the existence and specific properties of chemical elements still unknown at the time, whereas L. Meyer in his subsequent works revealed a lack of understanding of the nature of the periodic law. End of footnote. Yet the so-called mechanical conception amounts to nothing else. It explains all change from change of place, all qualitative differences from quantitative ones, and overlooks that the relation of quality and quantity is reciprocal, that quality can become transformed into quantity just as much as quantity into quality, that, in fact, reciprocal action takes place. If all differences and changes of quality are to be reduced to quantitative differences and changes, to mechanical displacement, then we inevitably arrive at the proposition that all matter consists of identical smallest particles, that all the qualitative differences of the chemical elements of matter are caused by quantitative differences in number and by the spatial grouping of those smallest particles to form atoms. But we have not got so far yet. It is our modern natural scientists' lack of acquaintance with any other philosophy than the most mediocre vulgar philosophy, like that now rampant in the German universities, which allows them to use such expressions like mechanical in this way, without taking into account or even suspecting the consequences with which they thereby necessarily burden themselves. The theory of the absolute qualitative identity of matter has its supporters. Empirically, it is equally impossible to refute it or to prove it. But if one asks these people who want to explain everything mechanically whether they are conscious of this consequence and accept the identity of matter, what a variety of answers will be heard. The most comical part about it is that to make so-called materialist equivalent to so-called mechanical derives from Hegel, who wanted to throw contempt on materialism by the addition mechanical. Now, the materialism criticized by Hegel, the French materialism of the 18th century, was in fact exclusively mechanical, and indeed for the very natural reason that at the time physics, chemistry, and biology were still in their infancy, and were very far from being able to offer the basis for a general outlook on nature. Similarly, Haeckel takes from Hegel the translation causae efficientes equals mechanically acting causes, and causae finales equals purposively acting causes, where Hegel therefore puts quote-unquote mechanical as equivalent to blindly acting, unconsciously acting, and not as equivalent to mechanical in Haeckel's sense of the word. But this whole antithesis is for Hegel himself so much a superseded standpoint that he does not even mention it in either of his two expositions of causality in his Logic, but only in his History of Philosophy, in place where it comes historically, hence a sheer misunderstanding on Haeckel's part, due to superficiality, and quite incidentally in dealing with teleology, Logic, Volume 3, 2, 3, where he mentions it as the form in which the old metaphysics conceived the antithesis of mechanism and teleology, but otherwise treating it as a long superseded standpoint. Hence Haeckel copied incorrectly in his joy at finding a confirmation of his quote-unquote mechanical conception, and so arrived at the beautiful result that if a particular change is produced in an animal or plant by natural selection, it has been affected by a causa efficiens, but if the same change arises by artificial selection, then it has been affected by a causa finalis. The breeder a causa finalis. Of course, a dialectician of Hegel's caliber could not be caught in the vicious circle of the narrow antithesis of causa efficiens and causa finalis. And for the modern standpoint, the whole hopeless rubbish about this antithesis is put an end to, because we know from experience and from theory that both matter and its mode of existence, motion, are uncreatable and are therefore their own final cause. While to give the name effective causes to the individual causes, which momentarily and locally become isolated in the mutual interaction of the motion of the universe, or which are isolated by our reflecting mind, adds absolutely no new determination, but only a confusing element. A cause that is not effective is no cause. N.B. Matter as such is a pure creation of thought and an abstraction. We leave out of account the qualitative differences of things in lumping them together as corporeally existing things under the concept of matter. Hence, matter as such, as distinct from definite existing pieces of matter, is not anything sensuously existing. When natural science directs its efforts to seeking out uniform matter as such, to reducing qualitative differences to merely quantitative differences, in combining identical smallest particles, it is doing the same thing as demanding to see fruit as such, instead of cherries, pears, apples, or the mammal as such, instead of cats, dogs, sheep, etc., gas as such, metal, stone, chemical compound as such, motion as such. The Darwinian theory demands such a primordial animal, Haeckel's pro-mammal, but at the same time, it has to admit that if this pro-mammal contained within itself, in germ, all future and existing mammals, it was in reality lower in rank than all existing mammals and primitively crude, hence more transitory than any of them. Footnote: E. Haeckel, Natürliche Schöpfungsgeschichte, 4th German edition, Berlin, 1873, page 538, 543, 588. Anthropogeny, Leipzig, 1847, page 460, 465, 492. End of footnote. As Hegel has already shown, Encyclopédie 1, page 199, this view, this quote-unquote one-sided mathematical view, according to which matter must be looked upon as having only quantitative determination, but qualitatively as identical originally, is, quote, no other standpoint than that, unquote, of the French materialism of the 18th century. Footnote: Hegel, Encyclopedia of the Philosophical Sciences, section 99, addendum. End of footnote. It is even a retreat to Pythagoras, who regarded number, quantitative determination, as the essence of things. In the first place, Kekule. Footnote: this fragment was written on a separate sheet, marked Noten, notes. It may be an original outline of the second note to Anti-Düring, headed on the so-called mechanical conception of nature. End of footnote. Then, the systematizing of natural science, which is now becoming more and more necessary, cannot be found in any other way than in the interconnections of phenomena themselves. Thus, the mechanical motion of small masses on any heavenly body ends in the contact of two bodies, which has two forms, differing only in degree, viz., friction and impact. So we investigate, first of all, the mechanical effect of friction and impact. But we find that the effect is not thereby exhausted. Friction produces heat, light, and electricity. Impact produces heat and light, if not electricity also. Hence conversion of motion of masses into molecular motion. We enter the realm of molecular motion, physics, and investigate further. But here too we find that molecular motion does not represent the conclusion of the investigation. Electricity passes into and arises from chemical transformation. Heat and light, ditto. Molecular motion becomes transformed into motion of atoms, chemistry. The investigation of chemical processes is confronted by the organic world as a field for research, that is to say, a world in which chemical processes take place, although under different conditions, according to the same laws as in the inorganic world, for the explanation of which chemistry suffices. In the organic world, on the other hand, all chemical investigations lead back in the last resort to a body, protein, which, while being the result of ordinary chemical processes, is distinguished from all others by being a self-acting, permanent chemical process. If chemistry succeeds in preparing this protein in the specific form in which it obviously arose, that of a so-called protoplasm, a specificity, or rather absence of specificity, such that it contains potentially within itself all other forms of protein, though it is not necessary to assume that there is only one kind of protoplasm, then the dialectical transition will have been proved in reality, hence completely proved. Until then, it remains a matter of thought, alias of hypothesis. When chemistry produces protein, the chemical process will reach out beyond itself, as in the case of the mechanical process above, that is, it will come into a more comprehensive realm, that of the organism. Physiology is, of course, the physics and especially the chemistry of the living body, but with that it ceases to be specially chemistry. On the one hand, its domain becomes restricted, but on the other hand, inside this domain it becomes raised to a higher power. Mathematics. The so-called axioms of mathematics are the few thought determinations which mathematics needs for its point of departure. Mathematics is the science of magnitudes. Its point of departure is the concept of magnitude. It defines this lamely and then adds the other elementary determinations of magnitude, not contained in the definition, from outside as axioms, so that they appear as unproved and naturally also as mathematically unprovable. The analysis of magnitude would yield all the axiom determinations as necessary determinations of magnitude. Spencer is right inasmuch as what thus appears to us to be the self-evidence of these axioms is inherited. They are provably dialectical, insofar as they are not pure tautologies. Mathematics. Nothing appears more solidly based than the difference between the four species of arithmetical operations, the elements of all mathematics. Yet, right at the outset, multiplication is seen to be an abbreviated addition and division an abbreviated subtraction of a definite number of equal numerical magnitudes, and in one case, when the divisor is a fraction, division is even carried out by multiplying by the inverted fraction. In algebraic calculation, the thing is carried much further. Every subtraction, a minus b, can be represented as an addition, minus b plus a. Every division, a divided by b, as a multiplication, a times 1 divided by b. In calculations with powers of magnitudes, one goes much further still. All rigid differences between the kinds of calculation disappear. Everything can be presented in the opposite form. A power can be put as a root, x squared equals square root of x to the power of 4. A root as a power, square root of x equals x to the power of 1 divided by 2. Unity divided by a power or root can be put as a power of the denominator. 1 divided by the square root of x equals x to the power of minus 1 divided by 2. 1 divided by x cubed equals x minus cubed. Multiplication or division of the powers of a magnitude becomes converted into addition or subtraction of their exponents. Any number can be conceived and expressed as the power of any other number, logarithms y equals a to the power of x, and this transformation of one form into the opposite one is no idle trifling. It is one of the most powerful levers of mathematical science, without which today hardly any of the more difficult calculations are carried out. If negative and fractional powers alone were abolished from mathematics, how far could one get? Minus times minus equals plus, minus divided by minus equals plus, square root of 1, square root of minus 1, etc., to be expounded earlier. The turning point in mathematics was Descartes' variable magnitude. With that came motion, and hence dialectics in mathematics, and at once too of necessity the differential and integral calculus, which moreover immediately begins, and which on the whole was completed by Newton and Leibniz, not discovered by them. Quantity and quality. Number is the purest quantitative determination that we know, but it is chock full of qualitative differences. 1. Hegel, number and unity, multiplication, division, raising to a higher power, extraction of roots. Thereby, and this is not shown in Hegel, qualitative differences already make their appearance, prime numbers and products, simple roots and powers. 16 is not merely the sum of 16 ones, it is also the square of 4, the fourth power of 2. Still more, prime numbers communicate new, definitely determined qualities to numbers derived from them by multiplication with other numbers. Only even numbers are divisible by 2, and there is a similar determination in the case of 4 and 8. For 3, there is the rule of the sum of the figures, and the same thing for 9 and also for 6. In the last case in combination with the even number. For 7, there is a special rule. These form the basis for tricks with numbers which seem incomprehensible to the uninitiated. Hence what Hegel says, quantity, page 237, on the absence of thought in arithmetic is incorrect. Compare, however, measure. Footnote. In the former case, Engels has in mind Hegel's remark that in arithmetic thought moves in so-called thoughtlessness. Science of Logic, Book 1, Section 2, Chapter 2, Observation on the employment of numerical determinations to express philosophic concepts. In the latter case, Hegel's statement that, quote, already the natural numerical system exemplifies a nodal line of qualitative moments which manifest themselves in the merely external progression, unquote, etc. Ibid, Section 3, Chapter 2, Observation on examples of nodal lines of measure relations, Natura non facit saltum, end of footnote. When mathematics speaks of the infinitely large and infinitely small, it introduces a qualitative difference which even takes the form of an unbridgeable qualitative opposition. Quantities so enormously different from one another that every rational relation, every comparison between them ceases, that they become quantitatively incommensurable. Ordinary incommensurability, for instance of the circle and the straight line, is also a dialectical qualitative difference. But here it is the difference in quantity of similar magnitudes that increases the difference of quality to the point of incommensurability. Number. The individual number becomes endowed with quality already in the numerical system itself, and the quality depends on the system used. 9 is not only 1 added together 9 times, but also the basis for 90, 99, 900,000, etc. All numerical laws depend upon and are determined by the system adopted. In dyadic and triadic systems, 2 multiplied by 2 does not equal 4, but equals 100 or equals 11. In all systems with an odd basic number, the difference between odd and even numbers falls to the ground. For example, in the system based on 5, 5 equals 10, 10 equals 20, 15 equals 30. Likewise, in the same system, the sums of digits, 3n of products of 3 or 9, 6 equals 11, 9 equals 14. Hence the basic number determines not only its own quality, but also that of all the other numbers. With powers of numbers, the matter goes still further. Any number can be conceived as the power of any other number. There are as many logarithmic systems as there are whole and fractional numbers. 1. Nothing looks simpler than quantitative unity, and nothing is more manifold than it, as soon as we investigate it in connection with the corresponding plurality and according to its various modes of origin from plurality. First of all, 1 is the basic number of the whole positive and negative system of numbers, all other numbers arising by the successive addition of 1 to itself. 1 is the expression of all positive, negative, and fractional powers of 1, 1 squared, square root of 1, 1 minus squared, are all equal to 1. It is the content of all fractions in which the numerator and denominator prove to be equal. It is the expression of every number that is raised to the power of 0, and therewith the sole number the logarithm of which is the same in all systems, viz. Equals 0. Thus 1 is the boundary that divides all possible systems of logarithms into two parts. If the base is greater than 1, then the logarithms of all numbers more than 1 are positive, and of all numbers less than 1 negative. If it is smaller than 1, the reverse is the case. Hence, if every number contains unity in itself, inasmuch as it is compounded entirely of 1s added together, unity likewise contains all other numbers in itself. This is not only a possibility, inasmuch as we can construct any number solely of 1s, but also a reality, inasmuch as 1 is a definite power of every other number. But the very same mathematicians who, without turning a hair, interpolate into their calculations, wherever it suits them, x to the power of 0 equals 1, or a fraction whose numerator and denominator are equal and which therefore likewise represents 1, who therefore apply mathematically the plurality contained in unity, turn up their noses and grimace if they are told in general terms that unity and plurality are inseparable, mutually penetrating concepts, and that plurality is not less contained in unity than unity is in plurality. How much this is the case we see as soon as we forsake the field of pure numbers. Already in the measurement of lines, surfaces, and the volumes of bodies, it becomes apparent that we can take any desired magnitude of the appropriate order as unity, and the same thing holds for measurement of time, weight, motion, etc. For the measurement of cells, even millimeters and milligrams are too large. For the measurement of stellar distances, or the velocity of light, even the kilometer is uncomfortably small, just as the kilogram for planetary, or even more so, solar masses. Here is seen very clearly what diversity and multiplicity is contained in the concept of unity, at first sight so simple. 0, because it is the negative of any definite quantity, is not therefore devoid of content. On the contrary, 0 has a very definite content. As the borderline between all positive and negative magnitudes, as the sole really neutral number, which can be neither positive nor negative, it is not only a very definite number, but also in itself more important than all other numbers bounded by it. In fact, 0 is richer in content than any other number. Put on the right of any other number, it gives to the latter, in our system of numbers, the tenfold value. Instead of 0, one could use here any other sign, but only on the condition that this sign taken by itself signifies 0, equals 0. Hence, it is part of the nature of 0 itself that it finds this application, and that it alone can be applied in this way. 0 annihilates every other number with which it is multiplied. United with any other number as divisor or dividend, in the former case it makes this infinitely large, in the latter infinitely small. It is the only number that stands in a relation of infinity to every other number. 0 divided by 0 can express every number between minus infinity and plus infinity, and in each case represents a real magnitude. The real content of an equation first clearly emerges when all its members have been brought to one side, and the equation is thus reduced to zero value, as already happens for quadratic equations, and is almost the general rule in higher algebra. The function f, x, y equals 0, can then also be put equal to z, and this z, although it is equal to 0, differentiated like an ordinary dependent variable and its partial derivative determined. The nothing of every quantity, however, is itself quantitatively determined, and only on that account is it possible to calculate with 0. The very same mathematicians who are quite unembarrassed in reckoning with 0 in the above manner, that is, in operating with it as a definite quantitative concept, bringing it into quantitative relation to other quantitative concepts, clutch their heads in desperation when they read this in Hegel generalized as the nothing of a something is a determinate nothing. But now for analytical geometry. Here 0 is a definite point from which measurements are taken along a line, in one direction positively, in the other negatively. Here, therefore, the 0 point has not only just as much significance as any point denoted by a positive or negative magnitude, but a much greater significance than all of them. It is the point on which they are all dependent, to which they are all related, and by which they are all determined. In many cases it can even be taken quite arbitrarily, but once adopted it remains the central point of the whole operation, often determining even the direction of the line along which the other points, the end points of the abscissae, are to be inserted. If, for example, in order to arrive at the equation of the circle, we choose any point of the periphery as the 0 point, then the line of the abscissae must go through the center of the circle. All this finds just as much application in mechanics, where likewise in the calculation of the motions, the point taken as 0 in each case forms the main point and pivot for the entire operation. The 0 point of the thermometer is the very definite lower limit of the temperature section that is divided into any desired number of degrees, thereby serving as a measure both for temperature stages within the section as also for the higher or lower temperatures. Hence, in this case also, it is a very essential point. And even the absolute 0 of the thermometer in no way represents pure abstract negation, but a very definite state of matter, the limit at which the last trace of independent molecular motion vanishes and matter acts only as mass. Wherever we come upon 0, it represents something very definite, and its practical application in geometry, mechanics, etc. proves that, as limit, it is more important than all the real magnitudes bounded by it. 0 powers of importance in the logarithmic series. 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, 10 to the power of 3. All variables pass somewhere through unity. Hence also a constant raised to a variable power. A to the power of x equals 1 if x equals 0. A to the power of 0 equals 1 means nothing more than conceiving unity in its connection with the other members of the series of powers of A. Only there has it any meaning and can lead to results. In parentheses, sigma x to the power of 0 equals x divided by omega. Otherwise, not at all. Footnote. This expression occurs in the book by Boschut, referred to by Engels in the fragment Straight and Curved, in the chapter on Integral Calculation with Finite Differences. In the chapter on integral calculation with finite differences, Boschut examines first of all the following problem, quote, to integrate or sum the whole number steps of a variable magnitude x. Unquote. Bossuet assumes that the difference delta x is constant, and he denotes it by the Greek letter omega. Since the sum of delta x or of w is equal to x, the sum of omega x1 or of omega x to the power of 0 is also equal to x. Bossuet writes this equation in the form sigma omega x to the power of 0 equals x. Bossuet then takes out the constant omega and puts it before the summation sign, obtaining the expression omega sigma x to the power of 0 equals x, from x divided by omega, which he obtains the equation sigma x to the power of 0 equals w divided by omega. This last equation is then used by Bossuet to find the magnitudes sigma x squared, sigma x cubed, etc. for solving other problems. See Bossuet, Traité de calcul différentiel et de calcul intégral, Volume 1, Paris, 1798, page 38. End of footnote. From this it follows that unity also, however much it may appear identical with itself, includes within it an infinite manifoldness, since it can be the zero power of any other possible number, and that this manifoldness is not merely imaginary, is proved on each occasion where unity is conceived as a determined unity, as one of the variable results of a process, as a momentary magnitude or form of a variable, in connection with this process. Square root of -1. The negative magnitudes of algebra are only real in so far as they are connected with positive magnitudes, and only within the relation to the latter. Outside this relation, taken by themselves, they are purely imaginary. In trigonometry and analytical geometry, together with the branches of higher mathematics, of which these are the basis, they express a definite direction of motion, opposite to the positive direction. But the sine and tangent of the circle can be reckoned from the upper right-hand quadrant, just as well from the lower right-hand quadrant, thus directly reversing plus and minus. Similarly, in analytical geometry, abscissae can be calculated from the periphery or from the center of the circle. Indeed, in all curves, they can be reckoned from the curve in the direction usually denoted as minus, or in any desired direction, and still give a correct rational equation of the curve. Here, plus exists only as the complement of minus, and vice versa. But algebraic abstraction treats them, negative magnitudes, as real and independent, even outside the relation to a larger positive magnitude. Mathematics. To common sense, it appears an absurdity to resolve a definite magnitude, for example a binomial expression, into an infinite series, that is, into something indefinite. But where would we be without infinite series and the binomial theorem? Asymptotes. Geometry begins with the discovery that straight and curved are absolute opposites. The straight is absolutely inexpressible in curved, and curved in straight, that the two are incommensurable. Yet even the calculation of the circle is only possible by expressing its periphery in straight lines. For curves with asymptotes, however, straight becomes completely merged in curved, and curved in straight, just as much as the motion of parallelism. The lines are not parallel, they continually approach one another, and yet never meet. The arm of the curve becomes more and more straight, without ever becoming entirely so. Just as in analytical geometry, the straight line is regarded as a curve of the first order with an infinitely small curvature. However large the x of the logarithmic curve may become, y can never equal 0. Straight and curved in the differential calculus are in the last resort put as equal. In the differential triangle, the hypotenuse of which forms the differential of the arc, in the tangent method, this hypotenuse can be regarded, quote, as a small, quite straight line, which is at the same time the element of the arc and that of the tangent, unquote. No matter whether the curve is regarded as composed of an infinite number of straight lines, or also, quote, whether one considers it as a strict curve, since the curvature at each point M is infinitely small, the last ratio of the element of the curve to that of the tangent is evidently a ratio of equality, unquote. Here, therefore, although the ratio continually approaches equality, but asymptotically in accordance with the nature of the curve, yet, since the contact is limited to a single point which has no length, it is finally assumed that equality of straight and curved has been reached. Boschot, Calcul différentiel et intégral, Paris, 4th French edition, 1, page 149. Footnote. In polar curves, the differential imaginary abscissae are even taken as parallel to the real abscissae and operations based on this, although both meet at the pole. Indeed, from it is deduced the similarity of two triangles, one of which has an angle precisely at the point of intersection of the two lines, the parallelism of which is the whole basis of the similarity. In parentheses, figure 17. Footnote. Polar curves. This is how Boschot terms the curves considered in the system of polar coordinates. Regarding figure 17, Engels has in mind this figure, which will be on the screen right now, and explanation to it on pages 148 to 51 of Boschot's treatise. This figure has the following form. BMK is the curve, MT is its tangent. P is the pole or origin of the coordinates. PZ is the polar axis. PM is the ordinate of the point M. Engels calls it real abscissa. Nowadays it is called the radius vector. PM is the ordinate of the point M lying infinitely close to M. Engels calls this radius vector the differential imaginary abscissa. MH, perpendicular to the tangent MT. TPH, perpendicular to the ordinate PM. M lowercase r, the curve describes by the radius PM. As MP lowercase m is an infinitesimal angle, PM and P lowercase m are considered parallel. The triangles M lowercase r lowercase m and TPM, as also the triangles M lowercase r lowercase m and MPH, are regarded as similar. End of footnote. When the mathematics of straight and curved lines has thus pretty well reached exhaustion, a new almost infinite field is opened up by the mathematics that conceives curved as straight, the differential triangle, and straight as curved, curve of the first order with infinitely small curvature. O metaphysics. Trigonometry. After synthetic geometry has exhausted the properties of a triangle regarded as such, and has nothing new to say, a more extensive horizon is opened up by a very simple, thoroughly dialectical procedure. The triangle is no longer considered in and for itself, but in connection with another figure, the circle. Every right-angled triangle can be regarded as belonging to a circle. If the hypotenuse equals radius, then the sides enclosing the right angle are sin and cos. If one of these sides equals radius, then the other equals tan, the hypotenuse equals sec. In this way, the sides and angles are given quite different, definite relationships, which, without this relation of the triangle to the circle, would be impossible to discover and use, and quite a new theory of the triangle arises, for surpassing the old and universally applicable, because every triangle can be resolved into two right-angled triangles. This development of trigonometry from synthetic geometry is a good example of dialectics, of the way in which it comprehends things in their interconnection instead of in isolation. Identity and difference. The dialectical relation is already seen in the differential calculus, where dx is infinitely small, but yet it is effective and does everything. Molecule and differential. Wiedemann, 3, page 636, puts finite and molecular distances as directly opposed to one another. On the prototypes of the mathematical infinite in the real world. Regarding pages 17 to 18, concordance of thought and being, the infinite in mathematics. Footnote. This note is one of the three larger notes which Engels put in the second folder for Dialectics of Nature. It was written originally as the first sketch of a commentary note to pages 17 to 18 of the first edition of Anti-Düring. The heading, On the Prototypes of the Mathematical Infinite in the Real World, was given by Engels in the list of contents of the second folder of Dialectics of Nature. The subheading, to pages 17 to 18, Concordance of Thought and Being, the Infinite in Mathematics, stands at the beginning of the note. End of footnote. The fact that our subjective thought and the objective world are subject to the same laws, and hence too, that in the final analysis they cannot contradict each other in their results, but must coincide, governs absolutely our whole theoretical thought. It is the unconscious and unconditional premise for theoretical thought. 18th century materialism, owing to its essentially metaphysical character, investigated this premise only as regards content. It restricted itself to the proof that the content of all thought and knowledge must derive from sensuous experience, and revived the principle nihil est in intellectu quod non ferit in sensu. Footnote. Nothing is in the mind which has not been in the senses. The fundamental tenet of sensualism. The content of this formula goes back to Aristotle. See his posterior analytics. End of footnote. It was modern idealistic, but at the same time dialectical philosophy, and especially Hegel, which for the first time investigated it also as regards form. In spite of all the innumerable arbitrary constructions and fantasies that we encounter here, in spite of the idealist, topsy-turvy form, the unity of thought and being, it is undeniable that this philosophy proved the analogy of the processes of thought to those of nature and history, and vice versa, and the validity of similar laws for all these processes in numerous cases and in the most diverse fields. On the other hand, modern natural science has extended the principle of the origin of all thought content from experience in a way that breaks down its old metaphysical limitation and formulation. By recognizing the inheritance of acquired characteristics, it extends the subject of experience from the individual to the genus. The single individual that must have experience is no longer necessary. Its individual experience can be replaced to a certain extent by the results of the experiences of a number of its ancestors. If, for instance, among us the mathematical axioms seem self-evident to every 8-year-old child, and in no need of proof from experience, this is solely the result of quote-unquote accumulated inheritance. It would be difficult to teach them by a proof to a Bushman or Australian Aborigines. In the present work, Anti-Düring, dialectics is conceived as the science of the most general laws of motion. This implies that its laws must be valid just as much for motion in nature and human history as for the motion of thought. Such a law can be recognized in two of these three spheres, indeed, even in all three, without the metaphysical Philistine being clearly aware that it is one and the same law that he has come to know. Let us take an example. Of all theoretical advances, there is surely none that ranks so high as a triumph of the human mind as the discovery of the infinitesimal calculus in the last half of the 17th century. If anywhere, it is here that we have a pure and exclusive feat of human intelligence. The mystery, which even today surrounds the magnitudes employed in the infinitesimal calculus, the differentials and infinites of various degrees, is the best proof that it is still imagined that what are dealt with here are pure, so-called, free creations and imaginations of the human mind, to which there is nothing corresponding in the objective world. Yet the contrary is the case. Nature offers prototypes for all these imaginary magnitudes. Our geometry takes as its starting point space relations, and our arithmetic and algebra numerical magnitudes, which correspond to our terrestrial conditions, which therefore correspond to the magnitude of bodies that mechanics term masses, masses such as occur on Earth and are moved by men. In comparison with these masses, the mass of the Earth seems infinitely large, and indeed terrestrial mechanics treats it as infinitely large. The radius of the Earth equals roughly infinite. This is the basic principle of all mechanics in the law of falling. But not merely the Earth, but the whole solar system and the distances occurring in the latter, in their turn appear infinitely small as soon as we have to deal with the distances reckoned in light years in the stellar system visible to us through the telescope. We have here, therefore, already an infinity, not only of the first but of the second degree, and we can leave it to the imagination of our readers to construct further infinities of a higher degree in infinite space, if they feel inclined to do so. According to the view prevailing in physics and chemistry today, however, the terrestrial masses, the bodies with which mechanics operates, consist of molecules, of smallest particles which cannot be further divided, without abolishing the physical and chemical identity of the body concerned. According to W. Thomson's calculations, the diameter of the smallest of these molecules cannot be smaller than a 50 millionth of a millimeter. Footnote. This figure is given in an article by William Thomson entitled The Size of Atoms, which was first published in the journal Nature, number 22 of March 31st, 1870, and afterwards reprinted as an appendix in the second edition of Treatise on Natural Philosophy by Thomson and Tate, Volume 1, Part 2, New Edition, Cambridge, 1883, pages 501 to 502. End of footnote. But even if we assume that the largest molecule itself attains a diameter of 25 millionth of a millimeter, it still remains an infinitesimally small magnitude compared with the smallest mass dealt with by mechanics, physics, or even chemistry. Nevertheless, it is endowed with all the properties peculiar to the mass in question. It can represent the mass physically and chemically, and does actually represent it in all chemical equations. In short, it has the same properties in relation to the corresponding mass as the mathematical differential has in relation to its variables. The only difference is that what seems mysterious and inexplicable to us in the case of the differential in the mathematical abstraction here seems a matter of course and as it were obvious. Nature operates with these differentials, the molecules, in exactly the same way and according to the same laws as mathematics does with its abstract differentials. Thus, for instance, the differential of x cubed equals 3x squared dx where 3x dx squared and dx cubed are neglected. If we put this in geometrical form, we have a cube with its sides of length x, the length being increased by the infinitely small amount dx. Let us suppose that this cube consists of a sublimated element, say sulfur, that the 3 of the surfaces around one corner are protected, the other 3 being free. Let us now expose this sulfur cube to an atmosphere of sulfur vapor and lower the temperature sufficiently. Sulfur will be deposited on the 3 free sides of the cube. We remain quite within the ordinary mode of procedure of physics and chemistry in supposing, in order to picture the process in its pure form, that in the first place a layer of the thickness of a single molecule is deposited on each of these 3 sides. The length x of the sides of the cube has increased by the diameter of a molecule dx. The content of the cube, x cubed, has increased by the difference between x cubed and x cubed plus 3x squared dx plus 3x dx squared plus dx cubed, where dx cubed, a single molecule, and 3x dx squared, 3 rows of length, x plus dx, consisting simply of linearly arranged molecules, can be neglected with the same justification as in mathematics. The result is the same. The increase in mass of the cube is 3x squared dx. Strictly speaking, dx cubed and 3x dx squared do not occur in the case of the sulfur cube, because 2 or 3 molecules cannot occupy the same space, and the cube's increase of bulk is therefore exactly 3x squared dx plus 3x dx plus dx. This is explained by the fact that in mathematics dx is a linear magnitude, while it is well known that such lines, without thickness or breadth, do not occur independently in nature. Hence also the mathematical abstractions have unrestricted validity only in pure mathematics. And since the latter neglects 3x dx squared plus dx cubed, it makes no difference. Similarly in evaporation, when the uppermost molecular layer in a glass of water evaporates, the height of the water layer, x, is decreased by dx, and the continual flight of one molecular layer after another is actually a continued differentiation. And when the hot vapor is once more condensed to water in a vessel by pressure and cooling, and one molecular layer is deposited on another, it is permissible to leave out of account secondary circumstances that make the process an impure one until the vessel is full. Then literally an integration has been performed, which differs from the mathematical one only in that the one is consciously carried out by the human brain, while the other is unconsciously carried out by nature. But it is not only in the transition from the liquid to the gaseous state and vice versa that processes occur which are completely analogous to those of the infinitesimal calculus. When mass motion as such is abolished by impact and becomes transformed into heat, molecular motion, what is it that happens but that the motion is differentiated? And when the movements of the molecules of steam in the cylinder of the steam engine become added together so that they lift the piston by a definite amount, so that they become transformed into mass motion, have they not been integrated? Chemistry dissociates molecules into atoms, magnitudes of lesser mass and spatial extension, but magnitudes of the same order, so that the two stand in definite, finite relations to one another. Hence, all the chemical equations which express the molecular composition of bodies are in their form differential equations. But in reality, they are already integrated owing to the atomic weights which figure in them. For chemistry calculates with differentials, the mutual relation of the magnitudes of which is known. Atoms, however, are in no wise regarded as simple, or in general as the smallest known particles of matter. Apart from chemistry itself, which is more and more inclining to the view that atoms are compound, the majority of physicists assert that the universal ether, which transmits light and heat radiations, likewise consists of discrete particles, which, however, are so small that they have the same relation to chemical atoms and physical molecules as these have to mechanical masses, that is to say, as d squared x to dx. Here, therefore, in the now usual notion of the constitution of matter, we have likewise a differential of the second degree, and there is no reason at all why anyone to whom it would give satisfaction should not imagine that analogies of d cubed x, d to the power of 4x, etc. also occur in nature. Hence, whatever view one may hold of the constitution of matter, this much is certain, that it is divided up into a series of big, well-defined groups of a relatively different mass character, in such a way that the members of each separate group stand to one another in a definite finite mass ratios, in contrast to which those of the next group stand to them in the ratio of the infinitely large or infinitely small in the mathematical sense. The visible system of stars, the solar system, terrestrial masses, molecules and atoms, and finally ether particles, form each of them such a group. It does not alter the case that intermediate links can be found between the separate groups. Thus, between the masses of the solar system and terrestrial masses come the asteroids, some of which have a diameter no greater than, for example, that of the younger branch of the Reuss Principality, meteorites, etc. Footnote: Reuss Principality, one of the dwarf states forming part of the German Empire since 1871. End of footnote. Thus, in the organic world, the cell stands between terrestrial masses and molecules. These intermediate links prove only that there are no leaps in nature, precisely because nature is composed entirely of leaps. Insofar as mathematics calculates with real magnitudes, it also employs this mode of outlook without hesitation. For terrestrial mechanics, the mass of the Earth is regarded as infinitely large, just as for astronomy, terrestrial masses and the meteorites corresponding to them are regarded as infinitely small, and just as the distances and masses of the planets of the solar system dwindle to nothing as soon as astronomy investigates the constitution of our solar system, extending beyond the nearest fixed stars. As soon, however, as the mathematicians withdraw into their impregnable fortress of abstraction, so-called pure mathematics, all these analogies are forgotten. Infinity becomes something totally mysterious, and the manner in which operations are carried out with it in analysis appears as something absolutely incomprehensible, contradicting all experience and all reason. The stupidities and absurdities by which mathematicians have rather excused than explained their mode of procedure, which remarkably enough always leads to correct results, exceed the worst apparent and real fantasies, for example, of the Hegelian philosophy of nature, about which mathematicians and natural scientists can never adequately express their horror. What they charge Hegel with doing, viz., pushing abstractions to the extreme limit, they do themselves on a far greater scale. They forget that the whole of so-called pure mathematics is concerned with abstractions, that all its magnitudes, strictly speaking, are imaginary, and that all abstractions, when pushed to extremes, are transformed into nonsense or into their opposite. Mathematical infinity is taken from reality, although unconsciously, and therefore can only be explained from reality and not from itself, from mathematical abstraction. And as we have seen, if we investigate reality in this regard, we come also upon the real relations from which the mathematical relation of infinity is taken, and even the natural analogies of the mathematical way in which this relation operates, and thereby the matter is explained. Haeckel's bad reproduction of the identity of thinking and being, but also the contradiction between continuous and discrete matter. See Hegel. Footnote. Here Engels possibly has in mind Haeckel's psychophysical monism and his view on the structure of matter. In the perigenesis of the plastidule, which Engels quoted in his second note to Anti-Düring, Haeckel affirms, for example, that the elementary quote-unquote soul is inherent not only in so-called plastidules or protoplasm molecules, but also in atoms, and that all atoms are quote-unquote animate and possess quote-unquote sensation and volition. In the same book, Haeckel describes atoms as something absolutely discrete, absolutely indivisible, and absolutely inalterable, while along with discrete atoms, he recognizes the existence of ether as something absolutely continuous. Opus Citato, Berlin, 1876, pages 38 to 40. Engels mentions in his note the divisibility of matter, how Hegel deals with the contradiction of continuity and discreteness of matter. End of footnote. The differential calculus for the first time makes it possible for natural science to represent mathematically processes and not only states, motion. Application of mathematics. In the mechanics of solid bodies it is absolute, in that of gases approximate, in that of fluids already more difficult, in physics more tentative and relative, in chemistry simple equations of the first order and of the simplest nature, in biology equals 0. Mechanics and astronomy. An example of the necessity of dialectical thought and of the non-rigid categories and relations in nature, the law of falling, which already in the case of a period of fall of some minutes becomes incorrect, since then the radius of the earth can no longer without error be put as infinite, and the attraction of the earth increases instead of remaining constant as Galileo's law of falling assumes. Nevertheless, this law is still continually thought, but the reservation omitted. Newtonian attraction and centrifugal force, an example of metaphysical thinking. The problem not solved, but only posed, and this preached as the solution. Ditto Clausius's dissipation of heat. Footnote. Engels is referring to Clausius's lecture on the second law of the mechanical theory of heat, delivered in Frankfurt on Main, September 23, 1867, at the 41st Congress of German Natural Scientists and Physicians, and published in book form in Braunschweig the same year. End of footnote. Newtonian gravitation. The best that can be said of it is that it does not explain but pictures the present state of planetary motion. The motion is given, ditto the force of attraction of the sun. With these data, how is the motion to be explained? By the parallelogram of forces, by a tangential force, which now becomes a necessary postulate that we must accept. That is to say, assuming the eternal character of the existing state, we need a first impulse, God. But neither is the existing planetary state eternal, nor is the motion originally compound, but simple rotation, and the parallelogram of forces applied here is wrong, because it did not merely make evident the unknown magnitude, the x, but had still to be found, that is to say, in so far as Newton claimed, not merely to put the question but to solve it. Newton's parallelogram of forces in the solar system is true at best for the moment when the annular bodies separate, because then the rotational motion comes into contradiction with itself, appearing on the one hand as attraction and on the other hand as tangential force. As soon as the separation is complete, however, the motion is again a unity. That this separation must occur is a proof of the dialectical process. Laplace's theory presupposes only matter in motion, rotation necessary for all bodies suspended in universal space. Medler, The Fixed Stars. Footnote. This and the two following notes consist of extracts from the following books: J. H. Medler, Der Wunderbau des Weltalls oder Populär Astronomie, 5th German edition, Berlin, 1861, sections 9 and 10. A. Secchi, Die Sonne, Braunschweig, 1872, part 3. Engels made use of these extracts in 1876 in the second part of Introduction to Dialectics of Nature. End of footnote. Halley. At the beginning of the 18th century, from the difference between the data of Hipparchus and Flamsteed on 3 stars, first arrived at the idea of proper motion, page 410. Flamsteed's British Catalogue, the first fairly accurate and comprehensive one, page 420. Then, circa 1750, Bradley, Maskelyne, and Lalande. Crazy theory of the range of light rays in the case of enormous bodies, and Medler's calculation based on this, as crazy as anything in Hegel's Philosophy of Nature, pages 424 to 25. The strongest apparent proper motion of a star equals 701 inches a century, equals 11 feet 41 inches, equals 1/3 of the sun's diameter, smallest average of 921 telescopic stars, 8.65 inches, some of them 4 inches. Milky Way is a series of rings, all with a common center of gravity, page 434. The Pleiades group, and in it, Alcyon, Eta Tauri, the center of motion for our island universe, quote, as far as the most remote regions of the Milky Way, unquote, page 448. Periods of revolution within the Pleiades group, on the average circa 2 million years, page 449. About the Pleiades are annular groups alternately poor in stars and rich in stars. Secchi contests the possibility of fixing a center at the present time. According to Bessel, Sirius and Procyon describe an orbit about a dark body, as well as the general motion, 450. Eclipse of Algol, every 3 days, duration 8 hours, confirmed by spectral analysis, Secchi, page 786. In the region of the Milky Way, but deep within it, a dense ring of stars of magnitudes 7 to 11. A long way outside this ring are the concentric Milky Way rings, of which we see 2. In the Milky Way, according to Herschel, circa 18 million stars, visible through his telescope, those lying within the ring being circa 2 million or more, hence over 20 million in all. In addition, there is always a non-resolvable glow in the Milky Way, even behind the resolved stars. Hence, perhaps still further rings concealed owing to perspective. Pages 451 to 52. Alcyone, distant from the Sun 573 light-years. Diameter of the Milky Way ring of separate visible stars, at least 8,000 light-years. Pages 462 to 63. The mass of the bodies moving within the Sun. Alcyone, radius of 573 light-years, is calculated at 118 million sun masses. Page 462, not at all in agreement with the at most 2 million stars moving therein. Dark bodies? At any rate, something wrong. A proof of how imperfect our observational bases still are. For the outermost ring of the Milky Way, Medler assumes a distance of thousands, perhaps of hundreds of thousands of light-years. Page 464. A beautiful argument against the so-called absorption of light. Quote, at any rate, there does exist a distance from which no further light can reach us, but the reason is quite a different one. The velocity of light is finite, From the beginning of creation to our day, a finite time has elapsed, and therefore we can only become aware of the heavenly bodies up to the distance which light has traveled in this finite time." Unquote. Page 466. That light, decreasing in intensity according to the square of the distance, must reach a point where it is no longer visible to our eyes, however much the latter may be strengthened and equipped, is quite obvious, and suffices for refuting the view of Olbers that only light absorption is capable of explaining the darkness of the sky, that nevertheless is filled in all directions with shining stars to an infinite distance. That is not to say that there does not exist a distance at which the ether allows no further light to penetrate. Nebulae. Of all forms, strictly circular, elliptical, or irregular and jagged, all degrees of resolvability merging into total non-resolvability, where only a thickening towards the center can be distinguished. In some of the resolvable nebulae, up to 10,000 stars are perceptible, the middle mostly denser, very rarely a central star, of greater brilliance. Ross's giant telescope has, however, resolved many of them. Herschel 1 enumerates 197 star aggregations and 2,300 nebulae, to which must be added those catalogued by Herschel 2 in the southern heavens. The irregular ones must be distant island universes, since masses of vapor can only exist in equilibrium, in globular or ellipsoidal form. Most of them, however, are only just visible even through the most powerful telescopes. At any rate, the circular ones can be vapor masses. There are 78 of them among the above 2,500. Herschel assumes 2 million. Mädler, on the assumption of a true diameter equal to 8,000 light-years, 30 million light-years distant from us. Since the distance of each astronomical system of bodies from the next one amounts to at least 100-fold the diameter of the system, the distance of our island universe from the next one would be at least 50 times 8,000 light-years, equals 400,000 light-years. In which case, with the several thousand of nebulae, we get far beyond Herschel 1's 2 million. Mädler, Locus Citato, pages 485 to 492. Secchi. Quote, "The resolvable nebulae give a continuous and an ordinary stellar spectrum. The nebulae proper, however, quote, in part give a continuous spectrum like the nebula in Andromeda, but mostly they give a spectrum consisting of one or only very few bright lines, like the nebulae in Orion, in Sagittarius, in Lyra, and the majority of those that are known by the name of planetary circular nebulae." Unquote. Page 787. The nebula in Andromeda, according to Mädler, page 495, is unresolvable. The nebula in Orion is irregular, flocculent, and, as it were, puts out arms. Page 495. Those of Lyra are ring-shaped, only slightly elliptical. Page 498. Huggins found in the spectrum of Herschel's nebula number 4374 3 bright lines. Quote, "From this it follows immediately that this nebula does not consist of an aggregate of separate stars, but is a true nebula, a glowing substance in the gaseous state." Unquote. Page 787. The lines belong to nitrogen 1 and hydrogen 1. The third is unknown. Similarly for the nebula in Orion. Even nebulae that contains gleaming points, Hydra, Sagittarius, have these bright lines, so that star masses in course of aggregation are still not solid or liquid. Page 789. The nebula in Lyra has only a nitrogen line. Page 789. The densest place of the nebula in Orion is p, its whole extension, 4 feet. Pages 790 to 91. Secchi, Sirius. Quote, 11 years later, subsequent to Bessel's calculation, Medler, page 450, not only was the satellite of Sirius discovered in the form of a self-luminous star of the 6th magnitude, but it was also shown that its orbit coincides with that calculated by Bessel. Since then, the orbit also for Procyon and its companion has been determined by Auvers, although the satellite itself has not yet been seen. Unquote. Page 793. Secchi, Fixed Stars. Quote, since the fixed stars, with the exception of 2 or 3, have no perceptible parallax, they are at least, unquote, some 30 light-years distant from us. Page 799. According to Secchi, the stars of the 16th magnitude, still distinguishable in Herschel's big telescope, are 7,560 light-years distant. Those distinguishable in Ross's telescope are at least 20,900 light-years distant. Page 802. Secchi, page 810, himself asks, when the sun and the whole system are extinct, quote, are there forces in nature which can reconvert the dead system into its original state of glowing nebula and reawaken it to new life? We do not know. Unquote. Secchi and the Pope. Descartes discovered that ebb and flow of tides are caused by the attraction of the moon. He also discovered simultaneously with Snell the basic law of the refraction of light. Note in the margin, contested by Wolff, page 325. End of note in the margin, and this in a form peculiar to himself and different from that of Snell. Footnote on Wolff. Engels is referring to Rudolf Wolff's book Geschichte der Astronomie, München, 1877. On page 325 of this book, Wolff asserts that the law of the refraction of light was discovered not by Descartes but by Snell, who formulated it in his unpublished works, from which Descartes subsequently after Snell's death took it. End of footnote. Meyer, Mechanische Theorie der Wärme, page 328. Kant has already stated that the ebb and flow of tides exert a retarding pressure on the rotating earth. Adams' calculation that the duration of the sidereal day is now increasing by 1/100th of a second in 1,000 years. Footnote. Engels is referring to Julius Robert Meyer's book Die Mechanik der Wärme in Gesammelten Schriften, 2nd edition, Stuttgart, 1874, pages 328-330. End of footnote. Physics. Impact and friction. Mechanics regards the effect of impact as taking place in a pure form, but in reality things are different. On every impact, part of the mechanical motion is transformed into heat, and friction is nothing more than a form of impact that continually converts mechanical motion into heat, in parentheses, fire by friction, known from primeval times. The consumption of kinetic energy, as such, in the field of dynamics, is always a twofold nature and has a twofold result. 1. The kinetic work done, production of a corresponding quantity of potential energy, which, however, is always less than the applied kinetic energy. 2. Overcoming, besides gravity, frictional and other resistances that convert the remainder of the used-up kinetic energy into heat. Likewise, on reconversion, according to the way this takes place, a part of the loss through friction, etc., is dissipated as heat, and that is all very ancient. The first, naive outlook is as a rule more correct than the later metaphysical one. Thus already Bacon, and after him Boyle, Newton and almost all the Englishmen said heat is motion. Boyle even said molecular motion. Footnote: Francis Bacon, Novum Organum, The New Organon, Book 11, Aphorism 20, published in London in 1620. End of footnote. It was only in the 18th century that the caloric theory arose in France and became more or less accepted on the continent. Conversion of energy. The quantitative consistency of motion was already enunciated by Descartes, and indeed almost in the same words as now by in parentheses, Clausius, Robert Meyer, ? On the other hand, the transformation of the form of motion was only discovered in 1842, and this, not the law of quantitative constancy, is what is new. Force and conservation of force. The passages of J.R. Meyer in his 2 first papers to be cited against Helmholtz. Force. Hegel, Geschichte der Philosophie, 1, page 208, says, quote, "It is better to say that a magnet has a soul, as Thales expressed it, than that it has an attracting force. Force is a kind of property that, separable from matter, is put forward as a predicate, while soul, on the other hand, is this movement itself, identical with the nature of matter." Unquote. Hegel's conception of force and its manifestation of cause and effect as identical is proved in the change of form of matter, where the equivalence is proved mathematically. This had already been recognized in measurement. Force is measured by its manifestation, cause by effect. Force. If any kind of motion is transferred from one body to another, then one can regard the motion, insofar as it transfers itself, that is active, as the cause of motion, insofar as the latter becomes transferred, that is passive, and then this cause, the active motion, appears as force, and the passive as its manifestation. From the law of the indestructibility of motion, it follows automatically that the force is exactly as great as its manifestation, since indeed it is the same motion in both cases. Motion that transfers itself, however, is more or less quantitatively determinable, because it appears in 2 bodies, of which one can serve as a unit of measurement in order to measure the motion of the other. The measurability of motion gives the category force its value, otherwise it has none. Hence, the more this is the case, the more are the categories of force and its manifestation usable in research. Hence, this is so especially in mechanics, where one resolves the forces still further, regarding them as compound, and thereby arriving at new results, although one should not forget that this is merely a mental operation. By applying the analogy of forces that are really compound, as expressed in the parallelogram of forces, to forces that are really simple, the latter still do not thereby really become compound. Similarly in statics. Then again, in the transformation of other forms of motion into mechanical motion, heat, electricity, magnetism in the attraction of iron, where the original motion can be measured by the mechanical effect produced. But here, where various forms of motion are considered simultaneously, the limitation of the category, or abbreviation, force, already stands revealed. No regular physicist any longer terms electricity, magnetism, or heat mere forces, any more than substances or imponderabilia. When we know into how much mechanical motion a definite quantity of heat motion is converted, we still do not know anything of the nature of heat, however much the examination of these transformations may be necessary for investigating this nature of heat. To conceive heat as a form of motion is the latest advance of physics, and by so doing the category of forces is sublated in it. In certain connections, those of transition, they can appear as forces and so be measured. Thus heat is measured by the expansion of a body on warming. If heat did not pass here from one body to the other, the measuring rod, that is, if the heat of the body acting as a measuring rod did not alter, there could be no talk of measurement, of a change of magnitude. One says simply, heat expands a body, whereas to say, heat has the force to expand a body would be a mere tautology, and to say, heat is the force which expands bodies would not be correct, since 1. Expansion, for example in gases, is produced also by other means, and 2. Heat is not exhaustively characterized in this way. Some chemists speak also of chemical force as the force that makes and maintains compounds. Here, however, there is no real transference, but a combination of the motion of various bodies into a single whole, and so quote-unquote force here reaches its limit. It is, however, still measurable by the heat production, but so far without much result. Here it becomes a phrase, as everywhere, where instead of investigating the uninvestigated forms of motion, one invents a so-called force for their explanation, as for instance explaining the floating of wood in water by a buoyancy force, the refraction of light by a refractive force, etc., in which case as many forces are obtained as there are unexplained phenomena, the external phenomenon being indeed merely translated into an internal phrase. Footnote. Compare Hegel's remark that force, quote, has no other content than the phenomena itself, unquote, and that this content expresses itself only, quote, in the form of into reflected determination or force, unquote, the result being a quote-unquote empty tautology. Hegel, Science of Logic, Book 2, Section 1, Chapter 3, Observation on the Formal Method of Explanation from Tautological Grounds. End of footnote. Attraction and repulsion are easier to excuse. Here a number of phenomena inexplicable to the physicist are embraced under a common name, which gives an inkling of an inner connection. Finally, in organic nature, the category of force is completely inadequate and yet continually applied. True, it is possible to characterize the action of the muscles in accordance with its mechanical effect as muscular force, and also to measure it. One can even conceive of other measurable functions as forces, for example the digestive capacity of various stomachs, but one quickly arrives ad absurdum, for example nervous force, and in any case one can speak here of forces only in a very restricted and figurative sense, the ordinary phrase to regain one's forces. This misuse, however, has led to speaking of a vital force. If by this is meant that the form of motion in the organic body is different from the mechanical, physical, or chemical form, and contains them all sublated in itself, then it is a very lax manner of expression, and especially so because the force, presupposing transference of motion, appears here as something pumped into the organism from outside, not as inherent in it and inseparable from it, and therefore this vital force has been the last refuge of all supernaturalists. The defect, 1. Force usually treated as having independent existence. Hegel, Naturphilosophie, page 79. Footnote. G.W.F. Hegel, Philosophy of Nature, section 266, observation. End of footnote. 2. Latent, dormant force. This to be explained from the relation of motion and rest, inertia, equilibrium, where also arousing of forces to be dealt with. Force, see above. The transference of motion takes place, of course, only in the presence of all the various conditions, which are often multiple and complex, especially in machines, the steam engine, the shotgun with lock, trigger, percussion cap, and gunpowder. If one of them is missing, then the transference does not take place until this condition is supplied. In that case, one can imagine this as if the force must be first aroused by the introduction of this last condition, as if it lay latent in a body, the so-called carrier of force, in parentheses gunpowder, charcoal, whereas in reality not only this body, but all the other conditions must be present in order to evoke precisely this special transference. The notion of force comes to us quite automatically in that we possess in our own body means for transferring motion, which, within certain limits, can be brought into action by our will, especially the muscles of the arms, through which we produce mechanical change of place and motion of other bodies, lifting, carrying, throwing, hitting, etc., resulting in definite useful effects. The motion is here apparently produced, not transferred, and this gives rise to the notion of force in general, producing motion. That muscular force is also merely transference has only now been proved physiologically. Force. The negative side also has to be analyzed. The resistance which is opposed to the transference of motion. Radiation of heat into universal space. All the hypotheses cited by Lavrov of the renewal of extinct heavenly bodies, page 109, involve loss of motion. Footnote. Engels is referring to Lavrov's book, Attempt at a History of Thought, Volume 1, published anonymously in St. Petersburg in 1875. On page 109 of this book, in the chapter The Cosmic Basis of the History of Thought, Lavrov writes, quote, "Dead suns with their dead systems of planets and satellites continue their motion in space as long as they do not fall into a new nebula in process of formation. Then the remains of the dead world become material for hastening the process of formation of the new world." Unquote. In a footnote, Lavrov quotes the opinion of Zollner that the state of torpor of extinct heavenly bodies, quote, "can be ended only by external influences, for example by the heat evolved on collision with some other body." Unquote. End of footnote. The heat once radiated, that is, the infinitely greater part of the original motion, is and remains lost. Helmholtz says up to now 453 out of 454. Hence one finally arrives after all at the exhaustion and cessation of motion. The question is only finally solved when it has been shown how the heat radiated into space becomes utilizable again. The theory of the transformation of motion puts this question categorically, and it cannot be got over by postponing the answer or by evasion. That, however, with the posing of the question, the conditions for its solution are simultaneously given, c'est toute la chose. The transformation of motion and its indestructibility were first discovered hardly 30 years ago, and it is only quite recently that the consequences have been further elaborated and worked out. The question as to what becomes of the apparently lost heat has, as it were, only been nettement posé since 1867, in parentheses Clausius. No wonder that it has not yet been solved. It may still be a long time before we will arrive at a solution with our small means, but it will be solved just as surely as it is certain that there are no miracles in nature and that the original heat of the nebular ball is not communicated to it miraculously from outside the universe. The general assertion that the total amount, die Masse, of motion is infinite and hence inexhaustible is of equally little assistance in overcoming the difficulties of each individual case. It too does not suffice for the revival of extinct universes, except in the cases provided for in the above hypotheses, which are always bound up with loss of force and are therefore only temporary causes. The cycle has not been traced and will not be until the possibility of the reutilization of the radiated heat is discovered. Clausius, if correct, proves that the universe has been created, ergo that matter is creatable, ergo that it is destructible, ergo that also force or motion is creatable and destructible, ergo that the whole theory of the so-called conservation of force is nonsense, ergo that all his conclusions from it are also nonsense. Clausius's second law, etc., however it may be formulated, shows energy as lost, qualitatively if not quantitatively. Entropy cannot be destroyed by natural means, but it can certainly be created. The world clock has to be wound up, then it goes on running until it arrives at a state of equilibrium from which only a miracle can set it going again. The energy expended in winding has disappeared, at least qualitatively, and can only be restored by an impulse from outside. Hence an impulse from outside was necessary at the beginning also, hence the quantity of motion or energy existing in the universe was not always the same, hence energy must have been created, that is, it must be creatable, and therefore destructible, ad absurdum. Conclusion from Thomson, Clausius, Loschmidt. The reversion consists in repulsion repelling itself, and thereby returning out of the medium into extinct heavenly bodies. But just therein lies also the proof that repulsion is the really active aspect of motion, and attraction the passive aspect. In the motion of gases, in the process of evaporation, the motion of masses passes directly into molecular motion, hence therefore the transition has to be made. States of aggregation, nodal points where quantitative change is transformed into qualitative. Cohesion, already negative in gases, transformation of attraction into repulsion, the latter only real in gas and ether, in parentheses question mark. At absolute zero temperature, no gas is possible, all motion of the molecules ceases. The slightest pressure, and hence their own attraction, forces them together. Consequently, a permanent gas is an impossibility. mv squared has been proved also for gas molecules by the kinetic theory of gases. Hence, there is the same law for molecular motion as for the motion of masses. The difference between the two is here abolished. The kinetic theory has to show how molecules that strive upwards can at the same time exert a downward pressure, and assuming the atmosphere as more or less permanent in relation to universal space, how in spite of gravity they can move to a distance from the center of the earth, but nevertheless at a certain distance, although the force of gravity has decreased according to the square of the distance, are yet compelled by this force to come to a stop or to return. The kinetic theory of gases, quote, in a perfect gas, the molecules are already so far distant from one another that their mutual interaction can be neglected, unquote. Clausius, page 6. What fills up the spaces between them? Ditto, ether. Footnote. Engels is evidently referring to page 16 of the pamphlet, where Clausius incidentally mentions the ether as existing outside the heavenly bodies. Here again, on page 6, it is a question of the same ether, though not outside bodies, but in the interstices between the most minute constituent particles of the bodies. End of footnote. Hence here the postulate of a matter that is not articulated into molecular or atomic cells. The character of mutual opposites belonging to theoretical development. From the horror vacui, the transition was made at once to absolutely empty universal space, only afterwards the ether. Footnote. Horror vacui, abhorrence of a vacuum, the view dating from Aristotle that, quote-unquote, nature abhors the void, that is, does not allow a vacuum to form, prevailed in natural science till the mid-17th century. This so-called abhorrence was given, among other things, as the reason why the water rises in a piston. In 1643, Torricelli discovered atmospheric pressure and thereby refuted the Aristotelian notion of the impossibility of a vacuum. End of footnote. Ether. If the ether offers resistance at all, it must also offer resistance to light, and so at a certain distance be impenetrable to light. That, however, ether propagates light, being its medium, necessarily involves that it should also offer resistance to light. Otherwise, light could not set it in vibration. This the solution of the controversial questions raised by Medler and mentioned by Lavrov. Footnote. Engels is referring to Lavrov's book, Attempt at a History of Thought. In the chapter, The Cosmic Basis of the History of Thought, Lavrov mentions the view of various scientists, Albers v. Struve, on the extinction of light coming from very great distances. Pages 103 to 4. End of footnote. Light and darkness are certainly the most conspicuous and definite opposites in nature. They have always served as a rhetorical phrase for religion and philosophy from the time of the Fourth Gospel to the Lumieres of the 18th century. Footnote. Fourth Gospel is the Gospel according to John. End of footnote. Fick, page 9, quote, "The law long ago rigidly demonstrated in physics that the form of motion called radiant heat is identical in all essential respects with the form of motion that we call light." Unquote. Footnote. Fick, The Interaction of Natural Forces, Würzburg, 1869. End of footnote. Clerk Maxwell, page 14, quote, "These rays of radiant heat have all the physical properties of rays of light and are capable of reflection, etc. Some of the heat rays are identical with the rays of light, while other kinds of heat rays make no impression upon our eyes." Unquote. Footnote. Maxwell, The Theory of Heat, 4th edition, London, 1875, pages 87, 185. End of footnote. Hence, there exist dark light rays, and the famous opposition between light and darkness disappears from natural science as an absolute opposition. Incidentally, the deepest darkness and the brightest, most glaring light have the same effect of dazzling our eyes, and in this way are for us identical. The fact is, the sun's rays have different effects according to the length of the vibration. Those with the greatest wavelength communicate heat, those with medium wavelength, light, and those with the shortest wavelength, chemical action. Secchi, page 632 et seq. The maxima of the three actions being closely approximated, the inner minima of the outer groups of rays, as regards their action, coming within the light ray group. Footnote. Engels is referring to the diagram on page 632 of Secchi's book, showing the relationship between the length of the wave and the intensity of the thermal, luminar, and chemical actions of the sun rays, the main portion of which is reproduced below. The picture should be on the screen right now. The curve BDN represents the intensity of heat radiation from the longest wave heat rays at point B to the shortest wave rays at point N. The curve AMH represents the intensity of light radiation from the longest wave rays at point A to the shortest wave rays at point H. The curve IKL represents the intensity of chemical rays from the longest wave rays at point I to the shortest wave rays at point L. In all three cases, the intensity of the rays is shown by the distance of the point on the curve from the line PW. End of footnote. What is light and what is non-light depends on the structure of the eye. Night animals may be able to see even a part, not of the heat rays but of the chemical rays, since their eyes are adapted for shorter wavelengths than ours. The difficulty appears if one assumes instead of three kinds, only single kind of ray, and scientifically we know only one, and everything else is a premature conclusion, which has different, but within narrow limits compatible effects according to the wavelength. Hegel constructs the theory of light and color out of pure thought, and in so doing falls into the grossest empiricism of home-bred Philistine experience, although with a certain justification, since this point had not been cleared up at that time. For example, where he adduces against Newton the mixtures of colors used by painters. Page 314. Footnote. Engels is referring to Hegel's Philosophy of Nature, Berlin edition, 1842, section 320, addendum. End of footnote. Electricity. In regard to Thomson's cock and bull stories, compare Hegel, pages 346 to 47, where there is exactly the same thing. On the other hand, Hegel already conceives frictional electricity quite clearly as tension, in contrast to the fluid theory and the electrical matter theory. Page 347. When Coulomb says that, quote, particles of electricity repel each other inversely as the square of their distance, unquote, Thomson calmly takes this as proved. Page 358. Footnote. Here and further on, Engels quotes from Thomson's book An Outline of the Sciences of Heat and Electricity, 2nd edition, London, 1840. Engels made use of these quotations in the chapter Electricity. End of footnote. Ditto, page 366. The hypothesis that electricity consists of two fluids, positive and negative, whose particles repel each other. It is said, page 360, that electricity in a charged body is retained merely by the pressure of the atmosphere. Faraday put the seat of electricity in the opposed poles of the atoms, or molecules, there is still confusion about it, and thus for the first time expressed the idea that electricity is not a fluid but a form of motion, a so-called force. Page 378. What old Thomson cannot get into his head at all is that it is precisely the spark that is of a material nature. Already in 1822, Faraday had discovered that the momentary induced current, the first as well as the second reversed current, quote, participates more of the current produced by the discharge of the leaden jar than that produced by the voltaic battery, unquote. Herein lay the whole secret. Page 385. The spark has been the subject of all sorts of cock and bull stories, which are now known to be special cases or illusions. The spark from a positive body is said to be a quote-unquote pencil of rays, brush or cone, the point of which is the point of discharge. The negative spark, on the other hand, is said to be a so-called star. Page 396. A spark, a short spark, is said to be always white, a long one usually reddish or purplish. Wonderful nonsense of Faraday on the spark, page 400. The spark drawn from the prime conductor of an electric machine by a metal sphere is said to be white, by the hand purple, by aqueous moisture red, page 405. The spark, that is light, is said to be, quote, not inherent in electricity, but merely the result of the compression of the air. The air is violently and suddenly compressed when an electric spark passes through it, unquote, is proved by the experiment of Kinnersley in Philadelphia, according to which the spark produces, quote, a sudden rarefaction of the air in the tube, unquote, and drives the water into the tube. Page 407. In Germany 30 years ago, Winterl and others believed that the spark, or electric light, was, quote, of the same nature with fire, unquote, and arises by the union of two electricities, against which Thomson seriously proves that the place where the two electricities unite is precisely that where the light is least, and that it is 2/3 from the positive and 1/3 from the negative end. Pages 409 to 10. That fire is still here something quite mythical is obvious. With the same seriousness, Thomson quotes the experiments of Desains, according to which, with a rising barometer and falling temperature, glass, amber, silk, etc., become negatively electrified on being plunged into mercury, but positively electrified if the barometer is falling and the temperature rising, and in summer always become positive in impure and always negative in pure mercury. That in summer gold and various other metals become positive on warming and negative on cooling, the reverse being the case in winter, that they are, quote-unquote, highly electric, with a high barometer and northerly wind, positive if the temperature is rising, negative if falling, etc. Page 416. How matters stood in regard to heat. Quote, in order to produce thermoelectric effects, it is not necessary to apply heat. Anything which alters the temperature in one part of the chain occasions a deviation in the declination of the magnet. Unquote. For instance, the cooling of a metal by ice or evaporation of ether. Page 419. The electrochemical theory, page 438, is accepted as, quote, at least exceedingly ingenious and plausible. Unquote. Fabroni and Wollaston had already long ago, and Faraday recently, asserted that voltaic electricity is the simple consequence of chemical processes, and Faraday had given the correct explanation of the shifting of atoms taking place in the liquid, and established that the quantity of electricity is to be measured by the quantity of the electrolytic product. With the help of Faraday, Thomson arrives at the law, quote, that every atom must be naturally surrounded by the same quantity of electricity, so that in this respect heat and electricity resemble each other. Unquote. Page 454. Static and dynamic electricity. Static or frictional electricity is the putting into a state of tension of the electricity already existing in nature in the form of electricity, but in an equilibrated, neutral state. Hence the removal of this tension, if and insofar as the electricity during propagation can be conducted, also occurs at one stroke, by a spark, which re-establishes the neutral state. Dynamic or voltaic electricity, on the other hand, is electricity produced by the conversion of chemical motion into electricity. Under certain definite conditions, it is produced by the solution of zinc, copper, etc. Here the tension is not acute, but chronic. At every moment, new positive and negative electricity is produced from some other form of motion, and not already existing negative and positive electricity separated into positive and negative. The process is a continuous one, and therefore too its result, electricity, does not take the form of instantaneous tension and discharge, but of a continuous current which can be reconverted at the poles into the chemical motion from which it arose, a process that is termed electrolysis. In this process, as well as in the production of electricity by chemical combination, in which electricity is liberated instead of heat, and in fact as much electricity as under other circumstances heat is set free, Guthrie, page 210, the current can be traced in the liquid exchange of atoms into adjacent molecules. This is the current. Footnote. Here and in the following note, Engels is referring to the book of the British physicist Frederick Guthrie, Magnetism and Electricity, London and Glasgow, 1876. On page 210, Guthrie writes, quote, the strength of the current is proportional to the amount of zinc dissolved in the battery that is oxidized, and is proportional to the heat which the oxidation of that zinc would liberate. Unquote. This electricity, being of the nature of a current, for that very reason cannot be directly converted into static electricity. By means of induction, however, neutral electricity already existing as such can be deneutralized. In the nature of things, the induced electricity has to follow that which induces it, and therefore must likewise be of a flowing character. On the other hand, this obviously gives the possibility of condensing the current and of converting it into static electricity, or rather into a higher form that combines the property of a current with that of tension. This is solved by Ruhmkorff's machine. It provides an inductional electricity which achieves this result. A pretty example of the dialectics of nature is the way in which, according to present-day theory, the repulsion of like magnetic poles is explained by the attraction of like electronic currents. Guthrie, page 264. Electrochemistry. In describing the effect of the electric spark in chemical decomposition and synthesis, Wiedemann declares that this is more the concern of chemistry. Footnote. See Wiedemann, Die Lehre von Galvanismus und Elektromagnetismus, 3, Braunschweig, 1874, page 418. End of footnote. In the same case, the chemists declare that it is rather a matter which concerns physics. Thus, at the point of contact of molecular and atomic science, both declare themselves incompetent, while it is precisely at this point that the greatest results are to be expected. Friction and impact produce internal motion of the bodies concerned, molecular motion differentiated as warmth, electricity, etc., according to circumstances. This motion, however, is only temporary. Cessante causa cessat effectus. At a definite stage, they all become transformed into a permanent molecular change, a chemical change. Chemistry. The motion of an actual chemically uniform matter, ancient as it is, fully corresponds to the childish view, widely held even up to Lavoisier, that the chemical affinity of two bodies depends on each one containing a common third body. Kopp, Entwicklung, page 105. Footnote. H. Kopp, Die Entwicklungen der Chemie in der neueren Zeit, München, 1871, page 105. End of footnote. How old, convenient methods, adapted to previously customary practice, become transferred to other branches and there are a hindrance. In chemistry, the calculation of the composition of compounds in percentages, which was the most suitable method of all for making it impossible to discover the laws of constant proportion and multiple proportion in combination, and indeed did make them undiscoverable for long enough. The new epoch begins in chemistry with atomistics. Hence Dalton, not Lavoisier, is the father of modern chemistry. And correspondingly in physics with the molecular theory, in a different form but essentially representing only the other side of this process, with the discovery of the transformation of the forms of motion. The new atomistics is distinguished from all previous to it by the fact that it does not maintain, idiots accepted, that matter is merely discrete, but that the discrete parts at various stages, ether atoms, chemical atoms, masses, heavenly bodies, are various nodal points which determine the various qualitative modes of existence of matter in general, right down to weightlessness and repulsion. Transformation of quantity into quality. The simplest example, oxygen and ozone, where 2 out of 3 produces quite different properties, even in regard to smell. Chemistry likewise explains the other allotropic bodies merely by a difference in the number of atoms in the molecule. The significance of names. In organic chemistry, the significance of a body, hence also its name, is no longer determined merely by its composition, but rather by its position in the series to which it belongs. If we find, therefore, that a body belongs to such a series, its old name becomes an obstacle to understanding it, and must be replaced by a series name, paraffins, etc. Biology. Reaction. Mechanical, physical, alias heat, etc. Reaction is exhausted with each occurrence of reaction. Chemical reaction alters the composition of the reacting body and is only renewed if a further quantity of the latter is added. Only the organic body reacts independently, of course within its own sphere of power, in parentheses sleep, and assuming the supply of nourishment. But this supply of nourishment is effective only after it has been assimilated, not immediately as at lower stages, so that here the organic body has an independent power of reaction. The new reaction must be mediated by it. Life and death. Already no physiology is held to be scientific if it does not consider death as an essential element of life. Note Hegel Encyclopedia 1, pages 152 to 53. The negation of life as being essentially contained in life itself, so that life is always thought of in relation to its necessary result, death, which is always contained in it in germ. Footnote. Hegel, Encyclopedia of the Philosophical Sciences, section 81, addendum 1, quote, "Life as such bears in it the embryo of death," unquote. The dialectical conception of life is nothing more than this, but for anyone who has once understood this, all talk of the immortality of the soul is done away with. Death is either the dissolution of the organic body, leaving nothing behind but the chemical constituents that formed its substance, or it leaves behind a vital principle, more or less the soul, that then survives all living organisms, and not only human beings. Here, therefore, by means of dialectics, simply becoming clear about the nature of life and death, suffices to abolish an ancient superstition. Living means dying. Generatio equivoca, spontaneous generation. All investigations hitherto amount to the following. In fluids containing organic matter in decomposition and accessible to the air, lower organisms arise. Protista, fungi, infusoria. Where do they come from? Have they arisen by generatio equivoca, or from germs brought in from the atmosphere? Consequently, the investigation is limited to a quite narrow field, to the question of plasmogony. Footnote. Plasmogony was the term Haeckel used to denote the hypothetical origin of organisms when the organism arises within some organic liquid, in contrast to autogeny, that is, the direct origin of living protoplasm from inorganic matter. End of footnote. The assumption that new living organisms can arise by the decomposition of others belongs essentially to the epoch of immutable species. At that time, men found themselves compelled to assume the origin of all organisms, even the most complicated, by original generation from non-living materials, and if they did not want to resort to the aid of an act of creation, they easily arrived at the view that this process is more readily explicable given a formative material already derived from the organic world. No one any longer believed in the production of a mammal directly from inorganic matter by chemical means. This assumption, however, directly conflicts with the present state of science. By the analysis of the process of decomposition in dead organic bodies, chemistry proves that at each successive step, this process necessarily produces products that are more and more dead, that are more and more close to the inorganic world, products that are less and less capable of being used by the organic world, and that this process can be given another direction, such utilization being able to occur only when these products of decomposition are absorbed early enough in an appropriate, already existing organism. It is precisely the most essential vehicle of cell formation, protein, that decomposes first of all, and so far it has never been built up again. Still more, the organisms whose original generation from organic fluids is the question at issue in these investigations, while being of a comparatively low order, are nevertheless definitely differentiated, bacteria, yeasts, etc., with a life cycle composed of various phases and in part, as in the case of the infusoria, equipped with fairly well-developed organs. They are all at least unicellular, but ever since we have been acquainted with the structureless Monera, it has become foolish to desire to explain the origin of even a single cell directly from dead matter, instead of from structureless living protein. To believe it is possible by means of a little stinking water to force nature to accomplish in 24 hours what it has cost her thousands of years to bring about. Pasteur's experiments in this direction are useless. For those who believe in this possibility, he will never be able to prove the impossibility by these experiments alone, but they are important because they furnish much enlightenment on these organisms, their life, their germs, etc. Footnote: Engels is referring to the experiments on spontaneous generation carried out by Pasteur in 1860. By these experiments, Pasteur proved that microorganisms, bacteria, yeasts, infusoria, in any nutritive organic medium develop only from germs already present in the medium or which reach it from outside. Pasteur concluded that the spontaneous generation of microorganisms and spontaneous generation in general is not possible. End of footnote. Moritz Wagner, Naturwissenschaftliche Streitfragen, Augsburger Allgemeine Zeitung, Beilage, October 6th, 7th, 8th, 1874. Footnote. The extracts from Wagner's article are taken from the Augsburg Allgemeine Zeitung of 1874, pages 4333, 4334, 4351, and 4370. Die Allgemeine Zeitung was a conservative daily founded in 1798. It appeared in Augsburg from 1810 to 1882. End of footnote. Liebig's statement to Wagner towards the end of his life, 1868, quote, "We may only assume that life is just as old and just as eternal as matter itself, and the whole controversial point about the origin of life seems to me to be disposed of by this simple assumption. On point of fact, why should not organic life be thought of as present from the very beginning just as much as carbon and its compounds, or as the whole of uncreatable and indestructible matter in general, and the forces that are eternally bound up with the motion of matter in space?" Unquote. Liebig said further, Wagner believes, November 1868, that he too regards the hypothesis that organic life has been, quote-unquote, imported onto our planet from universal space as, quote-unquote, acceptable. Helmholtz, preface to Thomson's Handbuch der theoretischen Physik, German edition, Part 2, quote, "It appears to me to be a fully correct procedure if all our efforts fail to cause the production of organisms from non-living matter, to raise the question whether life has ever arisen, whether it is not just as old as matter, and whether its germs have been transported from one heavenly body to another, and have developed wherever they found favorable soil." Unquote. Footnote. W. Thomson and P. G. Tate, Handbuch der theoretischen Physik, autorisierte deutsche Übersetzung von Dr. I. T. Helmholtz und G. Wertheim. First volume, second part, Braunschweig, 1874, page 9. Engels quotes from Wagner's article. End of footnote. Wagner, quote, "The fact that matter is indestructible and imperishable, that it can by no force be reduced to nothing, suffices for the chemist to regard it also as uncreatable. But according to the now prevailing view, life is regarded merely as a property inherent in certain simple elements, of which the lowest organisms consist, and which, as a matter of course, must be as old, that is, as originally existing, as these basic stuffs and their compounds themselves. In this sense, one could also speak of vital force, as Liebig does, in parentheses, Chemische Briefe, 4th edition, namely as a quote-unquote formative principle in and together with the physical forces, hence not acting outside of matter. Footnote: see Liebig, Chemische Briefe, 4. Umgearbeitete und vermehrte Auflage, Volume 1, Leipzig und Heidelberg, 1859, page 373. End of footnote. This vital force, as a quote-unquote property of matter, however, manifests itself only under appropriate conditions which have existed since eternity at innumerable points in infinite space, but which in the course of the different periods of time must often enough have changed their place in space." Unquote. Hence, no life is possible on the ancient fluid earth or the present-day sun, but the glowing bodies have enormously expanded atmospheres, consisting, according to recent views, of the same materials that fill all space in extremely rarefied form and are attracted by bodies. The rotating nebular mass from which the solar system developed, reaching beyond the orbit of Neptune, contained, quote, "also all water dissolved in vaporous forms in an atmosphere richly impregnated with carbonic acid up to immeasurable heights, and with that also the basic materials for the existence, in parentheses question mark, of the lowest organic germs." Unquote. In it there prevailed, quote, "most varied degrees of temperature in most varied regions, and hence the assumption is fully justified that at all times the conditions necessary for organic life were somewhere to be found." According to this, the atmospheres of the heavenly bodies, like those of the rotating cosmic nebular masses, would have to be regarded as the permanent repositories of the living form, as the eternal breeding grounds of organic germs. Unquote. In the Andes, below the equator, the smallest living protista, with their invisible germs, are still present in masses in the atmosphere up to 16,000 feet. Purdy says that they are, quote-unquote, almost omnipresent. They are only absent where the glowing heat kills them. For them, in parentheses, Vibrionidae, etc., existence is conceivable, quote, also in the vapor belt of all heavenly bodies, wherever the appropriate conditions are to be found. Unquote. Quote, according to Kohn, bacteria are so extremely minute that 633 million can find room in a cubic millimeter, and 636,000 million weigh only a gram. The micrococci are even smaller, unquote. And perhaps they are not the smallest, but being very varied in shape, quote, the Vibrionidae, sometimes globular, sometimes ovoid, sometimes rod-shaped or spiral, unquote, already possesses therefore a form that is of considerable importance. Quote, hitherto no valid objection has been raised against the well-founded hypothesis that all the multifarious, more highly organized living beings of both natural kingdoms could have developed and must have developed in the course of very long periods of time from such or similar extremely simple, neutral, primordial beings hovering between plants and animals on the basis of individual variability and the capacity for hereditary transmissions of newly acquired characters to the offspring, on alteration of the physical conditions of the heavenly bodies, and on spatial separation of the individual varieties produced. Unquote. Worth noting is the proof how much a dilettante Liebig was in biology, although the latter is a science bordering on chemistry. He read Darwin for the first time in 1861, and only much later the important biological and paleological geological works subsequent to Darwin. Lamarck he had, quote-unquote, never read. Quote, similarly, the important paleontological special researches which appeared even before 1859 of L.V. Buch, D'Orbigny, Munster, Klipstein, Hauer, and Quinstedt on the fossil cephalodos that throw such remarkable light on the genetic connection of the various creations remained completely unknown to him. All the above-mentioned scientists were driven by the force of facts, almost against their will, to the Lamarckian hypothesis of descent, unquote. And this indeed before Darwin's book. Quote, the theory of descent, therefore, had already quietly struck roots in the views of those scientists who had concerned themselves more closely with the comparative study of fossil organisms. As early as 1832, in Obe die Ammoniten und ihre Sonderung in Familien, and in 1848 in a paper read before the Berlin Academy, L.V. Buch very definitely introduced in the science of petrifacts, quote, the Lamarckian idea of the typical relationship of organic forms as a sign of their common descent, unquote. In 1848, he based himself on his investigation of the Ammonites for the declaration, quote, that the disappearance of old forms and the appearance of new ones is not a consequence of the total destruction of organic creations, but that the formation of new species out of older forms has most probably only resulted from altered conditions of life, unquote. Comments. The above hypothesis of so-called eternal life and of importation presupposes 1. The eternal existence of protein, 2. The eternal existence of the original forms from which everything organic can develop. Both are inadmissible. 81. Liebig's assertion that carbon compounds are just as eternal as carbon itself is doubtful, if not false. A. Is carbon simple? If not, it is as such not eternal. B. The compounds of carbon are eternal in the sense that under the same conditions of mixture, temperature, pressure, electric potential, etc., they are always reproduced. But that, for instance, only the simplest carbon compounds, CO2 or CH4, should be eternal in the sense that they exist at all times and more or less in all places, and not rather that they are continually produced anew and pass out of existence again, in fact, out of the elements and into the elements, has hitherto not been asserted. If living protein is eternal in the same sense as other carbon compounds, then it must not only continually be dissolved into its elements, as is well known to happen, but it must also continually be produced anew from the elements, and without the collaboration of previously existing protein, and that is the exact opposite of the result at which Liebig arrives. C. Protein is the most unstable carbon compound known to us. It decomposes as soon as it loses the capacity of carrying out the functions peculiar to it, which we call life, and it is inherent in its nature that this incapacity should sooner or later make its appearance. And it is just this compound which is supposed to be eternal and able to endure all the changes of temperature, pressure, lack of nourishment and air, etc., in space, although even its upper temperature limit is so low, less than 100 Celsius degrees. The conditions for the existence of protein are infinitely more complicated than those of any other known carbon compound, because not only physical and chemical functions, but in addition, nutritive and respiratory functions enter, requiring a medium which is narrowly delimited, physically and chemically, and is it this medium that one must suppose has maintained itself from eternity under all possible changes? Liebig, quote, prefers ceteris paribus, the simpler of the two hypotheses, unquote. But a thing may appear very simple and yet be very complicated. The assumption of innumerable continuous series of living protein bodies, tracing their descent from one another through all eternity, and which under all circumstances always leave sufficient over for the stock to remain well assorted, is the most complicated assumption possible. Moreover, the atmosphere of the heavenly bodies, and especially nebular atmospheres, were originally glowing hot, and therefore no place for protein bodies. Hence, in the last resort, space must serve as the great reservoir, a reservoir in which there is neither air nor nourishment, and with a temperature at which certainly no protein can function or maintain itself. AD 2. The vibrious micrococci, etc., which are referred to here, are beings already considerably differentiated, protein granules that have excreted an outer membrane, but no nucleus. The series of protein bodies capable of development, however, forms a nucleus first of all, and becomes a cell. The cell membrane is then a further advance. Amoeba Pterococcus. Hence the organisms under consideration here belong to a series which, by all previous analogy, proceeds barrenly into a blind alley, and they cannot be numbered among the ancestors of the higher organisms. What Helmholtz says of the sterility of attempts to produce life artificially is pure childishness. Life is the mode of existence of protein bodies, the essential element of which consists in continual metabolic interchange with the natural environment outside them, and which ceases with the cessation of this metabolism, bringing about the decomposition of the protein. Such metabolism can also occur in the case of inorganic bodies, and in the long runs occurs everywhere, since chemical reaction takes place, even if extremely slowly, everywhere. The difference, however, is that inorganic bodies are destroyed by this metabolism, while in organic bodies it is the necessary condition for their existence. If success is ever attained in preparing protein bodies chemically, they will undoubtedly exhibit the phenomena of life and carry out metabolism, however weak and short-lived that may be. But it is certain that such bodies could at most have the form of the very crudest monera, and probably much lower forms, but by no means the form of organisms that have become differentiated by an evolution lasting thousands of years, and in which the cell membrane has become separated from the contents and a definite inherited form assumed. So long, however, as we know no more of the chemical composition of protein than we do at present, and therefore for probably another 100 years to come cannot think of its artificial preparation, it is ridiculous to complain that all our efforts, etc., have failed. Again, the above assertion that metabolism is the characteristic activity of protein bodies may be put the objection of the growth of Traube's so-called artificial cells. Footnote: Traube's artificial cells, inorganic formations representing replicas of living cells, and capable of reproducing metabolism and growth, and serving to investigate various aspects of vital phenomena. They were created by M. Traube, a German chemist and physiologist, through mixing colloidal solutions. Traube reported on his experiments at the 47th Congress of German Natural Scientists and Physicians in Breslau on September 23, 1874. Marx and Engels had a high opinion of Traube's discovery. See Marx's letter to P. L. Lavrov, dated June 18, 1875, and W. A. Freund, dated January 21, 1877. End of footnote. But here there is merely unaltered absorption of a liquid by endosmosis. While metabolism consists in the absorption of substances, the chemical composition of which is altered, which are assimilated by the organism, and the residue of which are excreted together with the decomposition products of the organism itself resulting from the life process. In B, just as we have to speak of invertebrate vertebrates, so also here the organized, formless, undifferentiated granule of protein is termed an organism. Dialectically this is permissible, because just as the vertebral column is implicit in the notochord, so in the protein granule on its first origin, the whole infinite series of higher organism lies included, quote-unquote in itself, as if in embryo. The significance of Traube's so-called cells lies in the fact that they show endosmosis and growth as two things which can be produced also in inorganic nature and without any carbon. The newly arisen protein granule must have had the capacity of nourishing itself from oxygen, carbon dioxide, ammonia, and some of the salts dissolved in the surrounding water. Organic nutritive substances were not present, but the granules surely could not devour one another. This proves how high above them are the present-day Monera, even without nuclei living on diatoms, etc., and therefore presupposing a whole series of differentiated organisms. Dialectics of Nature. References. Nature, number 294, et seq. Alman on Infusoria. Unicellular character important. Footnote. Engels is referring to Alman's paper Recent Progress in Our Knowledge of the Ciliate Infusoria, delivered to the Linnaeus Society on May 24, 1875, and printed in numbers 294, 295, and 296 of the British journal Nature of June 17th and 24th and July 1st, 1875. End of footnote. Kroll on ice periods and geological time. Footnote. Engels is referring to the review of Kroll's book Climate and Time in Their Geological Relations, a theory of secular changes of the Earth's climate. London, 1875, printed in Nature, numbers 294, 295, of June 17th and 24th, 1875, and signed J.F.B. End of footnote. Nature, number 326, Tyndall on generatio, specific decay and fermentation experiments. Footnote. Engels is referring to Tyndall's article on the optical department of the atmosphere in reference to the phenomena of putrefaction and infection, which was an abstract of a paper read before the Royal Society on January 13, 1876. The article was published under the heading Professor Tyndall on Germs in Nature, numbers 326 and 327 of January 27th and February 3rd, 1876. End of footnote. Protista 1. Non-cellular. Begin with a simple granule of protein which extends and withdraws pseudopodia in one form or another, including the Monera. The Monera of the present day are certainly very different from the original forms, since for the most part they live on organic matter, swallowing diatoms and infusoria, that is, bodies higher than themselves, and which only arose after them, and as Haeckel's Plate 1 shows, have a developmental history and pass through the form of non-cellular ciliate swarm spores. Footnote. Haeckel, Natürliche Schöpfungsgeschichte, 4th German edition, Berlin, 1873. Plate 1 occurs between pages 168 and 169 of this edition, and the letterpress to it on page 664. End of footnote. The tendency towards form which characterizes all protein bodies is already evident here. This tendency is more prominent in the non-cellular foraminifera, which excrete highly artistic shells, anticipating colonies, corals, etc., and anticipate the higher mollusks in form just as the tubular algae, Siphonae, anticipate the trunk, stem, root, and leaf form of higher plants, although they are merely structureless protein. Hence, protamoeba is to be separated from amoeba. Engels' note in the margin, individualization small, they divide and also fuse. End of Engels' note in the margin. 2. On the one hand, there arises the distinction of skin, ectosarc, and medullary layer, endosarc, in the sun animalcule actinopris sol, in parentheses Nicholson, page 49. Footnote: Engels is referring to the book of Nicholson, A Manual of Zoology. End of footnote. The epidermal layer puts out pseudopodia in Protomyxa aurintachia. This stage is already a transitional one. See Haeckel, plate 1. Along this line of evolution, protein does not appear to have got very far. 3. On the other hand, the nucleus and nucleolus become differentiated in the protein, naked amoeba. From now on, the development of form proceeds apace. Similarly, the development of the young cell in the organism, compare Wundt on this, at the beginning. Footnote: Engels is most probably referring to Wilhelm Wundt's Lehrbuch der Physiologie des Menschen. It was first published in Erlangen in 1865. A second and a third edition appeared in the same town in 1868 and 1873. End of footnote. In amoeba, Spherococcus, as in Protomyxa, the formation of the cell membrane is only a transitional phase, but even here there is already the beginning of the circulation in the contractile vacuoli. Haeckel, page 380. Sometimes we find either a shell of sand grains stuck together, in parentheses Difflugia, Nicholson, page 47, as in worms and insect larvae, sometimes a genuinely excreted shell. Finally, 4. The cell with a permanent cell membrane. According to Haeckel, page 382, out of this has arisen, depending on the hardness of the cell membrane, either plant or, in the case of a soft membrane, animal. In parentheses, it certainly cannot be conceived so generally. With the cell membrane, definite and at the same time plastic form makes its appearance. Here again a distinction between simple cell membrane and excreted shell. But, in contrast to number 3, the putting out of pseudopodia stops with this cell membrane and this shell. Repetition of earlier forms, ciliate swarm spores, and diversity of form. The transition is provided by the labyrinthuli, Haeckel, page 385, which deposit their pseudopodia outside and creep about in this network with alteration of the normal spindle shape kept within definite limits. The Gregorinio anticipate the mode of life of higher parasites. Some are already no longer single cells, but chains of cells. Haeckel, page 451, but only containing 2 to 3 cells, a weak beginning. The highest development of unicellular organisms is in the infusoria, insofar as these are really unicellular. Here a considerable differentiation. See Nicholson. Once again, colonies and zoophytes, in parentheses epistylis. Footnote: Zoophytes, pflanzentiere, animal plants, a term applied from the 16th century onwards to a group of invertebrates, mostly sponges and coelenterates, possessing certain characteristics that were considered indicative of plants, such as a sessile way of life. The zoophytes were therefore regarded as forms intermediate between plants and animals. In the mid-19th century, the term became a synonym for coelenterate. It is no longer used. End of footnote. Among unicellular plants, likewise, a high development of form. Desmidiaceae, Haeckel, page 410. Engels note in the margin, rudiment of higher differentiation. End of note in the margin. 5. The next advance is the union of several cells into one body, no longer colony. First of all, the calacto of Haeckel, Magosphaera planula, Haeckel, page 384, where the union of the cells is only a phase of development. But here also there are already no pseudopodia. Whether there are any as a transitional phase, Haeckel does not state exactly. On the other hand, the radiolaria, also undifferentiated masses of cells, have retained their pseudopodia and have developed to the highest extent the geometric regularity of the shell, which plays a part even among the genuinely non-cellular rhizopods. The protein surrounds itself, so to speak, with its crystalline form. 6. Megasphaera planula forms the transition to the true planula and gastrula, etc. Further details in Haeckel, page 452 etc. Footnote. In the fourth edition of his book, Natürliche Schöpfungsgeschichte, Haeckel enumerates the following first 5 stages of development of the embryo in multicellular animals: monerula, ovulum, morula, planula, and gastrula, which, according to him, correspond to the 5 initial stages of the development of animal life as a whole. In the later editions of the book, Haeckel substantially altered this scheme, but his basic idea, to which Engels gave a positive appraisal, the idea of the parallelism between the individual development of an organism, autogeny, and the development of a particular form in the course of evolution, phylogeny, has become firmly established in science. End of footnote. Bathybius. Footnote. The word bathybius means living in the depths. In 1868, Huxley described a sticky slime dredged from the bottom of the ocean, which he regarded as primitive, structureless living matter protoplasm. In honor of Haeckel, he named this, as he thought, simplest living organism, Bathybius haeckeli. Haeckel considered the Bathybius as a species of modern, still living Monera. Afterwards, it was demonstrated that the Bathybius has nothing in common with protoplasm and is an inorganic form. Haeckel speaks of Bathybius and the small calcareous modules enclosed in it on pages 165 to 66, 306, 379 of the fourth edition of his Natürliche Schöpfungsgeschichte, Berlin, 1873. End of footnote. The stones in its flesh are proof that the original form of protein, still lacking any differentiation of form, the germ of, and capacity for, skeletal formation. The individual. This concept also has been dissolved into something purely relative. Cormus, colony, tapeworm, on the other hand, cell and metamere as individuals in a certain sense, anthropogeny and morphology. Footnote. In the first volume of his Generelle Morphologie der Organismen, Berlin 1866, Haeckel deals in 4 large chapters, chapters 8 to 11, with the concept of the organic individual and with the morphological and physiological individuality of organisms. He also considers the notion of individual in a number of passages of Anthropogenie oder Entwicklungsgeschichte des Menschen, Anthropology or a History of the Evolution of Man, Leipzig, 1874. He divides organic individuals into 6 classes or orders: plastids, organs, antimeres, metameres, individuals, and cormuses. The individuals of the first order are pre-cellular organic forms of the Monera, in parentheses, cytode, type and cells. They are, quote-unquote, elementary organisms. The individuals of each order, beginning with the second, consist of individuals of the preceding order. The individuals of the fifth order are, in the case of superior animals, so-called individuals in the narrow sense of the term. Cormus, a morphological individual of the sixth order, representing a colony of individuals of the fifth order. The series of marine lucifers may serve as an example. Metamere, a morphological individual of the fourth order, the recurrent limb of the individual of the fifth order. The segments of the tapeworm may serve as an example. End of footnote. The whole of organic nature is one continuous proof of the identity or inseparability of form and content, Morphological and physiological phenomena, form and function, mutually determine one another. The differentiation of form, the cell, determines differentiation of substance into muscle, skin, bone, epithelium, etc., and the differentiation of substance in turn determines difference of form. Repetition of morphological forms at all stages of evolution. Cell forms, the two essential ones already in gastrula, metamere formation at a certain stage, annelids, arthropods, vertebrates. In the tadpoles of amphibians, the primitive form of ascidian larvae is repeated. Various forms of marsupials, which recur among placentals, even counting only existing marsupials. For the entire evolution of organism, the law of acceleration, according to the square of the distance in time from the point of departure, is to be accepted. Compare Haeckel, Schöpfungsgeschichte, and Anthropogeny, the organic forms corresponding to the various geological periods. The higher, the more rapid the process. The Darwinian theory to be demonstrated as the practical proof of Hegel's account of the interconnection between necessity and chance. The struggle for existence. Above all, this must be strictly limited to the struggles resulting from plant and animal overpopulation, which do in fact occur at certain stages of plant and lower animal life. But one must keep sharply distinct from it the conditions in which species alter, old ones die out, and newly evolved ones take their place, without this overpopulation. For example, on the migration of animals and plants into new regions, where new conditions of climate, soil, etc. bring about alteration. If there, the individuals which become adapted survive and develop into a new species by continually increasing adaptation, while the other more stable individuals die away and finally die out, and with them the imperfect intermediate stages, then this can and does proceed without any Malthusianism. And if the latter should occur here at all, it makes no change to the process. At most it can accelerate it. Similarly, with the gradual alteration of the geographical, climatic, etc. conditions in a given region, drying up of Central Asia, for instance. Whether the members of the animal or plant population there exert pressure on one another is a matter of indifference. The process of evolution of the organisms that is determined by this alteration proceeds all the same. It is the same for sexual selection, in which case too Malthusianism is quite unconcerned. Hence also Haeckel's so-called adaptation and heredity can bring about the whole process of evolution without need for selection and Malthusianism. Darwin's mistake lies precisely in lumping together, in so-called natural selection, or the so-called survival of the fittest, two absolutely separate things. One, selection by the pressure of overpopulation, where perhaps the strongest survive in the first place, but can also be the weakest in many respects. Two, selection by greater capacity of adaptation by altered circumstances, where the survivors are better suited to these circumstances, but where this adaptation as a whole can mean regress just as well as progress. For instance, adaptation to parasitic life is always regress. Footnote. Natural selection, or the survival of the fittest, is the title of Chapter 4 of Darwin's The Origin of Species by Means of Natural Selection, or the Preservation of Favored Races in the Struggle for Life. End of footnote. The main thing, that each advance in organic evolution is at the same time a regression, fixing one-sided evolution and excluding the possibility of evolution in many other directions. This, however, a basic law. The struggle for life. Footnote. The contents of this note are almost identical with those of Engels' letter to Lavrov of November 12, 1875. End of footnote. Until Darwin, what was stressed by his present adherents was precisely the harmonious cooperative working of organic nature, how the plant kingdom supplies animals with nourishment and oxygen, and animals supply plants with manure, ammonia, and carbonic acid. Hardly was Darwin recognized before these same people saw everywhere nothing but struggle. Both views are justified within narrow limits, but both are equally one-sided and prejudiced. The interaction of bodies in non-living nature includes both harmony and collision, that of living bodies, conscious and unconscious cooperation, as well as conscious and unconscious struggle. Hence, even in regard to nature, it is not permissible one-sidedly to inscribe only so-called struggle on one's banners. But it is absolutely childish to desire to sum up the whole manifold wealth of historical evolution and complexity in the meager and one-sided phrase, struggle for existence. That says less than nothing. The whole Darwinian theory of the struggle for existence is simply the transference from society to organic nature of Hobbes's theory of bellum omnium contra omnes, and of the bourgeois economic theory of competition, as well as the Malthusian theory of population. Footnote: Bellum omnium contra omnes, a war of all against all, an expression used by T. Hobbes in his writing De Cive, of the Citizen, a preface to the Reader, and Leviathan, chapters 13 and 14. End of footnote. When once this feat has been accomplished, the unconditional justification for which, especially as regards the Malthusian theory, is still very questionable, it is very easy to transfer these theories back again from natural history to the history of society, and altogether too naive to maintain that thereby these assertions have been proved as eternal natural laws of society. Let us accept for a moment the phrase struggle for existence for argument's sake. The most that the animal can achieve is to collect. Man produces. He prepares the means of life in the widest sense of the words, which without him nature would not have produced. This makes impossible any unqualified transference of the laws of life in animal societies to human society. Production soon brings it about that the so-called struggle for existence no longer turns on pure means of existence, but on means of enjoyment and development. Here, where the means of development are socially produced, the categories taken from the animal kingdom are already totally inapplicable. Finally, under the capitalist mode of production, production reaches such a high level that society can no longer consume the means of life, enjoyment, and development that have been produced, because for the great mass of producers access to these means is artificially and forcibly barred, and therefore every 10 years a crisis restores the equilibrium by destroying not only the means of life, enjoyment, and development that have been produced, but also a great part of the productive forces themselves. Hence, the so-called struggle for existence assumes the form to protect the products and productive forces produced by bourgeois capitalist society against the destructive, ravaging effects of this capitalist social order, by taking control of social production and distribution out of the hands of the ruling capitalist class, which has become incapable of this production, and transferring it to the producing masses, and that is the socialist revolution. The conception of history as a series of class struggles is already much richer in content and deeper than merely reducing it to weakly distinguished phases of the struggle for existence. Vertebrates, their essential character, the grouping of the whole body about the nervous system. Thereby the development of self-consciousness, etc., becomes possible. In all other animals the nervous system is a secondary affair. Here it is the basis of the whole organism. The nervous system, when developed to a certain extent, by posterior elongation of the head, ganglion of the worms, takes possession of the whole body and organizes it according to its needs. When Hegel makes the transition from life to cognition by means of propagation, in parentheses, reproduction, there is to be found in this the germ of the theory of evolution, that organic life, once given, it must evolve by the development of the generations to a genus of thinking beings. Footnote. Hegel, Science of Logic, Book 3, Section 3, Chapter 1. End of footnote. What Hegel calls reciprocal action is the organic body, which therefore also forms the transition to consciousness, that is, from necessity to freedom to the idea. See Logic 2, Conclusion. Footnote. Engels is referring to the end of the second part of Hegel's Logic, Science of Logic, Book 2, Section 3, Chapter 3, Reciprocity, and Encyclopedia of the Philosophical Sciences, Part 1, Section 2, Reciprocity. Here Hegel himself mentions the living organism as an instance of interaction. Quote, individual organs and functions likewise prove to be in a relation of interaction towards each other. Unquote. Encyclopedia, Section 156, Addendum. End of footnote. Rudiments in nature. Insect states, the ordinary ones, do not go beyond purely natural conditions. Here even a social rudiment. Ditto productive animals with tools, bees, etc., beavers. But still only subsidiary things and without total effect. Even earlier, colonies of corals and hydrozoa, where the individual is at most an intermediate stage and the fleshy community mostly a stage of the full development. See Nicholson. Footnote. H. A. Nicholson, A Manual of Zoology, 5th edition, Edinburgh and London, 1878, pages 32, 102. End of footnote. Similarly, the infusoria, the highest and in part much differentiated form which a single cell can achieve. Work. The mechanical theory of heat has transferred this category from economics into physics, for physiologically it is still a long way from having been scientifically determined, but in doing so it becomes defined in quite a different way, as seen even from the fact that only a very slight, subordinate part of economic work, lifting of loads, etc., can be expressed in kilogram meters. Nevertheless, there is an inclination to retransfer the thermodynamical definition of work to the sciences from which the category was derived, with a different determination. For instance, without further ado, to identify it crudely with physiological work, as in Fick and Wislicenus's Faulhorn experiment, in which the lifting of a human body of, say, 60 kilograms to a height of, say, 2,000 meters, that is, 120,000 kilogram meters, is supposed to express the physiological work done. Footnote. Faulhorn, a peak in the Bern Alps, Switzerland. End of footnote. In the physiological work done, however, it makes an enormous difference how this lifting is effected, whether by positive lifting of the load, by mounting of vertical ladders, or whether along a road or stair with 450 slope equals militarily impracticable terrain, or along a road with a slope of 1/18, hence a length of about 36 kilometers. But this is questionable if the same time is allowed in all cases. At any rate, however, in all practicable cases a forward motion is also combined with the lifting, and indeed, where the road is quite level, this is fairly considerable, and as physiological work, it cannot be put equal to zero. In some places there even appears to be not a little desire to re-import the thermodynamical category of work back into economics, as with the Darwinists and the struggle for existence, the result of which would be nothing but nonsense. Let someone try to convert any skilled labor into kilogram meters, and then to determine wages on this basis. Physiologically considered, the human body contains organs which in their totality, from one aspect, can be regarded as a thermodynamical machine, where heat is supplied and converted into motion. But even if one presupposes constant conditions as regards the other bodily organs, it is questionable whether physiological work done, even lifting, can be at once fully expressed in kilogram meters, since within the body internal work is performed at the same time, which does not appear in the result. For the body is not a steam engine which only undergoes friction and wear and tear. Physiological work is only possible with continued chemical changes in the body itself, depending also on the process of respiration and the work of the heart. Along with every muscular contraction or relaxation, chemical changes occur in the nerves and muscles, and these changes cannot be treated as parallel to those of coal in a steam engine. One can, of course, compare two instances of physiological work that have taken place under otherwise identical conditions, but one cannot measure the physical work of a man according to the work of a steam engine, etc. Their external results, yes, but not the processes themselves, without considerable reservations. In parentheses, all this has to be thoroughly revised.